Hello, good morning, everyone. Good morning, everyone, for joining today's International Conference on Solar Energy Materials and Technology 2022. And it's a great pleasure to have on board many people from different countries. So, without wasting any more times, let's welcome everyone. My dear colleagues, professors, lecturers, researchers, students, ladies and gentlemen. On behalf of the University of Exeter, I would like to express my sincere gratitude and welcome you to the 2 days virtual International Conference on Solar and Energy Materials and Technology, in short, ICSEMT 2022. It is a great pleasure for me to declare open and warmly welcome our honorable plenary speakers, guest speakers, early career researcher speakers, and delegates across the world. I hope the ICSEMT 2022 will achieve its objective of providing an effective forum for academicians, researchers, and practitioners to advance knowledge, research, and technology for humanity. There has been always a gap between people, communities who can effectively use technology and those who can't. It is high time that such an event took place to highlight the remarkable contribution that solar and energy materials and their applications that make in so many areas of our lives. Glance through the list of presentations planned for the next couple of days reveals the amazing diversity of these applications. Today, I would like to focus on 4 actions that will get us here. First, the current solar energy status, recent development, and is there any saturation? Second, energy harvesting materials and their progression. Battery, supercapacitor, energy storage material, solar fuel, and photocatalyst. The role of material, design, and their performance impact. Third, cooperating closely with industry to advance projects and innovation and giving the sector the predictability it needs. Finally, building a truly global connection and interdisciplinary research and development relation. It's my pleasure to walk you through the conference and introduce you to the speakers and delegates from all over the country today to share their knowledge and enhance our research horizon. Today's conference has about 350 participants registered from more than 15 countries, making this conference a truly international conference in spirit, a mutual industrial and academic perspective into the development of action research. The impact on research in progress prior to COVID-19 was rapid, dramatic, and no doubt will be long-term. The pandemic curtailed most academic, industry, and government basic science, clinical research, and redirected research to COVID-19. The pandemic has created unprecedented challenges for the research and innovation community, with profound impacts on institutions and businesses and on the people working in them. I believe this conference can develop world-class early career research staff through generic research-related skills acquisition, team working, and networking opportunities, and ensure our early career researchers are globally competitive and effective in their research. We are recording this event and live streaming into the ESI Facebook page. So your camera is turned off and you are on mute, so you will not be seen or heard. But if you prefer to be completely anonymous, you can change your name on screen. With this, I would like to conclude my speech by encouraging the delegates to participate in more activities and discussion throughout us for the next 2 days. I wish you a very productive conference with exciting and encouraging discussion and knowledge exchange so that together we can anticipate a future groundbreaking expertise, research, and technology for humanities. We are proud to be celebrating Environment and Sustainability Institute's first decade of successful operation. Our strapline is working with natural systems for sustainable futures, and our events will highlight the research, opportunities, and new thinking being done on campus, past and present. With this, I would like to take the opportunity to welcome Professor Jane Wills, who is the director of ESI, University of Exeter, to say a few words to the audience on behalf of ESI. Professor Jane has been tracking the development of the Living Wage campaign since it was launched in Walthamstow, East London in 2001. Since moving to the University of Exeter and working in Cornwall, her focus has shifted to public and policy engagement for sustainability. Her philosophical interests are reflected in a recent editorial volume of The Power of Pragmatism, Knowledge Production and Social Inquiry. Let me close by wishing you a delightful and stimulating day. Thank you so much, and over to you, Professor Jane.
Thank you very much, Anurag. It has been a marvelous thing to watch you organise this conference. Many congratulations and good morning to everybody who's joining us. I'm hoping to just share a few slides with you to give you a flavour of what the ESI, which is the Environment and Sustainability Institute, is all about. So hopefully you can now see these slides. So a very warm welcome from us. The reason I'm here is that I'm proud that we are the home to your hosts for this conference. So Dr. Anurag Roy, you just met, is a postdoctoral researcher with the solar team in the Environment and Sustainability Institute, and he's part of a group of solar researchers led by Professor Tapas Malik and Professor Asif Tahir, who you will hear from very shortly. We're really proud of the work that they've been doing for a decade now, building on the work that you'll hear about today and putting energy at the centre of what we do in the Environment and Sustainability Institute. So just a little bit of background. The picture there shows you our building. The ESI opened in 2013. As Anurag says, we're now celebrating our first decade. There's about 30 academics at the core of the building, and they come from a very, very wide range of disciplines. So we have ecologists and microbiologists, sustainable mining engineers, mathematicians, landscape ecologists, through to politics professors and cultural historians, all working together on a shared concern around environmental change and the need for greater sustainability solutions. Around those 30 there, we have about 200 early career researchers, postdoctoral researchers, PhD students, technicians, professional service support, and it's a really lovely community to share ideas. We organise that work around 3 E's: ecosystems, energy and engagement. And you'll see that the energy is in the middle and it's really central to everything we do, delivering our strapline, as Anurag said, working with natural systems for sustainable futures. So I thought I should just say a little bit about geography, because I am a geographer by background. Geography really matters. So if you can imagine, and I know a lot of you are located outside the UK, if you can see the map there on the right of the screen, that shows you the red bit is southwest England. And we're in the further southwest of the southwest. We're in the bit sticking out right at the end called Cornwall, and our building is in Penryn. And that, I think, is very salient for the kinds of issues we're researching, because we are blessed. It's a very rural area and we're blessed with a richness of natural capital. You can see it in the landscape here, but you've also got under the ground, the geology is particularly important in terms of geothermal heat that's now being developed, but also the critical minerals and metals that will be needed for the new industrial revolution that you're all researching So there are deposits of lithium which are now being explored for extraction. We're blessed by the marine environment right around us, so we have lots of blue natural capital, and we're now in the process of developing offshore wind in Cornwall, which again you might hear more about later on. And we are blessed obviously with solar energy too. So we have this unique concentration, for the UK anyway, of 5 different types of natural capital all coming together in a community that's got a long, proud history and is relatively well organised to try and think about how we develop new paths for regional development by building on these natural capital endowments in ways that don't destroy them for future generations. So you can see we've got the brown, the green, the blue, the yellow, the solar at the top there, and wind power all coming together in our place. And I think that shapes the kinds of work we do and why we put energy at the centre of everything we're doing. This slide just gives you a flavour of some of the important research that's going on at the ESI, and you can look at our website, sign up for our social media to find out more about what we're doing. But it's remarkable that a relatively small group of researchers cover such a range of pressing issues, from microbiology and antimicrobial resistance at one end, through to public policy and how we manage our resources so we don't destroy them for future generations at the other. And in the centre, as I said, has been this long-standing work on energy and solar energy in particular, led by Professor Tapas Malik, who will talk to you shortly, and his colleagues. So energy is central to what we do on the campus, and while we are focused on solar energy in the ESI, there are colleagues on campus in the Department of Renewable Energy who teach and research across a broad spectrum of renewable technologies: solar, wind, wave, tidal, geothermal, hydrogen, new storage solutions. And I think actually I've missed off their methane, which is another area that Tapas might touch on, that has been developed here in relation to the dairy industry and slurry pits and so on. So there's a lot going on. It's a really exciting place to be doing this work. We do teaching programs, if anyone's interested in those, for undergraduate programs and master's programs in renewable energy engineering and sustainable energy futures. So that's enough from me, just to say that these are really the hosts for your conference today. This is our solar energy team in the ESI. It's small but perfectly formed. I looked at some data yesterday, and since 2017, they've brought in, getting on for £6 million of research income directly, but are part of much bigger collaborative projects stretching across the world. Many of you are involved in them. At the moment, there are 22 PhD students working with them, and there's been 600 outputs of PhD theses and journal articles since 2017. I just wanted to put in a slide there to Professor Senthil Sundaram, who has been part of that work, but recently left to go and work at Napier, and I think he might be joining as well during the conference. So they're a wonderful team, and we're really pleased and proud to have them with us in the ESI. So that's my last slide, to say have a wonderful conference. We're really pleased to be hosting it, and big support to Anurag for all the work he's done. Really pleased you're joining us, and I hope it's a very successful 2 days. Thank you. Stop sharing. I will now hand over to Asif and Tapas, I think.
Thank you, Jen. Thank you, Professor Jen. Anurag, good morning, everybody. It is also my pleasure to welcome all of you. While I do that, I will just share my screen. I think you can see my screen.
Yes, it is visible. Yeah.
Perfect. Thank you. It is also my great pleasure to welcome all of you from around the world in this particular solar energy conference. And as Jen said, we've been here about just over a decade now, beginning of 2013. So I will give you some of the journeys, what we have come through during the last decade in terms of the research and development we have made. And also my colleague Professor Tahir is here, and he will talk to you about the particular type of research we are engaged with many countries around the world and many collaborators in this context. As Professor Jane Will says, that the solar energy group was one of the first cohort in the ESI. It started back in 2013, and it was in fact a very handful number of people, along with me, only 3 other people, researchers, started in 2013 February, when the solar was a part of ESI. So as you can see, in 2013, we had only 3 PhDs and 1 postdocs along with me, starting the solar energy as a basic research of the within the ESI. But within no time, we expanded that to quite significantly a number of researchers. In 2014, 2 of my other colleagues started, Professor Tahir and Professor Sundaram, who is moved to in Edinburgh Napier University very recently. And along the way, we had number of obviously postdocs, publications, continuously attracted research funding for all sort of research councils, the European Union, so Horizon 2020, GCRFs, Royal Academy of Engineering, primarily on the UKRI, EPSRC's research funding. Also, we have had a large number of engagement between UK and India context. So over that period, some of the largest achievements what we have got in 2017, ESI also developed one of the first spin-out companies within the ESI, which is called the Build Solar, developing solar technologies. You will hear more of those, and quite a large number of talks you will be hearing later on from various members. And just to summarize from my side is the ESI Solar Group is continually developing, has a very strong collaborations, not only within the country, but outside the country also, internationally, something like 28% the female within that cohort, and also 60% BAME categories. It's a very multinational team, and we have a very successful solar energy programs. You will be hearing a lot of our research, particularly later on during the talks, but I would like to welcome you to have a very great conference in that sense. So I will give it to my colleague, Professor Tahir, to talk through some of the research, what we are doing as of today. Professor Tahir.
Thank you very much, Professor Tapas. And first of all, it's my pleasure to welcome you all in this exciting conference. So I would like to give a very brief overview of the research activities or the solar activities which we cover at ESI. So in ESI, we are covering majority of the solar related research, starting from the material development involving the theoretical simulation, DFT calculations, and design of material using the in-house fabrication technologies to make those materials in the form of nanoparticles, nanopowders, composites, thin films, coating. And then we use those materials to build devices and we have excellent facilities to test those devices in-house. And from devices, we go one step further to build a system level design and evaluation of those systems for real life applications in terms of solar energy. And we got unique facilities to do those ones. Majority of our focus is on starting from solar fuel and energy storage devices. So if we are really looking for a transition from fossil fuel to renewable fuel, we need to have a transportable and storable fuel. And in this respect, we are focusing to develop materials which are able to split water into hydrogen. And then we are also looking on how we can store hydrogen for zero emission fuel to fulfill the net zero target sets by the UK government as well as by the world in COP27 very recently. And then we are going from a step further, looking onto those materials in photocatalysis for wastewater treatment and providing a clean water for remote communities to establishing some of the techniques which can be bespoke and can be used for remote areas instead of having a standalone using a standalone system. And we also focus on a lot of simulation. And this simulation is not the material simulation, which is like the computational chemistry and things. We also do a lot of simulation work to simulate the energy performance of the building, heat transfer through on to the concentrated photovoltaics, for thermal energy storage and related areas. And we are also focusing on smart windows and building energy efficiency. So recently we have a 1.6 million EPSRC project to develop a composite materials which enable transparent envelope of the building to become much more energy efficient. So in winter, it will stop heat loss, and by flipping in summer, so it will stop heat gain. So in this way, we can reduce the energy consumption of the building to make buildings more energy efficient, as well as making the design more user friendly, so that it can have both the elements of the daylighting as well as comfort. Then we are focusing on soiling losses and anti-soiling coatings. So whenever the solar panels are outside, so there are a lot of issues of accumulating dust onto them, which affect their efficiency and things. So we are designing materials which makes them self-cleaning and overcome the challenge of soiling losses and dust accumulation onto the solar cells. And the one of the most developed area in solar energy is the concentrated photovoltaics, where Professor Tapas has high level expertise, and we are looking to the next stage of the solar cells, where we are looking to concentrate the sunlight to reduce the material use, as we know that silicon is one of the costly component of the material, as well as the concentrated photovoltaic reduce the size, so that can also be used in locations where the normal photovoltaic or solar panels are not effective due to their larger size. On the other hand, this technology is also looking into the building integrated solar applications. So instead of having a rooftop or solar panels where we need to use a lot of land, so we can make our building as a part of the energy generation. So making the buildings as energy machines. So one of the example is the development of the Build Solar Spin-out company, which is now we are putting to make development of a large scale application or building where these build solar bricks will be actually deployed for the energy conversion and applications, so that the technology can go from one step beyond the lab for the customer and users. On the other hand, we are also looking onto the second and third generation solar cell technologies to overcome the challenges. Especially, we are focusing on a flexible substrate for dye-sensitized solar cell, as well as onto the thin film solar cells, so that we can also have the applications for indoor light harvesting and making some of the inside decorations as energy machines to generate energy applications. So from the screen, you can see that we are starting from the basic of making the materials from the first hand, developing a new materials for solar energy applications, and then to take them around for a range of applications to test, to develop, to make the devices, and then going a step forward to develop systems and evaluating those systems in real environmental conditions, not only inside the lab. And from the picture, as from the previous slide, you have seen that we have a very diverse group of researchers, which include a range of nationalities. So currently we have a team from 11 nationalities, which composed of a good ratio between the male and females. So we are strongly collaborating with the institutes and industry around the world to bring more knowledge and exchange knowledge with what we do. And thank you very much. And that's a brief overview from the solar energy technologies. And it's my pleasure again to welcome you into this exciting conference.
Thank you very much, Professor Tapas and Professor Asif, for your time and introduce solar energy research in front of the whole this conference participants. Thank you for your time. Now we will move to Professor Mark Goodwin's talk, and we are so privileged to have Professor Mark with us today. Professor Mark Goodwin leads on global engagement for the university. He is responsible for delivery of the university's global strategy and has oversight of all of the university's global activities, including student recruitment and global partnerships. Our growing portfolio includes significant strategic partnership with international universities, including the University of Queensland and the Chinese University of Hong Kong. He became the Deputy Vice Chancellor at Exeter in 2013, having previously been Dean of the College of Life and Environmental Sciences. He graduated in Geography from the University of Sussex, UK, before completing his PhD at the London School of Economics. It is our great pleasure to welcome on board Professor Mark. Over to you.
Thank you very much, Anurag. I think you know more about me than I do. So thank you for that very kind invitation. It's great to be here, and it's an absolute delight to be speaking to you at the conference this morning. It's also a great delight to me that this conference is a collaboration between Exeter and King Fahd University of Petroleum and Minerals. I had the pleasure of going to Dammam earlier this year, and I visited King Fahd. So it's absolutely great to see our two universities working together to put on this wonderful event. What I was going to do is just to talk through Exeter's global activities as a context for the conference. So to provide some sort of background for you so that you can see where this fits into what Exeter is doing more broadly. So Exeter's global strategy is centered around these 5 interconnected pillars: global partnerships, and I'll say more about those later because I think that's the crucial element of this conference. So I'll focus on global partnerships, global student recruitment, global experiences, global alumni and advancement, and global reputation. And those are the 5 pillars that make up our global strategy. So as I say, I'll come back to global partnerships in a minute. I'll just say a few words about student recruitment. This is really important because, as you've just heard, Exeter wants to be a diverse and multicultural institution. Many of our staff and about a quarter of our students are international. Our students come from about 185 different countries. Our staff come from about 110 different countries. It's wonderful for us to have that diverse culture. It's also important that we provide every opportunity for students around the world to be able to study with us, whether that's at undergraduate level or at postgraduate level. So it's very important to us that we maintain and indeed increase our percentage of international students, because we want to provide those opportunities for students. As I say, at the moment, we're probably just under 25% international. We want to increase that, and we will be increasing that in the years to come. So we'll be pushing that up much more towards 35% and potentially even higher. Again, as a way of recruiting the very best students from across the globe, this becomes really important to us. It's also important to us to offer global experiences for our staff and our students. We want our staff to make connections with the best researchers internationally, and you can see that that's very much happened in the area of solar energy, and Tapas and the team have done a fantastic job in building those connections. I'll say a bit more about them later. But it's important for all of our staff to be able to do that, to be able to work with the top academics internationally. So we provide financial support for our staff. We encourage our staff to spend some of their time working internationally. We provide finances for them to go overseas, to work with partners for periods of 3 or 4 weeks or 2 or 3 months. And we're very happy for our staff to do that and to engage with the best international staff working in their subjects. But also we want to provide global experiences for our students. So we are encouraging our students to spend some of their time studying internationally, whether that's for a term, whether that's for a year, could even be for a month. But we want all of our students to have that opportunity to spend at least some of their time overseas. And if they can't actually physically travel, then we want to open up opportunities for our students to learn online with students from other countries. So we're now developing joint courses. We're developing a joint master's course, for instance, with the University of Queensland on global environmental futures that will be taught online by staff from Exeter and Queensland to give students access to the very best staff in both those institutions. We're developing joint modules with universities across the globe. And we're also developing courses with more than one institution. So we've just run for the first time last year a new course for our students called Future 17. It's called Future 17 because it has a focus on the 17 UN Sustainable Development Goals. And what happens in that course is that our students come together with students from the University of Sao Paulo, the University of Stellenbosch in South Africa, and the Chinese University of Hong Kong. to study projects that external partners set them linked to the UN Sustainable Development Goals. And these external partners are sourced by QS, who do the world rankings, and QS have a range of employers who take part in those world rankings. So we've got major employers, we've got NGOs, we've got local governments, we've got charities, setting our students real world projects based on the UN Sustainable Development Goals. And the key thing is that the students work on those projects in multinational teams with students from Sao Paulo, from Stellenbosch, from CUHK. The University of Auckland in New Zealand has just signed up to join us. The University of Social Sciences in Rome has just signed up to join us. The American University in Cairo will be joining us. So we want our students to learn with students from around the world so that they appreciate different cultures, different ways of learning. They appreciate what the UN Sustainable Development Goals look like. If you're sitting in Latin America, they look slightly different than if you're sitting in the UK. And if you're sitting in South Africa, they look slightly different again. And of course, energy is a key component of those UN SDGs. So all the time, we're trying to open up opportunities for our students and staff to learn and to research internationally. We also want to work with our global alumni. We've got an ever-growing alumni base across the world. So we want to work with that base, and we want to work with that base to support our current and future students. So this is not just about those alumni giving us money, but it's about those alumni offering advice to our students, offering internships and placements to our students. It's about those alumni being able to work with potential students, being able to help us recruit students, being able to help us spread the word in their home countries about Exeter. So our global alumni and advancement work is very important. If we get all of that right, it should lead into a positive in terms of our global reputation. So if we get our global partnerships, our student recruitment, our experiences, our alumni and advancement work right, it should have a positive impact on our global reputation. So at the moment, we're 137th in the Times Higher World University Rankings. We want to push that much closer to being a top 100 institution. But we're 42nd in the world in the Times Higher Impact Rankings. And we're 48th in the world in the QS Sustainability Rankings. And those last two rankings are important to us because they are measuring the impact of our work, particularly the impact of our work in the area of sustainability. And obviously the work that's done by the Solar Energy Group and the work that's done by ESI more generally is really important elements of that broader work around sustainability. So I'll just talk a little bit more about our global partnerships. Why are these important to us? They're important to us for several reasons that I've set out here. They allow the delivery of world-leading collaborative research and education because, let's face it, the key challenges and problems the world faces are not going to be tackled by a single university working on its own. We've got to bring together the very brightest researchers, the very best academics from across the globe to tackle these global challenges. We're not going to tackle them by working on our own. So we need to work collaboratively with universities across the globe to tackle these global challenges. And we need to work with them to provide education for our students because our students are going out into a global world. They need to understand that global world. They need to understand other cultures. They need to be in diverse settings, in diverse communities. They need to be able to operate in a multicultural environment. So it's really important, both in terms of education and research, that we build these global partnerships. They also provide opportunities for our academics to win research funding. And obviously we have a prime example, the grant that Dr. Anurag has got, the UK Saudi Challenge Fund British Council grant with KFUPM is a crucial example of the way that you can work with others internationally to win research funding to support your work. I've talked about the way that this work can address these global grand challenges. And of course, energy, particularly renewable energy, is one of these grand challenges. I travel a lot in this job, and almost everywhere I go in the world, people are asking, what do we do on energy? How can you help us on renewable energy? And I'll say a bit more about that later. But time and time and time again, I get approached to say, can you help us with work on renewable energy? Unfortunately, because of the work of this team, I'm able to say, yes, we can help you on this, and we would like a partnership with you on this. Looked at from an academic point of view, collaboration increases the impact of research and publications. You only have to look at the citation rate to see this, where we're now in what's called the fourth age of research, where universities are researching together. The first age was individual. The second age was groups coming together. The third age was academics beginning to work together. The fourth age is academics crucially working together. And you see this all the time. So the citation rates for co-published work with international authors are way higher than if you publish on your own. And at Exeter now, some 65 to 70% of all of our research outputs are co-authored with international partners. Again, you've only got to look at the solar energy group to see that. And they have much higher citations if you publish internationally. This is crucial for postgraduate students. We try and use our collaborative partnerships to offer opportunities for postgraduate students for joint study so that they can go overseas, they can build their networks, but also they can have joint supervision. Why be supervised by somebody from one country when you can benefit from being supervised by people from more than one country? You want PhDs to be supervised by the very best academics, wherever they are. So we have schemes where we're able to allow our students to be supervised jointly. And we even have joint PhDs where students can study and receive PhDs from two institutions. So the networks expand for staff and students, which is absolutely crucial. And as I've been saying all the way through, these collaborative partnerships offer students a chance to learn with, but crucially from, others across the globe. We want to open our students' minds to the views of others. We want to inform our students about societies and cultures across the globe. And how better to do that than to be in a classroom with students from elsewhere? It's absolutely crucial that our students learn from others. They learn from other countries, they learn from other students. We want this to happen, and we want to give them a chance for this. So just a bit more about our partnerships before I finish. The collaborations that we're building, we try to make around the themes of Exeter's new strategy. That 2030 strategy for the university says that we will use the power of our education and research to create a sustainable, healthy, and socially just future. It can be summarized in those three words. We want work that helps us become greener, become healthier, and become fairer. And again, the work that the Solar Energy Group does, it is crucial to that, particularly in terms of sustainability, but also in terms of a socially just future. So we have very strong partnerships, as you heard before, at a university level with the University of Queensland. I talked before about joint PhDs. We have 45 joint PhDs with the University of Queensland, where students spend at least a year of their time in Australia, and the Australian students spend a year of their time here, and they graduate with degrees from both institutions. We have a research partnership with the Chinese University of Hong Kong that's on environmental sustainability and resilience. We have partnerships with Tsinghua University in Beijing, and again, we have joint PhDs with Tsinghua in the area of environmental studies. We work with the University of British Columbia, and we have a big partnership with the University of British Columbia's Okanagan campus and our Penryn campus, which is really important for us, where this conference is being hosted from. We are the only UK member of Venice International a university that has 20 universities coming together across the world to provide teaching. So our students will go to Venice to be taught by academics from those 20 institutions, and our academics will teach students from the other 19 institutions. And we have PhD summer schools as a result of VIU, and we can go to Venice across the summer and run summer schools for our PhD students. We're developing new institutional partnerships in Saudi Arabia, so it's particularly pleasing to see this conference being provided in collaboration with KFUPM. I've been to Saudi Arabia 3 times this year. I was last there 2 weeks ago on a trip where I met about 30 institutions from across Saudi Arabia. We're building very strong institutional partnerships there. We're building strong institutional partnerships in Sharjah, one of the United Arab Emirates. We had a delegation visit Sharjah last week, and we've been asked to help them found a new university building on marine science in particular. We're also developing institutional partnerships in India. These all operate at an institutional level, but we have hundreds of specialized partnerships, including the renewable energy work and the solar energy work. We have partnerships around solar energy with Saudi Arabia, as you know, with KFUPM, but also with IAU in Dammam. We have partnerships in India that Tapas has helped us to form with IIT Madras, with IIT Delhi. We have the marine renewable partnerships and our work on energy grids in China, very strong partnerships with a number of Chinese universities. And this conference, above all, is a fantastic example of the way that by collaborating, you can bring scholars together to have those conversations, to develop those intellectual agendas, to develop those academic agendas that you could never do on your own. So it's a real pleasure for me to be here. It's a pleasure for me to introduce our global activity. So on behalf of the University of Exeter, I just want to wish you all the very best for the next 2 days, and I hope you have an absolutely fantastic conference. So thank you hugely.
Thank you, Professor Mark, for your time and the wonderful summarize of our global relationship. It's really appreciate. Thank you so much. We will moving on to our first plenary speaker of the conference. Let me introduce Professor Muhammad Ashraf Gondal. He is a distinguished professor, Department of Physics, and coordinator of the Laser Research Group, King Fahd University of Petroleum and Minerals, Saudi Arabia. So with this, I would like to invite and welcome Professor Gondal. Over to you.
Thank you very much, Dr. Anurag, and it's my great pleasure, and I am really very much impressed by the work what your university is doing, and I'm very proud of that I am also a partner now in this work. Can you kindly see me all my slides now fully?
Yes, everything is okay.
Yeah, great. So my talk is basically about green synthesis of green method, which I will introduce you, and how we produce or synthesize such materials using a unique technique, what we call pulse laser ablation in liquids. And then I will go through quickly what activities we are doing when we make these functional materials. So we use for energy harvesting, for third generation solar cells. We use them for supercapacitors. We use them for photodetectors, and also we use them for photocatalysis. We were talking today, and all these efforts lead us to renewable energy harvesting and energy storage activities. I don't want to waste much time on this, so I go straight away to to my talk, and the outline of my talk is that I will just give some motivation about why all we are after renewable energy. And then I will just briefly introduce what our group is doing. Basically, we are doing many things what you are doing in your university, but our group is not as large group as your group, as your university is doing. But still we are struggling, and we have also multinational team of many students. Although a little bit we have now handicap due to this corona, it has affected a lot of our international students due to this corona pandemic. And we are still struggling, and we are doing so. I will go to introduce dye-sensitized solar cell during this time, and how we fabricate perovskite solar cells. Then I will briefly go through thermoelectric films for power generation. And of course, our main also focus is, as you visited us, that we are doing a lot of work on supercapacitors for energy harvesting and energy storage. We are working on materials which can generate electricity, and same time it can store the electricity. So that's our main focus here. So we are doing dual function materials, which can work as a supercapacitor as a solar cell. And then briefly, I will show some results which we did on bifacial perovskite photodetectors, and I will conclude my talk. We all know that the major world problem at this time is that we have fossil fuels which are depleting, and they are also polluting our environment. And we have a lot of problem, climate change and floods. Like the worst example is now that Pakistan and India and Bangladesh, they suffered this year a lot of rain, and rain happened in those areas where we don't have monsoon normal, but due to this climate change, we have rain and we have a lot of flooding and a lot of problems. So energy is the main, clean energy and renewable energy is the main parameter which can really bring the prosperity to the world and the sustainability. So if we have a clean and enough energy, we can have a clean water. So we can overcome the poverty, so we can have a clean environment. And of course, when we have a clean water and clean energy, enough energy which is cost effective, we can food, and we can overcome a lot of diseases. So main parameter in this is that for sustainability is the clean energy on which most of the world is focused. And behind this all clean energy is the basically advanced functional material. When we talk about functional material, we desire such material should have very unique electronic, magnetic, and optical properties, so that we can use efficiently these materials to generate the electricity, to store the energy, and also we can use in communication, and many are even sensors. So the main backbone of this, all these activities, that how much better advanced functional material we can have, so that we can have a tunable band gap. They should have high optical activity, and they can have high surface area, and they could be transparent. So all these properties can be tailored if we can really develop some better synthesizing materials and the methods. So that's what our group is doing. We have a unique, method which we have developed here in our lab, where we use lasers basically, and I will introduce you. And meanwhile, when I reach to there, and one of the material which our focus of our group is the perovskite materials. And we all know that perovskite material, they are the best absorber, and they have excellent, they are good and excellent transport carriers. They have lower excitant binding energy, lower affinity, and the important thing is that the main feature of them is that they can be very easily synthesized, and one doesn't require a big lab or very complicated, chemical process to synthesize such perovskite material. And such materials have a lot of application in daily life now, in solar cell, photodetectors, LEDs, photoluminescence or lights. So now I just like to brief you very quickly the activities which my group is doing at King Fahd University of Petroleum. So most of these application which is done at conducted at my group, they are related to renewable energy initiatives, and it could be energy harvesting, that we are developing solar cells and thermoelectric materials where we can use heat to generate electricity. And we are also working same time that we can use these material for hybrid energy storage devices, for example, supercapacitors and batteries. And the same time, we are working on, as Dr. Tahir Asif mentioned, we are working equally on solar cells safeguarding. We have developed, done some projects in the past with MIT, where we have developed hydrophobic, hydrophilic surfaces. And for that work we are doing. But recently we are working on some special system which we call electrical dust shielding system, that which is unmanned system, and it can safeguard, or it can not let any dust accumulation on any PV module. So we have just completed one PhD thesis, and we have recently one published paper in ACS Applied Energy Materials on that technique. And we found that this technique is really a very useful technique, and it can doesn't need any water, or it doesn't need any manpower. It can self alone can protect and safeguard against any dust accumulation, which is the major problem in our area here, because we have a lot of desert where we have some installation of PV energy. So we need such kind of technology. We are working that. Also, we are working on photocatalysis and photoelectrochemical systems, especially for green hydrogen production by water splitting. And we are not only using traditional materials, but we are also developing materials which are inorganic perovskite material and ferromagnetic nanocomposite material. We also worked working still on CO2 conversion into high value hydrocarbons using photocatalysis process. And these are, and in addition to that, for energy detection, and we are also developing some photo detector and photonic devices in our group. Due to time limitation, maybe I will not touch all of these applications, but I will try to give you very small, some flavor of all these activities, what we are doing in our group. So the important thing why everybody is motivated for renewable energy is that we know that at present the need of the energy is increasing very on rapid scale, because we have industrial growth, we have a tremendous population growth in the world, and we need a lot of energy, and we need energy which is clean energy, because we have gone through catastrophes due to environmental changes, climate warming and all these issues. So I have just a very small statistics that by year 20 in China at this time is producing around 7%, and by 2050 they want to take the renewable energy share to 67 to 70%, and India also is going to 70% in that time. Also, one of the Nobel laureate has quotation that energy will be the biggest problem for humanity in next 50 years. And we all know that sun's core has these fusion process going on, and it produces neutrons and a lot of solar energy. And according to, rough estimate that the energy which is produced by sunlight in 1 hour, it's more than enough for the humans in the entire year. But there are, of course, a lot of challenges, and challenges are the materials. And we know that solar radiation, they consist mostly in, the visible region is 43% and 52% is in the near infrared. So we have to develop material which absorb in the visible light, which absorb the major portion of the solar light, which is around 43%. So this is a great challenge. Most of the material they absorb in the UV region. So we have to engineer the band gap of most of the material and develop the technology that is cost-effective technology. This slide, I just want to show you that at present, we have thermal power plants which produce 80% and renewable energy share is just 20%, which we like to bring it to 42% in the coming year by 2035. And in this, the share could be of PV and wind and also CSP, concentrated solar power, which is shown on the right side. But main focus, most of the people know they are working on PV and wind. They are the technologies which are quite, feasible and doable. Now I will go to some more technical, the work which we are doing. We are working on third generation solar cell, which are dye-sensitized solar cell and perovskite solar cell. In this, we know why the motivation is basically stems by Professor Gratzel group that they have developed dye-sensitized solar cell, which are coated on the walls of Swiss Technical Convention Center. So it's a stand system which can generate the electricity and give the electricity to this convention center. Similarly, Newcastle, the Parliament of Australia, they have also developed a system based on dye-sensitized solar cell. And these dye-sensitized solar cell can be used even for our military and other, when they go in the remote area for their mobile or for communication system, one can use such dye-sensitized solar cells. When we like to select that what is the best solar cell, this is called a golden triangle, maybe because I like to just show, maybe we have some students and you are maybe familiar already. So there are three main parameters which we consider when we talk about these three generation of solar cells. So first generation of solar cell is silicon solar cell, the second is thin film solar cell, and the third generation is dye-sensitized and perovskite solar cell. And this golden triangle, the three parameters which we take into consideration is the power generation cost, then power generation efficiency, and how these cells are stable in harsh environment like we have in the kingdom, in the Saudi Arabia. So first of all, we have a silicon solar cell, which are mainly used at this in PV modules all over the world. The drawback in these silicon solar cell is that we need a very high quality silicon, and that costs a lot of energy, and it's a very costly material to make that. So one require really some material or some alternative that can generate electricity, but they are cheap. Thin film solar cell, on the other hand, we don't need much material, so they are, cost is low. Dye-sensitized, the cost is low, and perovskite solar cell as well, also cost is low because we don't need a lot of material, we need just the films. Power generation efficiency, silicon solar cell, they are high, 18 to 20%, depending on the climate, the environmental temperature. And thin film solar cell, they have some medium efficiency. Dye-sensitized solar cell, they are not reached more than 13%. Perovskite solar cell efficiency is quite high, but they have a drawback still that they are not highly stable under, harsh environment. So these are three criteria when we discuss and we select which, generation of the solar cell we need. So most of the focus at this time is on perovskite solar cell and dye-sensitized solar cell. The physics behind these dye-sensitized solar cell and perovskite solar cell is almost similar. We use dye as a photosensitizer. When we shine the light on dye, we tunnel electron from the HOMO level to LUMO level, and then we have a substrate which is coated with the TiO2, and then this TiO2 coating is absorbed in a dye overnight, and we have an electrolyte, and we have a counter electrode, which is the platinum electrode. Our focus in my group is that we like to work on some materials which are mostly nanocomposite, and we also used not expensive counter electrode, which is platinum. We have replaced with carbon. On the perovskite solar cell side, a photosensitizer is a perovskite, and then we have electron transport layer, which is the electron transport material, and then we have whole transport layer, and we get this such kind of solar cell functional. The excitation mechanism is shown here, that we shine the light on the die, and then we tunnel an electron from S level to S plus level, and then this electron is captured by this TiO2, and then there is a load here, and then we have a counter electrode, which is a platinum electrode, and this dye we regenerate by taking one electron from the electrolyte, and then electrolyte is replenished by another electron, which comes back through the platinum. So this is similarly in perovskite solar cell, we have a valence band and we have a conduction band. When we shine the light, we turn an electron from methyl ammonium lead iodide to conduction band, and then we have a TiO2, and we have electron transport material, and we have hole transport material, and on the counter electrode is here a gold electrode. Our focus is that we like to modify the photoanode by nanocomposite and multi-wall carbon nanotubes or quantum dots. And on the dye side, we co-sensitize different dyes, we mix together so that we can better efficiency. And we have replaced the expensive counter electrode by cost-effective material like carbon. That's the focus of our group in our lab. So this is a simple method how we fabricate a dye-sensitized solar cell. We have FTO substrate, we mask, tape on it, and then we have a TiO2 paste, use a doctor blade, and typical the people, they use this to make a dye-sensitized solar cell. Then we calcine this TiO2 over certain temperature for a certain time, and then we put 24-hour in the dye solution, this film what we have built, and then we assemble the dye-sensitized solar cell, and then we inject the electrolyte, and solar cell is ready for testing. The main focus of my talk is that what our group is doing, that we have pioneered in this technique, and we started in 2007, that we synthesize material using pulse laser ablation technique, PLAL. We all know that there are two methods to synthesize nanomaterial. One is we call top-down approach, and the other is the bottom-up approach. Bottom-up approach is all wet chemical method that you start from atom and the molecules, and you build the materials, nanomaterial. While ball milling and pulse laser ablation fall in the top-down approach. And in next few slides, I will show you the physics behind it, that there are two kinds of method which one can use, that we can use this pulse laser deposition for making thin film. But on the left-hand side, we use the pulse laser ablation in liquids to generate the setup is very simple, but it needs the experience and that one can really use such material. The unique feature of such material which we synthesize with this advanced technique is that we have no contact with the material. We just use the photon which are contacting with the material. So you don't pollute or we don't contaminate our sample. And the other thing, we don't need any precursors. And through this method, we can make any nanomaterial of any kind, of any phase, what we like. Only we should have to control the laser parameters and the timing of the laser irradiation in this. The physics behind this pulse laser ablation and liquid is shown here, that we can use either a solid target or we can use the powder. which is a bulk material, which is of the size of, let's say, millimeter size. And then we shine the laser, and we know laser is a very unique source of radiation. We focus the laser beam. We generate a plasma inside the liquid. And this plasma, which is created inside the water, it has almost temperature of 4,000 to 5,000 degree Kelvin. So we develop some cavitation bubble, and this cavitation bubble then explodes, and it generates a high, very strong ultrasonic shock wave. And this acoustic shock wave, which is generated by this, cavitation bubble of the plasma, it compresses the material and make the nanomaterial very, promptly. Within 15 minutes, 20 minutes, we can make nanomaterial of any size, whether we need a nanocomposite or we need a pure nanomaterials without any, the material which got doping or other stuff. So we can really control the parameter of the laser, and we can get a material of our requirement. We can have many outcomes of using pulse laser synthesis. So just by controlling the laser power and the pulse width of the laser and the wavelength of the laser, we can, if we have some atoms, we can make chemical bonds between them. And if we have some bonds, we can break the bond, and we can, for example, by just when we change the power, we can change the pressure and the temperature inside the plasma. So we can break the bond, or we can form the bond. And we can also do the phase transformation of the material. So we can resize the material, of any size, what we need, just by controlling the laser parameters here. This is a very simple setup. We are using here a neodymium YAG laser, which has a pulse width of 6 nanoseconds. And we can use the fundamental wavelength of the YAG laser, which is 1064 nanometer, or we can double the frequency and get 532, or triple the frequency, 355 nanometer, or fourth harmonic, we can get 266 nanometer. The ablation time, normally we use 15 minutes, and sometimes we use some oxidizing medium. For example, if I put just pure zinc and I put some oxidizing material and shine the laser, I can make pure zinc oxide nanoparticles using this technique. This is one of the example you can see here. On the left-hand side, we have a cadmium selenide before, and the right side, we have a quantum dots of cadmium selenide, which has now clearly different color. Black has converted to yellow. And this is advantage is cost effective, no need for high vacuum and clean chambers or expensive setups. We can generate high purity nanomaterials, and we can control the size and the composition of nanoparticle by laser, the wavelength of the laser, energy of the laser, pulse duration of the laser, and to some extent the medium also. So these are the main, the advantages of this. And the best thing is that it is a green method. We do not generate any chemical waste, and it is very rapid technique that in few minutes, while in normal other chemical wet methods, you can use days sometime to get nanomaterial. So that's the unique feature of this technique. One of the example I just show you that we have, make a nanocomposite titanium ZNO CDS, and we need this material for, photocatalysis, for example, that we like to engineer the band gap of this material. So we know that TiO2 has 3.2 electron volt, and ZNO has 3.37, and CDS has 2.4. So we can engineer the band gap of such material just by using pulse laser ablation and liquids. So we have tried many nanocomposites using this technique, and we have applied in different applications. This is just one example of synthesis of CD cadmium selenide quantum dots using a pulse laser ablation method for co-sensitization of dye-sensitized solar cell. And you can see here, this is a transmission electron micrographs of cadmium selenide quantum dots. One can clearly see that the most of the size of particle size is less than 10 nanometer, which is basically, we define that it is a quantum dot. And when we make such material, this is just a UV spectra, the absorption spectra of different material, what we make this nanocomposite. You can see that just by using the yellow, you can see we have enhanced a lot of absorption in the visible region, starting from 350 to 700 nanometer, just using this technique. And now we can use this material in the visible light. Also, these material, when we make such nanocomposite, we can control the electron hole recombination when we excite, for example, from valence band to the conduction band. There's always probability that the electron can jump back and emit light, and we can monitor this by photoluminescence, that is there any electron hole recombination taking place. So you can see pure TiO2, you have here this a lot, very high for emission, while when we go to TiO2 CDSC, you can have reduced almost from 26, 27 to almost to 7. So we can really control by electron hole recombination by just the making this nanocomposite material in this. This is a table which different kinds of dye-sensitized solar cell which we have fabricated in our lab, and we have over the years, and we have, you can see here, we have ZNO, TiO2, CDS, silicon carbide. We achieved so far 11 almost efficiency, and we are just working on the manuscript. And most of these material which we have used here, they are CDS, and some are with the dye sensitization, co-sensitization was Z907 SQ2 dyes, and we do different kinds of work in our lab, and still we are continuing to improve the efficiency and search for new materials which are efficient. Just quickly, I go to perovskite solar cell. Our main focus in perovskite solar cell was a single crystal solar cell, and we know that single crystal solar cell, they are more efficient than polycrystalline solar cell because there are no edges, and the conductivity of the mobility of charge carriers is much faster. So so far we succeeded around a single crystal of size of 4 millimeter. This was work we did with the joint with the KAUST, and we also still working on such kind of single crystal perovskite material. And this is just how we synthesize a perovskite solar cell, FTO, TiO2 blocking layer, and then we have zirconium oxide and porous carbon. We used a carbon electrode also instead of gold, and in order to also remove the spiro, which is whole transport material, which is very expensive material. And this is just the IV characteristics and the efficiency of such solar cell, which we recently published in this International Journal of Energy Research. Now I go to the second application, which we are doing, fabrication of thermoelectric materials. Again, we use here pulse laser deposition, and we know that thermoelectric material are a big, good material. We have a lot of heat in Saudi Arabia. In summer, we have almost 50-degree temperature. So if we can really develop a very efficient material, we can generate the electricity. And opposite or reverse, we can use this as a Peltier effect. If you apply heat, you can generate electricity. If you apply a little voltage, you can lower the temperature. So you can both, you can do generation of electricity based on Seebeck effect, and the refrigeration is based on the Peltier effect. which is opposite to thermoelectric power generation. And we have this chamber, and we have is excimer laser, which we shine. We have is the substrate on one side, and we have a target material. We work with bismuth telluride. We started, and then we should use bismuth telluride, selenide, and other materials, which we are still continuing. We don't have at present in our lab to measure the direct Seebeck coefficient, but we developed an indirect method using Raman spectroscopy. And we know that the figure of merit of any thermoelectric material efficiency is given by Seebeck coefficient. Electrical conductivity is directly proportional to electrical conductivity and the temperature of the film and the thermal conductivity. So this thermal conductivity part we have measured through this Raman spectroscopy, and these are, DFT, on the other side, bismuth telluride, and this is the Raman spectra of this. So these vibrational, phonon vibrational mode, through that we can estimate the thermal conductivity and test our material. Is it a good material or not a good or efficient material? So we have quite a number of some papers on this work, and we still continuing to do this work further. We already completed one PhD thesis and one master thesis on this work, and we like to continue further this work. We have a team who are kind of working with us on density function theory to do the modeling, and we are experimentalists, and so we have working on that. Now I just moved to energy storage and photonic detection devices. Under energy storage system, we are mainly working on supercapacitors, and we all know that renewable energy is not 24-hour available. When wind is blowing, we have the wind energy, or when the sun is shining, we have the solar energy. So we need for intermittent, so we need to store the energy. So we started with a supercapacitor, and there are different kinds of supercapacitor. We all know that we have electrical double layer supercapacitor, and we have the pseudo capacitor, where we have basically, the metal oxides. And there are three kinds of storage devices at present in the market. One is the battery energy storage, where you use a Faradic redox reaction and the electrode electrolyte interface. While in a supercapacitor, mostly we use just a double layer of the charge separation between the electrode and the electrolyte, and we can store the energy and get a very high capacitance through that. We have also worked on a supercapillary, that we have combined the battery effect as well as the supercapacitor effect when we use a lithium-ion rich gel electrolyte. And we were quite successful in this, and we like to continue because this has a potential application for any commercial or the field application if we want to go into that area. Supercapacitor, all we know is they're really a very big emerging device because it can have very high capacity of the order of people have reached even commercially now, more than 10,000 farad or even 100,000 farad for this, and their power density is 100 to 1,000 times more than the normal batteries, although their energy density is less than the battery. And you can charge and discharge this in very fast, so it has a lot of application, especially in automobile industry, where you have to stop the automobile very fast. So the braking system, in electric car, mostly the people will use and are using this technology through this. There are different kinds, as I mentioned earlier, supercapacitor, we have electrical double layer capacitor, EDLC, where you don't have any Faradic reaction, but you do just the charge, static charge separation just by applying the external voltage, what we like to store, and there is a double layer formed between electrolyte and the electrode. And you can have pseudo capacitance where you use metal oxide as an electrode, and you can have a redox reaction, and then you can diffuse these these charge carrier inside. You can have hybrid supercapacitor where you can use EDs, both electrical double layer capacitor on one side, and other side the electrode is a metal oxide pseudo capacitance. So we are working on three kinds of these supercapacitor in our group. For the characterization, we use cyclic voltammetry, and we can use also charge discharge, galvanostate, and we can measure these the capacity, specific capacitance, which is capacitor per unit area or capacitance per unit mass, and we can then analyze and characterize, and we can measure also the equivalent series resistance using Nyquist plots. All this are standard techniques which people use, so we are also using the same. We have also worked on some materials which are self-charging supercapacitor, and then they generate electricity and then they store electricity. So one of the example is polyaniline material, which is we used as an electrode, and we are quite successful, and we proved that this can work, that it can do a dual function. It can store, it can generate the electricity as well as it can store the charge. So it can work as a solar cell as well as it can work as a supercapacitor. The other our focus is on perovskite-based supercapacitor, where we like to develop some perovskite material which has long cycle life, and we can use a polymer gel electrolyte, so we can have all solid state device which can really work, or has a potential to be as a commercial device in the future. So we are working in that direction also, where we have used a polymer gel solid state electrolyte, and we are using other perovskite. Mostly we are now working on inorganic perovskite material, so they are quite stable, and they have long cycle life. We also worked on supercapillary using lithium-ion rich gel electrolyte for unified energy harvesting and energy storage, because we know that any perovskite material is a photosensitizer, so it can generate electron, and we can store work as also as a supercapacitor. And then we enrich our electrolyte with the lithium ions, and we can have a supercapillary. Inorganic, we have used copper antimony iodide perovskite photoresponsive capacitor, and we have used PV polymer gel electrolytes for hybrid energy investing and storage applications. This is, the characteristics of some of our, devices. We have, cyclic voltammetry on the left side. We have a Nyquist plot in the figure B, and we have charge and discharge, also galvanostat to measure the capacitance, and we have also worked on how this our capacitor is supercapacitor is recyclable. So now I go to some example of perovskite based material. This is just one of them, you can see, and here we have reached almost these recyclability around 10,000. And we are still working on this to improve more and more. And in the capacitance, we reach almost 150 to 200 farad. We have some publication on this work and even some patents we have submitted to USPTO. Now, just quickly, I go to sandwiched, perovskite-based photodetectors. So we have worked on these using perovskite material, lateral or vertical, configuration. And we found that our bifacial, that our photodetector can get light from both sides. So we have tried this, and we are quite successful. Some of the characteristics are shown here, that it's rise time, how fast this is, and we have compared our work with different previous works. The quantum efficiency we have also improved here, and we still continuing this. This was actually a master thesis, one of our students who worked on this work. We are still continuing this to go. Due to time limit, I think I should conclude my talk. So we have applied different, I have briefed you on pulse laser ablation liquid to synthesize functional material and nanocomposite materials for different application. One can ask question that how this method is good, because you can not make tons of this material, but our application don't require a lot of material, so we don't need 100 grams or this. So we have enough material which we can make in 20 minutes. We use co-sensitization techniques to improve the efficiency of dye-sensitized solar cell. We have replaced the costly electrodes using in platinum with a porous carbon, which mostly conventional dye-sensitized solar cell people use. And also we use multi-wall carbon nanotube to get better efficiency. We used inverse temperature crystallization method to grow these single crystal in our lab, and we were successful to reach to 4 to 5 millimeter size single crystal in our lab. Bismuth telluride based thermal active power generation we fabricated using pulse laser deposition technique. We are worked on integrated energy harvesting and energy storage devices 2-in-1 using solid gel electrolyte. And we also brief you bifacial perovskite photodetectors using different architectural modifications and methyl ammonium iodide solution passivation technique. Due to time, I could not brief you on the hydrogen, green hydrogen, what we are doing with electrochemical analysis and this electrical dust shielding system. But we are working on that for safeguarding our PV module. Some of the work which we have published on all these techniques, as you can see on my Google Scholar. So we have almost 395 journal publications, some conferences, and so far we produced 25 PhD theses from my group, and 26 patent has been issued by USPTO, and 20 patents are still lying. This is not work by me alone, so we have a big team, multinational team and diversified. So we have the 3 professors here up on the top. 2 of them are theoretician who was expert in density function theory. We have done this Mr. Talal, who is from Yemen, Mr. Dastgir the second from India, Mr. Yunus from Pakistan, and then we have Abdul Jalili and Luqman and all this from Nigeria. Then we have a student from Singapore. So my team is almost, is not 59 countries, but still it can give a flavor of different countries. So I should acknowledge my home institute, King Fahd University of Petroleum, who's really supporting me a lot, my own department, physics department, and we should also talk here, which is King Abdullah City for Atomic and Renewable Energy. And we have a core center in renewable energy, and we have a core center in hydrogen, and now they call it energy storage, IRC hydrogen and ES. Also, we have collaboration with COAST, and we have also funding from CAXT, which is NSF in US. So we have different, funding agencies who have supported my work. So I should acknowledge them and thanks them. And I think thank you very much for your patience and listening me. So welcome for any question if you have about my work.
Thank you, Professor Gondal, for your interesting talk and variety of topics that you have covered during your talk. And we will be here stop for a 10 minutes comfort break, as we are little running out of time. So if anyone has any questions, please put on the chat box in Zoom. So we will collect the questions, and we have a panel discussion sessions after the comfort break. So please join us, and we will stop here for 10 minutes comfort break. See you there.
Can you hear me?
Yes, Professor. Yeah.
Okay. So tell me when you want to start.
Yeah, yeah, we can start now as we are also a little learning late. So welcome back, everyone. Once again, we have our next plenary speaker, and thank you. We glad to welcome Professor Mohammed Naziruddin from EPFL Switzerland. And we all know those who are working on perovskite or solar cells related field. He doesn't need any extra introduction. I think so. So welcome, Professor Naziruddin on board, and over to you.
Thank you. Thank you, Anurag, for your kind introduction. And I would like to thank all the organizers for inviting me to share our results. Let me share the presentation. Can you see my presentation?
Yes, all okay. Yeah.
Perfect. Thank you. Good morning. And again, thank you for attending this conference, a very interesting conference. There are a lot of very high profile speakers. So I would like to share some of our recent results. So the title of my talk is Stable Perovskite Solar Cells by Compositional and Interface Engineering. What you will see in my presentation is how you can make the perovskite solar cells more stable, either by compositional engineering and interface engineering. So this is the conference which we are discussing, and my name is Mohammed Khaja Naziruddin. I'm working at EPFL Sion. This is on the below, you have my email address. If you have any queries regarding my presentation, you can send me your queries. So this is my main affiliation. I have a secondary affiliation with the World Class University, Korea University, and King Abdulaziz University. This is our campus, very nice, beautiful campus located on the shore of Lake Leman. It's also called Geneva Lake. I come back to the topic. Perovskite solar cells is very high efficient and comparable to silicon solar cells. You can see from my presentation here. Perovskite solar cells efficiency is 25.7, which is certified. And similarly, last week, Lungyi has reported 26.8% of silicon solar cells. But you can see, you can contrast the performance is almost same, but the technological intensity in silicon solar cells is enormous. And also energy input is very high, 1,400 degrees temperature in order to melt this metallic silica. Besides that, you have a lot of carbon dioxide production because you're converting silicon dioxide into metallic silica. On the contrary, perovskite solar cells are a solution process material, and the required temperature to form this type of perovskite solar cells to reach 25% efficiency is 120 degrees temperature. So you have a huge difference in the energy input of these two technologies. Now I come to the material. What is the perovskite material? So perovskite material, a general formula of ABX3, and which is given here. The structure is a three-dimensional structure. When we have these three components together, they spontaneously self-assemble into three-dimensional material. So that's the beauty of this material. So what are these three materials? You have A is the organic or inorganic cation. That's a inorganic, particularly cesium. That's the largest cation in the periodic table. And then you have an organic, which can be methylammonium or formidinium. And the B cation is a lead, which we are working and everybody is working. And tin is a possible replacement, but it has it's a stability issues. And the hal X is a halides starting from the iodide, chloride, or bromide. But these materials has a very interesting properties, which I highlighted on the below. Very strong light absorption. It absorbs all the visible light between 420 to 800 nanometers, and the tunable band gap. You will see in my presentation how you can tune the absorption properties of this material, either by changing the halide or by changing the cation or by changing the central metal ion. And another interesting property of this material is a small excitation dissociation energy, which is typically 30 millielectron volts. What happens is, if we have this such as a small excitation dissociation energy, the moment we shine the light, the carriers, positive and negative charges, are immediately extracted towards their contacts, and the recombination from the same germinate pair is happening. So that's the reason why the efficiency of these materials are extremely high. As I mentioned before, the absorption spectral property is shown here on the left side of the view ground. And on the right side, I'm highlighting another interesting property of these materials, a sharp onset of the perovskite materials similar to gallium arsenide, that's a blue line. And if you compare contrast with a single crystalline silicon, which has a sluggish onset. So this as a sharp onset indicates that a well-ordered microstructure and low trap densities in these materials. And the advantage of this sharp onset is you can use this type of material for a tandem configuration of either silicon or CIGS perovskites. Now I come to the tuning of the absorption properties. So this is on the top, what we are seeing is methyl ammonium. I have taken a classical example, methyl ammonium lead iodide perovskite, which has the absorption onset around 850 nanometers. It goes up to the whole visible region up to 400 nanometers. Wherever you excite, we get a emission maximum 790, 800 nanometers. And this emission maxima is you can tune by changing the halides, for example. And here we take on the bottom, we have a halide tuning. In the one case, we have a completely I3, that's iodide perovskite, like a methyl ammonium iodide perovskite. On the extremely left side, you see bromide perovskite, lithium methyl ammonium lead bromide perovskite. So in between, you can have a different ratios of iodine and iodide and bromide, and that gives you the various spectral responses in the whole visible region. It has its disadvantages, which I will not discuss here. Now I come back to the cation modifications. I have taken 3 examples here. One is a cesium, that's a pure inorganic perovskite, and the organic cation, that's a methyl ammonium, and the second organic cation, which has a formidinium. And if you look at the band energy, the band gap of these 3 materials, inorganic perovskite has a 1.73 band gap, and the methyl ammonium is a 1.57, the formidinium is a 1.48. Because the formidinium lead iodide perovskite has a low band gap, therefore it's a highly useful for solar cell applications. However, it has its own drawbacks, which we will discover during my presentation. Now, again, within the 2 organic cations, you can see further changes in the spectral properties. Here, this is a normalized emission of the pure methyl ammonium lead iodide perovskite, that's on the extreme, the left side. On the extreme right side, you see pure formidinium lead iodide perovskite emission maximum. In between, we have a different ratios of formidinium and methyl ammonium, the composition of the cations. If you can prepare these various mixed halides, mixed cation perovskites, but however, when we shine the light and exposing to a longer period of the intensity of the light, so they tend to segregate. So the take-home message from this my slide says it's better to have a 1 cation, 1 anion. It can be iodide. That's the most the absorbing absorber in the visible region compared to the mixed halides. Now I come to the deposition. So the perovskite composition and deposition methods are very important for getting high efficiencies. For the deposition methods, we have typically 2 methods. One is called one-step method, and second is a 2-step method. Third one is not very popular, but however, it's quite useful for a tandem silicon perovskite tandem solar cells. That's a vacuum sublimation. In one-step process, usually what we do, you have a next slide, you will see the details. In a one-step procedure, what we are using is you combine methyl ammonium iodide or organic cation iodide or inorganic cation iodide, lead iodide in a one solution, and you spin coat it. For the 2-step process, what you do is first you take your electrode and then you deposit lead iodide, first coating, then followed by you convert into perovskite by coating with the organic halides. So here is a typical example of a one-step method where you deposit methyl ammonium lead iodide in particular DMS or DMF a particular ratio, and this gives you nice perovskite film. Then we have to do the solvent quenching. This solvent quenching is very important, interesting property of this technique. So here what we are doing is we are crystallizing, enhancing the crystallization process by 2 methods. One, by heating the substrate. At the same time, we are precipitating by putting the anti-solvent. So this process gives you the controlled crystallization of the perovskite films. And this is the one of the criteria to get the high efficiency. Of course, there are people who are working replacing the DMF DMSO by NMP, and these are the formation energy, that's a energy of the solvents is shown here. So this is the one-step process. Now I come to the very quickly go to the device configuration. And what you see here is a two types of device configurations. One is called PIN and another one is NIP. In both these configurations, NIP is the highest efficiency, which I showed you, the 25.7% certified efficiency, and PIN is very close to 24% certified efficiency. What is the difference between the NIP and PIN is both have the same absorber material, except the hole transporting material and electron transport material are interchanged. In the NIP configuration, the electron transport material has to be transparent, and in the PIN configuration, the hole transport material has to be transparent. So therefore, here there is a lot of synthetic efforts will go into developing transparent hole transporting materials for PIN configuration and stable hole transporting material for the NIP configuration. And here is the energy scheme and the operating principles of the perovskite solar cells, where the perovskite absorbs the light and it creates a charges, positive and negative. Negative charges are injected into the conduction band of the ETL layer, and the positive charges are extracted into the hole transporting materials. And the negative charges will not go to the hole transporting material. It's because of the LUMO level of the whole HTM. And then the positive charges will not tunnel to the ETL layer. It's because of the deep HOMO level of the ETL layer. So this is a selective extraction of the charges between from positive and negative charges. On the bottom side, what you see is a cartoon of this device configuration. What we are having is a mesoporous TiO2 followed by tin oxide as a passivation layer, perovskite. And here is a phenyl ethyl ammonium iodide two-dimensional perovskite. You will see in the interface engineering this topic very clearly. And then we have a hole transporting material. So the real cell cross-sectional image is shown here. Our perovskite solar cells typically have 600 to 800 nanometers thick. So the same configuration, we have a conducting glass. First we deposit compact layer of TiO2, followed by mesoporous layer of TiO2. And then we have a tin oxide as a passivation layer, perovskite deposition. And then in this case, we have a excess of lead iodide that will be converted into two-dimensional perovskite by treating phenyl ethyl ammonium iodide. The whole transporting material with the dopants, and then we have a contact. And this gives us in the lab 24.3% efficiency, and these cells were sent to Newport, and there they obtained almost the same efficiency as in our lab. So this is a certified efficiency of 24.3% efficiency in our lab. That's based on the very small cell area. Now we will have a very high efficiencies, which we will report in coming weeks. So here is the mini module. So based on this configuration, we fabricated 6.5 centimeters by 7 centimeters, 45 square centimeters of the area, total area. So the efficiency is 22.9% of this mini module. So these are the types of mini modules which we are preparing, and we also have a flexible solar cells. So this mini module efficiencies has been entered into the charts of Martin Green's. This is the issue where you can see our data is entered. This is the highest efficiency of a perovskite modules so far in the world. So now I come to the topic. So we have all these things are excellent, but what is missing in perovskite solar cells is I highlighted here. Stability is missing. How do you increase the stability of the perovskite solar cells? So that's the reason why my talk is there. So we are trying to compositionally engineering the perovskite layer so that we can improve the stability significantly. And the second approach we are taking is we have several interfaces. The interfaces, for example, between the ETL and perovskite and HDL. So these interfaces can be improved. So we can interface engineering by modifying the interfaces to reduce the recombination at the interface and then to avoid the decomposition of the perovskite. This is one aspect. Now I have mentioned the ETL is a TiO2 and HDL is a spirometide. These materials are very interesting to get high efficiency. However, the stability of these materials is not guaranteed. So we have to develop a new charge transport materials. So you will see a couple of slides on charge transport materials. And finally, if time permits, I will do the cost analysis. What happens if we are successful making the stable perovskite solar cells? If we want to put 100 megawatts per the production line, what would be the cost of the perovskite solar cells? Now, I start with the compositional engineering of perovskite layer. So in the compositional engineering of perovskite layer, so let's say talk about why we should do the compositional engineering. Methyl ammonium lead iodide is an interesting material, but the stability of methyl ammonium iodide is not extremely high. It's because methyl ammonium cation is sublimable and it escapes from the perovskite lattice. On the contrary, Fa, that's a formidinium, because of increased nitrogen NH2 groups, there is an enhanced hydrogen bonding. It's more stable than methyl ammonium iodide. However, the formidinium methyl ammonium lead iodide has a drawback of converting its absorbing black phase into non-absorbing delta phase. So here the challenge is how can you stabilize absorbing alpha phase and preventing the conversion of alpha phase into delta phase. So there are in the literature, people are working with the different approaches. One, reducing the Fa cation and incorporating either cesium, a small percentage, and methyl ammonium, or adding additives into the composition to stabilize the alpha FAPY3. You'll see some of our efforts. And then we have a non-stoichiometric ratio. What do I mean by the non-stoichiometric ratio? When you are making the one-step solution, we are mixing 1:1 lead iodide and organic cation. This is a stoichiometric ratio. So here we want to increase the stability by bringing the non-stoichiometric ratio of lead iodide to organic cation, organic halide. So what it does when we have a non-stoichiometric ratio, look at the data. If we have a stoichiometric ratio between lead iodide and methyl ammonium iodide, we are taking here a classical example of methyl ammonium iodide. In 1:1 ratio, the efficiency is 16%. Now, if we increase 5% of lead iodide compared to organic cation, the efficiency increases from 16 to 17. If we increase further to 10%, then the efficiency goes to 18.42. Further, it is decreasing. Now, it's very nice data. And the optimized efficiency is 19.1. But the question is, what is this excess of lead iodide doing into your perovskite solar cells? This is optimized data, which has a 19.1% efficiency. This is typical IV characteristics, IPC data. So now, what is the excess of lead iodide doing? When we analyzed in depth, what we found was the excess of lead iodide is increasing the crystal size of the perovskite. Point number one. The second, it's decreasing the width of the, if you look at the XRD peak, the typical XRD peak of methyl ammonium lead iodide perovskite at 2 theta 14. So the width is decreasing significantly. So these are the two things you can observe. Then we have a so we now question is, so this is the effect of excess of lead iodide, but where is this excess of lead iodide is located? So can we identify? So what this is the absorption spectral properties, typically 0 to 20. There is not much difference because lead iodide absorbs in the most of the UV region. But if you look at if you interrogate at the interface, if you look at from 0 to 20% excess of lead iodide, so the carrier lifetime is decreasing. So it shows indirectly that the electron injection process is improved. So then we have taken the assistance of theoreticians to understand what is happening at the interface. So the excess of lead iodide is entering into the TiO2 interface, and this is modifying the interface. Therefore, the electron injection process is enhanced. So this is a real net take-home message that the excess of lead iodide is improving the efficiency because of enhanced electron injection into the ITL layer. And this similarly, at the same time, there is another group who has investigated excess of lead iodide. This is Professor Sok's group, who has a record efficiency of 25.7% efficiency. The high efficiency coming from this group. They also investigated excess of lead iodide. This is lead iodide emission peak, excited at 510 nanometers. And then if you look at if you see the imaging, this is excess of lead iodide by exciting at 510 nanometers. And this is the same film excited at 770 nanometers. The overlap of these two figures shows the presence of lead iodide around the crystals. So the conclusion here is that the excess of lead iodide, it's forming a shell around the crystals, our findings is it's mostly forming a interface modification between the ETL and the perovskite. And this independent studies also confirms that it's besides the ETL layer, it's also forming a shell around the perovskite grains. So that's the compositional engineering. And then finally, I come to the cation engineering. And here I have taken 3 examples just to show to students how the cations can modify. This is the methylammonium, formidinium, and guanidinium. So the purpose of having guanidinium is increase the number of hydrogen bonds in the perovskite unit cell so that you can increase the stability of these materials. So here is the tolerance factor, where the size of the cation dictates your formation of 3-dimensional perovskite or low-dimensional perovskites. So the empirical formula of tolerance factor, Goldsmith tolerance factor, is between 0.8 to 1. It forms a cubic perovskite if the cation sizes are in this region. And if the size is too large, then we don't have a 3-dimensional perovskite, it undergoes a low-dimensional perovskite. So here is a theoretical analysis of a unit cell where 100% guanidinium is not forming a 3-dimensional perovskite. However, combining some portion of the guanidinium and methylammonium iodide in a particular 3:1 ratio, 75% methylammonium and 25% guanidinium, it can happily accommodate in the unit cell and then can enhance the hydrogen bonding as we anticipated. That is an interaction between the NH2 hydrogen bonds with iodides, and that gives you significantly enhanced performance and stability over 1000 hours. So this is a remarkable finding that the cation modification enhances the stability of this composition. And second example I'm taking is based on a ionic liquid, and the ionic liquid has ions. Why I should take an ionic liquid? So let me come back to the perovskite. The perovskite is an ionic compound. The bonds are not very strong. So there is a movement of ions in the perovskite composition. Can we stop this movement of ionic moments by incorporating the ionic liquids, which has a positive and negative charges in this ionic liquid? And instead of having just pure ionic liquid, we functionalize this ionic liquid with the fluorinated substitutions. The purpose here is to create the hydrophobicity of this ionic liquid so that you can prevent the moisture-induced degradation of the perovskite solar cells. That's the goal of these studies. Now, if you look at what is the decomposition product of perovskite? The decomposition product is formation of lead iodide, methylammonium iodide. Now you can see here, the pure perovskite, the formation of lead iodide is clearly visible. So this is a expanded spectra. This is a characteristic peak of lead iodide, XRD peak. And this is a formation of lead iodide. As we put 1% of this ionic liquid, we decrease the formation of lead iodide. If we increase the 2% ionic liquid into the perovskite composition, you can see significantly decrease of the lead iodide formation. And with the 4%, so the perovskite composition extremely stable. So this gives you hints how to stabilize the perovskite composition. And here is another demonstration to show that 1% of this ionic liquid and the perovskite films exposed to 2 months at 50% humidity. And this is the front side with 1% of ionic liquid. This is the back side with 1% of ionic liquid. On the left side, what we are seeing is a reference sample. So there is a clear difference that having this fluorinated ionic liquid is protecting the perovskite solar cell. Now the question is, again, where is this ionic liquid? So the efficiency data is shown here. I will not go into the details. They are typically in the range of what should be expected. But my question here is to answer how this excess of this hydrophobic ionic liquid is protecting your perovskite composition. So then we have taken the focus ion beam. So let me just give you the detailed information here. So this is the binding energy of the fluorine. This is a reference. So the binding energy of fluorine comes around 689. This is a binding energy. This is a reference which we measured. Now we take our grains of the perovskite. With the focused ion beam, we dig it from the top to bottom. On the top at 0 nanometers, you see clearly presence of 688 peak. That's coming from the fluorine binding energy. Now, if you go further deep, at 50 nanometers, and we still see the peak coming from this presence of fluorine. At 75 nanometers, there is nothing. So that means what is happening here is this hydrophobic ionic liquid forming a shell around the perovskite grain. Why should it form a shell around the perovskite grain? It's because the solubility of the fluorinated ionic liquid is not good in the DMS or DMF solvent. It's floating during the crystallization process. It's forming a nice shell around the perovskite grains, and that's the reason why we could enhance the stability of these perovskite solar cells. This is again demonstrating with ionic liquid. You see, even after 720 hours at 60 degrees temperature, there is no formation of lead iodide. On the contrary, you can see the significant formation of lead iodide in the reference sample. I take another example for the ionic liquids, why we should work with the ionic liquids. In the perovskites, when you mix and then you form the thin films, the crystallization process is uncontrolled. So now we want to control the crystallization process by bringing the functionalized ionic liquid. Here, the functional group we have identified is a cyanide. Cyanide is a coordinating ligand. Lead 2+ is the acid, so it can coordinate. Once if you have a coordination, then you can slow down the crystallization process. So that's the purpose of having this functionalized ionic liquids, particularly coordinating groups. So without going into the details, so we have taken several types of ionic liquids. I highlighted only 3 here. Among the 3, with the butyl cyanide group is giving the best efficiency. And if you look at the stability is remarkable compared to our reference sample, which is the black. And the remaining types of ionic liquids are blue and green, which is shown here. Now I come to the interface engineering. This topic is quite interesting. Interface engineering is very important to increase the VOC and increase the fill factor because of the increased conductivity. So I introduced the low-dimensional perovskite here. So far, what we have seen is discussed is a 3-dimensional perovskite using a small cation which fits into the cavity of the perovskite matrix. Now, what happens if we have a larger cation? The larger cations examples here I have shown. There are several cations in the literature, but we discuss only phenylethylamine and then the flow substituted phenylethylamine cations. So what happens if we increase the cation size? Now we slice the perovskite because it doesn't fit into the cavity. Now we slice the 3-dimensional perovskite into low-dimensional perovskite. But the beauty of the low-dimensional perovskite is extremely stable, but the efficiencies are low because it's absorbing only a small portion of the visible light below 500 nanometers. On the contrary, the 3-dimensional perovskites are extremely high efficient, but the stability is questionable. So at this stage, can we combine 3-dimensional perovskite and 2-dimensional perovskite layer by layer deposition? How can you do that one? Well, since you remember we mentioned that excess of lead iodide. So the excess of lead iodide, by using this cation, they can form on the surface a surface passivation layer. That's what you will see in our presentation. So now I characterize this 2-dimensional perovskite. The 2-dimensional perovskite structure is shown here. That's a phenylethylammonium cation, lead I4, and this has absorption spectral properties below 550 nanometers. And this is a black line is a typical the 3-dimensional perovskite, and the red line is a deposition of the 2-dimensional perovskite on top of 3-dimensional perovskite. So if we have to characterize that whether the presence of the 2-dimensional perovskite is there or not. So if you look at the pure 3-dimensional perovskite, that's a black XR. These are the XRD characteristics. The fingerprinting is around 14.8. This is a pure 3-dimensional perovskite. And the pure 2-dimensional perovskite is shown on the top, that's a green. And the characteristic peak of 3-dimensional perovskite is below 5 delta 2 theta. Now, if you look at the 3-dimensional and 2-dimensional perovskite two together, you see the presence of 2-dimensional perovskite, you see the presence of 3-dimensional perovskite. So this is a way of confirming that we do have a layer by layer deposition. And another technique which we have used is exciting by using 450 nanometer lasers from the top side and from the bottom side. Since we have a deposition of the 2-dimensional perovskite on the top, you can see the emission coming from the 2-dimensional perovskite, which is a very characteristic peak of the 2-dimensional perovskite. And now, since the lasers, the penetration depth is below over 50 nanometers, now we can see touching the perovskite onto the three-dimensional perovskite, and the emission coming around 760 nanometers. As a reference sample, you don't see any two-dimensional perovskite. And similarly, and if we excite from the bottom side, the two reference sample as well as the with the layer by layer deposition sample, they overlap. It clearly shows that the deposition of the two-dimensional perovskite is exclusively on top of three-dimensional perovskite, forming a layer by layer. So this is what we call interface modification. It's fine. What is it is doing? Now we did the UPS analysis to find out the energetic scheme of these materials. So this perovskite material energy level is HOMO level is well aligned with the two-dimensional perovskites, and then the two-dimensional perovskite has a well aligned with the HOMO level of the whole transporting material. So this way you will get a efficiencies in the range of 18.65. But if I using this two-dimensional perovskite on the top of three-dimensional perovskite, the VOC increased from 1.09 to 1.14, even though it looks very small, but there is a clear difference in the VOC. So this enhanced VOC is coming because of the reduced recombination at this interface. What happens is when the electrons come to the two-dimensional perovskite, the LUMO level is quite high. They are directed towards the ETL layer, whereas the positive charges are extracted into the whole transporting material, therefore reducing the recombination at this interface significantly. As a result, you can see enhanced VOC. And then the champion cell efficiency at that time was close to 21% efficiency. But the take-home message is, by having this two-dimensional perovskite on top of three-dimensional perovskite, the maximum power point tracking up to 800 hours, you can see the two curves here. The red one is with the two-dimensional perovskite, and the blank ones is under argon atmosphere, stability data measured under argon atmosphere, and the filled one is encapsulated cells measured under normal conditions. And similarly, without two-dimensional perovskite, measured under argon atmosphere condition, and the filled circles are measured with the glass-to-glass encapsulation under normal conditions. Now you can contrast having two-dimensional perovskite on top of three-dimensional perovskite, not having the two-dimensional perovskite on the top of three-dimensional perovskite. You can see the huge difference in the stability. Now, can we further modify? Since we know very well the hydrophobicity will prevent the hygroscopicity of the materials. So here we have taken the fluorinated. So I took two examples. One is a fluorophenylethylamine, and the second one is the pentafluorobenzylamine. So these are the two examples. And similarly, you can see the absorption spectral properties of the two-dimensional perovskites and the absorption spectral properties of two-dimensional perovskite deposited on three-dimensional perovskite. Black one is the reference, and the blue one is the fluorophenylethylamine, and the red one is a pentafluorobenzylamine. Now, if you go directly without characterization techniques, we directly go to the PV data. That our reference sample is giving me 20% efficiency with 1.09. Having fluorophenylethylamine as a two-dimensional perovskite, my efficiency increased from 20 to 21% efficiency. And this VOC increased from 1.09 to 1.13. And similarly, the pentafluorobenzylamine efficiency increased from 21.3 to 21.65, the VOC from 1.09 to 1.15. This is a small difference, but the striking effect is you can see the stability. This is pentafluorobenzylamine is more stable than the fluorophenylethylamine compared to the blanks, the reference sample. This is our recent study where we have used this type of isomeric configurations of various cations. This is the para, this is the meta, and ortho. As you know, that's the two-dimensional perovskite formation is not happening with the ortho substitution, that's this one, and the meta substitution, that's this one. But however, if we use the para, this group, sorry, the para group, the two-dimensional perovskite is forming. So the take-home message is, even though we are not forming a two-dimensional perovskite, but the efficiency is quite remarkable here. This is our reference sample, that's at 20%. Having the para substitution one, it gives a similar to the reference sample. The meta is somehow decreased significantly. We don't know the reasons, but on the contrary, and the ortho increased significantly the efficiency. The best efficiency is 23.92. And so this ortho substitution it gives you some kind of a binding to the interface, and that is giving us enhanced efficiency as shown here. So the data is shown here exclusively for the ortho-substituted cation. So here we are not forming a two-dimensional perovskite. It's just a surface specification using the organic cation. Very quickly, I move towards the charge transport materials. So here is the ETL layer. First, I'm focusing on the ETL layer. Within the ETL layer, we are using compact layer of TiO2 followed by TiO2 or tin oxide or mixed layers. Now here, if you look at the data, the stability, because I'm focusing on the stability data, pure TiO2, you can see the decrease of the stability. And now if we use a pure tin oxide, the performance is significantly enhanced. And if we combine TiO2 followed by the tin oxide, the data is overlapping with the tin oxide. Why this is happening? When we use a TiO2 as ETL layer, there will be some UV component which is penetrating and exciting the TiO2 and then damaging the interface between the perovskite and ETL layer. This you can see clearly after a few thousand hours of the excitation, the delamination is happening. Now, by having this surface specification tin oxide, so the delamination is decreases significantly. So this way you can improve the stability of your perovskite solar cell by modifying the ETL layer. So there is another paper which we worked on this modification of the ETL layer. So we have taken a typical sunscreen which everybody uses during the summertime. So from this sunscreen, we incorporated into the tin oxide as ETL layer. So it's to reduce the UV-based degradation of this material. So the efficiency is increased significantly compared to pure tin oxide reference sample. This work you can find this recent publication of our advanced material interfaces. Now I take another approach. So far I have talked about the TiO2, but the type of TiO2 is the nanoparticles, which I have discussed. What happens if we change nanoparticles to nanocrystalline material? So here is the study based on a comparison between the nanoparticles, TiO2, this is a nanocrystalline material. So if you see this one, so small difference in the energy level around say 10 millielectron volts, but however, so this is a configuration, but the conductivity of this material, nanocrystalline material, is significantly increased compared to nanoparticles of TiO2 based on the conductivity measurements. And using this type of configuration, we obtain very high efficiencies, close to 23% efficiency and 22% on the maximum power point scanning. But the important information is, even if we use this type of materials with the mini modules with the 9 subcells, and that gives you 10.15 volts, showing extremely well structured P1, P2, P3 configurations that gives you very high VOC. And if you look at the fill factor of the nanoparticles is 81, and fill factor of this nanocrystalline material is 84. So this is due to the enhancement of the conductivity of these nanoparticles. So this is another way of increasing the power conversion efficiency of the perovskite solar cells. I have a last couple of minutes. I quickly scan to the whole transporting material. So this is a spirometad which everybody is using. Spirometad is a non-conducting material, so we have to dope with the different dopants. The dopants are highlighted here: lithium TFSI, pyridine. So what happens? And cobalt complex, cobalt 3 complex removes 1 electron from the whole transporting material, and it makes more conductive. But the whole transporting material, once if we have this removed one with the dopants, you can see without dopants, the contact angle measurement shows 77 degrees, this angle data, and with the dopants 56. That means it's proven to the hygroscopicity. Second problem with the whole transporting material is this pyridine, which we are using, it attacks to the molecule as a nucleophilically. So these are the disadvantage of this material. So we developed new whole transporting materials, and this work was published in 2016. Here, the concept is to bring the interface close to the whole transport material so that you have a strong interaction between the whole transport material, particularly the sulfur groups as a d orbitals. You have a strong pi back bonding from the lead. So we want to enhance the interface by creating within the whole transport material. This is a concept in this paper. And here the efficiencies are comparable to the spirometad. And at that time, this is a remarkable data. And now this is our recent work where we focus on the carbazole substitution versus methoxy substituted amines. So if you look at the spirometad as our reference sample, the power conversion efficiency is 23.37. Now using this carbazole BSC-50 molecule, which is a carbazole substituted one, which has a 22.65% efficiency. And if we replace the carbazole by methoxy substituted phenylamines, so which has a 21.26% efficiency. So this shows the modification of the stable whole transport materials is still possible and reaching the similar efficiencies. And similarly, we made the mini modules, and the mini module efficiency is 21%. Now, all these molecules are still doped. Can we develop a dopant-free whole transport materials? So here is the concept here is when we have a disk type of molecules, they can stack each other and then they can conduct the positive charges through this stack. That's the concept here. Since we have seen the thiophene groups binds to the surface, so we want to incorporate thiophene groups. So here are the three cases I am showing. One is a disk type of core followed by monothiophene, disk type of core with the 2 thiophenes, disk type of core with the 3 thiophenes. So the difference between the data here, spirometad, which is 19% with the dopants, and KR321, which is here, KR321, the middle entry, red entry, it has a 19% efficiency. But the difference is that the spiro is fully doped with all the dopants which I have described before. Now this molecule is from the lab to the solar cell and it gives the same efficiency. So this is a first time we reported dopant-free whole transport materials comparable to spirometad. And now we have a very recently published on the phthalocyanins, because phthalocyanins also very nice stacking molecules. So phthalocyanins are quite interesting, very stable, and most of our products contains phthalocyanin. So, but however, the efficiencies are slightly lower, but the take-home message between the phthalocyanins using different metals, zinc and copper, zinc is the best one, 20% efficiency. Among the substituents, methoxy versus branched methoxy, the methoxy is the best one. Now, I quickly go through the dopant, the whole transport material field devices. This is the work which we published long back, 2017. And the take-home message is this triple layer configuration of, this is another configuration, triple layer configuration of perovskite solar cells. They show extremely stable performance up to 12,000 hours. But if you look at the efficiencies, not very high. It's around 10% efficiency. So can we change this configuration? Since we have the knowledge of the two-dimensional perovskite, combining the two-dimensional perovskite and the graphene, similar to here, then we can increase the efficiency and the stability. And this is our recent work, this is collaborative research work between Fraunhofer and the EPFL. So this work shows the concept here, combining the two-dimensional perovskite, which reduces the recombination at the interface, and using graphene as a whole transport material that gives a stable performance up to 500 hours. The efficiency goes up to 18.2% efficiency. So this is a remarkable data compared to 10% efficiency, 18.2% efficiency. Now, I quickly, remaining 1-2 minutes, I just quickly go through the design of a cost analysis of 100 megawatts perovskite solar panel manufacturing process. This work is published in ACS Energy Letters. So here is the different configurations I have highlighted. There are 5 options, and among these 5 options, I take the option 3, which is if I want to produce 1 square meter of perovskite panel, the material costs me $2.7. And if I go gigawatt scale, the materials cost me $1.9 per square meter. That's a material cost. And if we have a perovskite solar cell manufactured, and then the minimum selling price, manufactured selling price is $0.35 per watt. Now, this manufactured selling price depends on the the power conversion efficiency. Suppose if the power conversion efficiency is around 10, so the manufacturing minimum selling price is $0.6 per watt. And if the efficiency is in the 20% region, then we have a $0.4 per watt. This is that's a cost of the watt. Now, if somebody is interested, how much a square meter of perovskite panel costs, and this information I can give you, it costs $36 per square meter based on all these calculations. Now we have taken two more calculations. That's a levelized cost of electricity, which is typically 3 cents depending on the regions, but I'm taking the lowest region, that's Egypt and Poland, which gives you, Egypt and Spain, which gives a 3 cents, the levelized cost of electricity per kilowatt hour. And this levelized cost of electricity again depends on the efficiency. The graph is shown here. Now, energy payback time. Suppose if you install the perovskite solar cells on your rooftop, how much time is required to get your money back without installation cost? It's less than 1 year. And if we incorporate the installation cost, it will be 1.5 years. So these are the cost analysis, which is very interesting. And if somebody is interested, they can contact me. So my take home, my time is up. And so I would like to highlight my conclusions. Stability is generated by 3D, 2D configurations. And we showed you the highest record certified efficiency of mini module 22.4, that's a certified, and 22.9 in the lab. And this single crystalline TiO2 now data I have showed. Atmolite, this is a Chinese company, they have reported ours is still 6.5 by 7 centimeters. Atmolite 2 weeks back, they reported 18.2% efficiency of a module containing 30 by 30 centimeters. So these are my group members, which I have to thank them because it's their contribution, and the funding is coming from various organizations. I would like to thank the funding and thank my group. And if you have any questions, just to follow our either Facebook or ResearchGate or LinkedIn or Twitter, so that you will get all our publications and information on a weekly basis. Thank you for your attention, and I will be happy to answer your questions.
Thank you very much, Professor Naziruddin. Wonderful talk, lots of information, and I think all the participants have some idea that how we can get the stability of the perovskite solar cell, including their chemical engineering. We are running out of time, but we will stick to a few questions. There is a questions from Saravan from India. He's saying that I'm working in the field of using anti-solvents to make best thin film perovskite solar cells. Which anti-solvents is best to make a high quality thin film perovskite solar cells?
Okay. Yeah, this is a very interesting question, and there is a lot of studies, and from my group also we have done very extensively on different solvents. So to make it simple, use diethyl ether. This is a very good anti-solvent. And if the diethyl ether, depending on the availability or good quality, if it's not there, then use chlorobenzene.
Thank you, Professor. Another question from Shantanu Shaha. He is asking, what is the key difference between nanoparticle and nanocrystal from the point of view of crystallinity? Do the nanoparticle lack crystallinity? That is, are they completely amorphous? From what I understand, crystalline structure is necessary to give rise to suitable electronic structure, that is the HOMO-LUMO levels or band gap. So how crystallinity matter, what I understand, to get the stability?
The data which I showed, the crystallinity is just to enhance the fill factor by increasing the conductivity of the electron transport layer. Not the stability. The stability with the TiO2, we always have the same problem because we are exciting the TiO2, which by UV light, and this TiO2 is eating the interface. Stability, I'm not talking here. So we are increasing the fill factor by increasing the conductivity of semiconductor crystalline material compared to the nanoparticles. Sure. So this data is just exclusively to increase the fill factor by increasing the conductivity, which we measured the conductivity data of these two ETL layers.
Okay, thank you very much. We are as running out of time. So I think Professor Gondal is on board still, I can see. Professor Gondal, I think one question is for you. Is that how photocapacitor potentially useful for the society? Are you on mute, Professor? Yeah.
Can you hear me?
Yes, we can hear you. Yeah, just one quick question for you.
Yeah, just 1 minute. Let me raise my sound. Yes, now please go ahead.
Yes, the question, one question is for you, that how photocapacitors potentially useful to the society?
Yeah, it has a lot of applications, especially when you need very fast switching of any action. You need such supercapacitors, especially when you have a car and you want to stop it, electric car or bus or a truck. So it can promptly, you can, discharge the charge on the brakes, and you can even recover such, energy through this braking system. So this supercapacitor can store that charge which you lose on the friction between wheels and your brakes. So that's one big application, and then it can be used in many other medical applications, especially now if somebody has a heart attack and you like to discharge on her chest, give a shock, so you can discharge a lot of charge fast on that chest if you like. So there are many applications coming up for this, especially fast charging and fast discharging. So it's very useful for the society.
Thank you very much.
Any other question? There was another question, I think they were asking me.
Yes,
CIGS.
Yes, I can see many questions, but we don't have time to, discuss in this short period of time. So
Okay.
the participants can directly ask the question to the speakers. I think their biographies and email IDs all are in the website. So please go through. Thank you so much for your time. Thank you so much, Professor Naziruddin. Thank you so much, Professor Gondal, for your valuable time and accepting our request. It is a great, glad to welcome all of you, and our pleasure. Thank you.
Same feelings from our side for you. You gave us opportunity and you provided us this platform.
No problem. Okay,
Thank you very much.
Thank you all. We will moving to our next category, which is the early career researcher session, and we will start with Dr. Mohammad Zafar Sadiq. He is currently doing a postdoctoral researcher in King Fahd University of Petroleum and Minerals from Saudi Arabia. Over to you, Zafar. Are you there? I can see you, Zafar. Could you mind to share your screen? Zafar, are you there? I can see you, but I...
Dr. Sadiq, please can you unmute yourself?
I think he has some technical problem, looks like.
Is Dr. Abdul Khan available to come and do his presentation, please?
Abdul, are you available? I'm sorry, due to some technical reason, our speakers are on board, but they can't able to share screen. Yeah, I can see Abdul is here. Abdul, am I audible and visible to you?
Can you
We
hear me?
can't hear. Yeah, we can hear you now. Could you mind to
Okay.
go for your presentation, please?
Yeah, sure. I will.
Thank you.
Thank you so much. Thank you, Dr. Anurag. Can you share? Can you see my screen?
Yes, we can see, but it's not in slideshow mode.
Now?
Yeah, it is. Perfect. Yeah. You have 15 minutes, okay? Yeah.
Yeah, sure.
Yeah, thank you.
Thank you so much, everyone. I hope everyone can enjoy this presentation, and thank you so much for International Conference on Solar Energy Materials and Technology. Actually, I did my PhD from King Fahd University, and now I just joined Foreman Christian College. So today I will start with the recent trend that hematite surface and electrolyte interface for photoelectrochemical water spreading. My name is Zishan, and you can find me in the Google Scholar as well. And if you have any query, I will update my email also. So I will quickly go for the outlines, and which is motivation, introduction, methodology, result, and discussion. And finally, I will conclude with the conclusion and outlooks. Actually, everybody know about the carbon footprints, about why the global warming is increasing, about we are using non-renewable energy resources, oil, coal, natural gas, nuclear energy. These are depleting, and they are increasing the carbon footprints over the entire universe. And actually, by using these non-renewable energy resources, we are actually burning our earth. So we have to think about the other resources, like what we can see, which is one is hydropower, ocean energy, bioenergy, wind energy, solar energy, geothermal energy. And we can also utilize the main thing is hydrogen energy, which everybody is working nowadays. And it's a very hot topic nowadays that everybody is working on. So now if we move further about the hydrogen economy, so we see there are different types, like by using photovoltaics with electrolyzer, and by photoelectrochemical water splitting and photocatalytic water splitting, we can able to generate hydrogen, and this can be utilized, like we can store it as well. And this can be utilized for different applications, for the power, for heating, industrial process, electricity, fertilizers, by using the ammonia. And this can also be in the coming years. It's still people are using for some cars, buses, and this is one of the example in Saudi Arabia, like in 2030 visions. They already started a pilot vision, the Iran Techno Valley. They have a pilot station for hydrogen pump. And moreover, whenever we are discussing about these three different types, we always discuss about the price and the high efficiency, and photoelectrochemical water splitting is like among between these three, these two, like the photovoltaics with electrolyzer and with photocatalytic water splitting, it's more or less good opportunity for the hydrogen production. So in case of solar energy driven water splitting, we always consider, like in electrolyte, we have photoanode and photocathode. We shine with the sunlight, and once we shine, for example, if you have an N-type semiconductor material, so the holes and electrons are generated, and these electrons jump to the higher conduction band, and the holes left behind the valence band. So now, if you are considering about these electrons, so they are going back contact to the counter electrode, which is platinum electrode, and they are involved in the hydrogen production. And for example, for in case of holes, which is present in the valence band, which we can say, like if you have like your working material, So these holes can be utilized for the water oxidation. Now the point is, we are more interested for the hydrogen production, but still the people are more interested in the oxygen. Why? Because it is a rate limiting step. So if you are somehow like, you can say you are able to utilize more oxygen production. So of course you are using the platinum electron, which can give you the best efficiency. So the people are working on mostly on the N-type materials to get more hydrogen production in case of solar energy driven water splitting. So now in case of, if you are considering the material, any material of like a photoanode, so in that case, if you shine with the light, the holes electrons pair are generated. They may recombine or they may go to the surface. Whether once they reach to the surface, they may also recombine on the surface, or they can utilize for the water oxidation process. So now if you consider about the absorption of absorption of the sunlight and carrier generation, it is almost from femtosecond to the picoseconds level. And then if you are distinguished between the charge separation of these charge carriers and the bulk recombination, it's almost in between this level from till you can say into milliseconds level. And the surface recombination, it reaches from milliseconds to the seconds level, and which we are more interested, which is water oxidation. It's are like in from seconds levels to more onward. So the life is started from femtoseconds to the seconds level, and these electrons and holes are needed to stay on the surface for seconds level to in order to utilize for water oxidation or reduction. So now, if we are considering for the characteristic property of the ideal photoanodes, there are some characteristic properties like they must have good absorption capacity, high chemical stability in the dark and light, low cost and abundantly available. And moreover, it must have the lower potential for the oxidation of water. The band edge position must overlap the potential for water oxidation, and the efficient charge transport must be there. So in case of like, if you're considering some materials, so they are like photoanodes because their valence band is lower than the water oxidation band. So it's more suitable for the water oxidation. So now, in case of these semiconducting material, we are more interesting for the suitable one. So now if we consider, we are considering the hematite. Why we are considering the hematite? Actually, the reason is it has suitable band gap, which is around 2.2 electron volts. So that can be able to produce 12.6 milliampere per centimeter square if you are using the visible light spectrum for the sunlight. So these have some characteristic properties. And for example, if you are considering about the hematite material, so it has good absorption capacity. Also stability is very good in the dark and high drastic situation like in the sodium hydroxide solution, and low cost, and it's abundantly available. The drawback is the charge transport is not efficient, and in case of the over potential is very less in case of if you are considering for hematite materials. So now if we are considering about the recent trends of hematite, so by using the Scopus, we are using Scopus to analyze the data. So we can see the hematite has approximately 13.36% of the total data available for the photoelectrochemical water splitting process. And the rest, the second number one is 11.44 with bismuth vanadate, and the rest are 64.96 for the rest of the electrodes. And now we can see around 1,000 papers are published over the year from 2002 to around 2023. So you can see a lot of papers are working on the hematite surface. So now about the current, if you are considering, so now the people are working and they are able to achieve the 6 milliampere in 2017. So this is the highest current until now the people achieve for the hematite electrode. But as I mentioned before, we can able to achieve 12.6 milliampere. There are some problems with the hematite electrode. So for example, if I consider for the hematite electrode, how we can prepare, there are different methodology, but I will go with one of them, which is chemical bar deposition for the hematite preparation. So we have aqueous solution of iron chloride, and we we do the hydrothermal treatment, and we able to achieve iron oxyhydroxide, and then we calcine at very high temperature for this FTO glass, and then we almost achieve the bare hematite electrode. And once we do the XRD analysis to confirm, we get the hematite layer or we get something else. So around 37.3 and around 64 degree for a degree. This gives us the bare hematite. It's basically for the hematite electrode, and the rest of the peaks, if you're considering, because we are using the glass, so it's almost related to the glass tin oxide peaks. So now we modified the bare hematite by using the phosphate ion modified solution by different optimization, the pH, absorption time, calcination temperature. With respect to also calcination time, we are able to modify the phosphate layer. And now actually the bare hematite have the hydroxyl group present on the surface. So once we lower the pH of the surface, it is positively charged, and if we increase the pH, it's negatively charged, which is basically we call as 0-point charge, which is around 8.3. We go below, we get positive surface charge, and if it is we are going above, the surface is negatively charged, and we can attach the other materials for this type of things. So in case of our, because phosphate is negatively charged, we move to the lower pH. So now we confirm, because from XRD we are not able to achieve the phosphate is attached to the surface, so we move to the XPS analysis. And we see the phosphorus is not present for the bare hematite, but around 133.7 electron volt binding energy confirm the phosphorus is present in the phosphate group. The phosphate group is present, and now we can also see what is the effect of the phosphate. It's basically creating the oxygen vacancies, and we can see from the bare hematite this shoulder peak is not appeared, and once we deconvolute, we see this oxygen vacancies is much more as compared to the for the bare hematite. So we also did the hydrogen treatment in order to confirm that this shoulder peak is appearing, and which is creating the oxygen vacancies. So we did the hydrogen treatment, and we see this shoulder peak is appeared, which confirm the oxygen vacancies are created by creating the defects. So we modified with the phosphate to increase the oxygen vacancies, which is more suitable for the water oxidation process. So actually we did with the phosphate modification, and which basically lower the band gap, and we can also say, like, because of the absorption, there is no change in the absorption spectra. So it's completely shift entire band structure towards down, and which is basically suitable for our co-catalyst, which we basically modified with cobalt iron % blue analog. So this is basically the methodology we and the experimental setup we used. This is the photoelectrochemical cell, and this is the NOVA instrument, and this is the solar simulator we used for these measurements. And now if we are considering for the cobalt iron, as I mentioned before, so we did the simple CELAR process, which is successive ionic layer adsorption reaction process. So we dip in the iron and cobalt solution, and we see a different formation of cobalt iron % blue analog on the phosphate modified layer. So as we can see, we did the linear sweep voltammetry for confirming that there is a difference by modification of phosphate layer, and we see the enhancement, which we can say around from 0.4 to 0.7 milliampere per centimeter square once we modify with the phosphate. And once we modify with the cobalt iron % blue, there is a significant change, and it reaches to the 1.2 milliampere per centimeter square for the phosphate modified hematite electrode. And we also did with the cobalt iron % blue for the bare hematite, but the change is not so much significant as we see from the phosphate with cobalt iron % blue analog. So we also did the whole cell solar conversion efficiency, and we see IPCE, and it's also consistent with the LSV measurement, and we can find out by using this formula. And actually half cell efficiency we also calculated, and we can say once we modify it with the phosphate with the cobalt iron % blue, it's actually created a 200 milliwatt cathodic shift in the potential window, and which is significant in terms of half cell efficiency. And moreover, we also achieved from 0.2% to 0.7% efficiency, which is significant in terms of if we are considering the terms of efficiency for the half cell efficiency for hematite electrode. So these also we can also confirm that our modification is we also did the Nyquist plot for the EIS measurement by using solar light, and we see there is a change in the Nyquist plot, and we also fit this circuit by using the equivalent circuit. And basically this is for the hematite bulk electrode, and this is basically we use for the charge transfer resistance for basically semiconductor electrolyte interface in terms of hematite with electrolyte. So we measured and we calculated the RCT values, which is charge transfer resistance, and for the different electrodes we find these values are reducing after the modification. For example, for the bare hematite, the resistance is around more than 4K kilo ohm, and it's reduced to significantly to around 0.5 kilo ohm once we modified with the final cobalt iron % blue with the phosphate group on hematite electrode. So now we also find out the role of cobalt iron. It is either water oxidation or it is acting as a passivation layer on the surface of the hematite. So we have the bare hematite. We measured this in sodium sulfide, which is act as a hole scavenger, it can absorb all the holes which is present on the surface of the electrode. So now, for example, if there is any holes present on the surface which may recombine, so these holes can be extracted by this sodium sulfide. So that's why we call as a hole scavenger, and we put it in the same solution, and we can see for the bare hematite, it's moved towards high current, and these dotted lines is basically with sodium sulfide, same condition, same electrolyte, but we added with sodium sulfide. And we can see significantly there is a change after the modification of bare with cobalt iron % blue analog, even in the case of with sodium sulfide. So we extracted the data from the sodium hole scavenger and the linear sweep voltammetry, and we can see it directly this charge separation. The charges very good separated in terms of when we modified with a cobalt iron % blue. So that means it's passivating agent. So that means it's passivate the surface and it reduce the recombination on once we modified with a cobalt iron % blue. And it's also catalyzed efficiently in terms of cobalt iron % blue on the surface of phosphate or hematite surface. So we see there is a clear change on the bare hematite surface. So this basically indicates that our catalyst cobalt iron % blue is actually playing a role for passivating agent, and moreover also it's acting as a catalyst on the surface of phosphate group. So now if we are considering
sorry, Dr. Jishad, you have just 1 minute left. Could you mind to conclude, sir?
Oh, okay, thank you, I will do. So I will quickly go to the conclusion. So we modified with the different doping in order to enhance in order to reduce the charge, you can say the bulk recombination, and we introduced some oxygen vacancies by using the bismuth ions, and we also passivate the surface of the hematite surface by different catalysts and by the PI layer with the lanthanum oxide layer, and this can be also, we also activate the cobalt iron % blue system for water oxidation process. And we used CoPi and gold nanoparticles in order to use that a water oxidation catalyst, which can effectively utilize those holes present on the surface of hematite, can go easily for the water oxidation process. So if we consider about this is basically the picture for the hematite electrode. So this is the iron, the people are saying about the researcher are contributing for the hematite electrode. This on-site potential is shifted towards cathodic shift by using the surface chemistry and catalysis, and by doping and by other catalysts. modification, we can reduce the bulk recombination and we can achieve the 12.6 milliampere current by using this doping and the surface modification. And thank you so much. And actually, again, the hydrogen is basically, like we can say, the future of the coming, you can say, the coming future energy resource. Thank you so much.
Thanks a lot, Jisan. I'm sorry we are running out of time, so we need to stop it in a hurry. So thank you so much for considering our request. So we will move to our next speaker, Dr. Katie Shanks from the University of Exeter, UK. Katie, over to you.
Thanks, Anurag. Can you hear me okay?
Yes, all good.
And hopefully you can see my screen as well.
Yeah, it is visible. Yeah, cool. Please.
Yep. So my name's Katie Shanks. I'm a research fellow at the University of Exeter, based in the Environment and Sustainability Institute. And my research focuses more on conditioning the light before it hits the solar cells, so before it hits the perovskites, etc. And that's those devices are called concentrator photovoltaics. Whenever you have optics that focus the light onto the solar cells or filter the wavelengths or do some kind of light management. And this also involves a little bit of biomimicry, which I'll get into. But as part of optical design, obviously materials and surface structures are very important. So first of all, solar concentrators, for those of you that haven't come across them yet, in their simplest form, so for example, in your the image to the left, far left, they are literally mirrors or lenses that help funnel light towards a solar cell. And those solar cells could be big solar panels or very small, 1 centimeter by 1 centimeter size solar cells, or now we're even seeing smaller than that. Fresnel lenses are a very popular type of solar concentrator. So for example, your second image there is an example of a Fresnel lens which focuses light down to a solar cell. And these types of optics have been used in lots of devices before in PV technology. So they were used in lighthouses before, for example, but they only became popular in lighthouses actually when we discovered things like PMMA, so a lightweight material that we could structure more efficiently and at a low cost. So that's just one example of how we had designs in theory that worked, but we need materials and manufacturing to then increase the popularity and the rollout of those devices. There's also more novel materials for solar concentrators, like luminescent solar concentrators. So in the bottom right of the page, we've got some transparent material that has luminescent materials inside, or things like quantum dots, which basically absorb light coming in and then re-emit that light to the sides, where you then have your solar cells. And this is one way of having solar windows, for example. And one of the reasons that we have solar concentrators, there's a few different benefits. One is that you can reduce the amount of PV material that you require, which can reduce your costs or your carbon footprint. But the main reason, or usually the main reason, is that you can increase your efficiency of the solar cell because of the thermodynamic limits and this increased flux that you've got in the solar cell. And so you've probably seen some of this this graph before, but some of the higher efficiencies are only possible with concentrating light. So the very highest efficiencies there, with a 47.1%, for example, is under 143 times light concentration. So they're using lenses or mirrors to increase the irradiance on the solar cells to get that efficiency. Specifically, what I look at, or what my research fellowship is looking at right now, is looking at the optics within nature to see if we can copy some of these nanostructures to make more compact, low-profile devices that are also lightweight. And in doing that, we can increase the applications and the integration of solar energy technology. So, for example, on the left here is, like I've said before, kind of a lens system that focuses light down to possibly a second optic and then a very small solar cell. This is quite a big, kind of bulky system. It's not practical if you're wanting to put this on a roof or on a car or something like that. So it needs to be a lot more compact, and we're definitely capable of doing that. There are lots of advanced optics that have reflective and refractive properties that manage light and filter wavelengths, etc., that could do these concentration properties at a much lower profile. And we need to do that to be able to, as I said, integrate into electric vehicles, for example, which are needing more power and higher range, or smart houses. So we've got a lot more technology and automation going into our buildings, and that includes things like thermal management of houses. And with that, you can also have electricity generation as well as thermal management. So the whole idea, you know, for all of us doing solar energy research is to try and increase the amount of solar devices out there. And we have to think about the practical considerations of that, as well as the things like efficiency. So if we try to break down what some of those practical considerations, as well as the scientific considerations in terms of performance are, we've got things like low profile. So on the left here, I've got concentrator photovoltaics and kind of the ideal performance requirements for them. Now, it's not usually possible to try and, you know, tick all of these boxes, but ideally you would have a low profile, you'd have them reliable and durable. So we want them to be able to last for a long time, so we get our monies back, but also so that we can, they have to be reliable so that they perform, you know, no matter if there's a storm outside or if it's high temperatures or low temperatures, etc. It needs to be a reliable source of power. With that comes sun tracking. So the system either has to need to follow the sun throughout the day and the year, or be designed such that even when the sun's low in the sky, you know, in the mornings and the evenings, we're still getting some power, or a good amount of power. We need it to be, if we are integrating this into more and more structures, there is aesthetics. So is it going to look good? Are people going to want to buy it? This is something that isn't usually thought about, but it is possible to change how they look. And if it's going to be integrated into your car, for example, or on the back of your laptop, or for example, inside homes to power things like automated systems or the Internet of Things. Like I said before, we've got a lot more smart technologies going on inside our houses. Then, yeah, people are going to care about how it looks. So that is an aspect. And then, of course, we've got high efficiency of the PV performance or of the optics and other parts of the system. And you want low cost and lightweight as well. So lightweight for practical terms, as well as transport and logistics, and low cost because, yeah, we need that. And if we specifically think about the materials which feed into all of those things, we've got things lightweight, of course, like I just said, low cost, all depends on the material. The scalability also depends on, you know, can we do certain processes with those materials? How tolerable is a material? There's things like the temperature tolerance and the UV tolerance, and the wettability. So wettability can determine how durable it is in terms of rainfall. So does it perform as well when it's got water on it? Can it self-clean if the water rolls off it and gathers away all the dust, for example? So these are all the things I could think of, at least for optical materials and also for concentrator photovoltaics. So if we're thinking about those aspects, those properties that we're trying to improve, and then we look at nature, there has been some biomimicry for some properties for solar cells already. So the moth eye, for example, has been copied for anti-reflection properties and to increase the absorption for solar cells. And there's a whole kind of world of research for which nanostructures work best and which are easiest to manufacture as well and low cost to manufacture. So that has already been done for solar cells. For the optics side, not so much. So I'm currently looking at two types of butterfly. There's the cabbage white butterfly on your left and the glasswing butterfly on your right. And these both have very interesting, unique nanostructures, which give them very reflective and also very anti-reflective properties. So the cabbage white butterfly has high reflectance, or I should say a very high reflectance considering how thin and its natural components. So I've compared this to the V-trough concentrator, and the cabbage white butterfly does the exact same thing in nature. So it holds its wings in a V shape, it funnels the light, concentrates it down onto its body, and by doing that, it heats up its flight muscles so that it can fly before the other butterflies. But same concept, the V-trough concentrator, we funnel light down and we have a little bit more light going into the solar cell, so we've got a little bit more power coming out of the solar cell, but the same area of PV material required. And I think I had a picture of a V-trough concentrator, similar to a previous slide. But by using these nanostructures, we can try and truncate that system down, which is what I'm trying to do, and make it more lightweight. And also the glasswing butterfly, because it's high transparency, so it has very anti-reflective properties even when the sun is very low in the sky, so very low glare. That could help increase the efficiency of the lenses or these optics that I'm talking about. And yeah, and I've already done some experiments with the cabbage white butterfly. So first thing first is just to compare the wings directly to reflective materials that we already have. And we found that the white wings do reflect enough light to increase the power output from solar cells by about 40%. And when you compare that with reflective films that we have available, they're not quite as good as reflective film, but the main advantage is the weight difference. So the power to weight ratio is much, much better for the butterfly wings. The wings are about 17 times lighter than the metal than the reflective films. So that could be a big advantage in terms of not just transport, but where can you actually install these devices if the weight is a lot lower. And this is starting to tick off some of the things we were talking about. The glasswing butterfly. So this graph shows the reflectance of glass is the blue line, and then the reflectance of the glasswing butterfly is the green line. So as you can see, it's a lot lower, especially in the lower wavelengths. It's surprisingly only 1 or 2% in those wavelengths, and then it kind of dips in and out due to the structure. But this could definitely increase the amount of light that's getting into the solar cells. And if we look at the transmittance, similar kind of dipping in and out, but you can see that it's higher than any of the other glass samples, and that's even if we go to very thin glass. So the thing about transmittance is obviously it depends on your thickness of your material. So trying to compare like for like, it's still, the glasswing butterfly still has a very high transmittance or low reflectance due to its nanostructure. Oh, wrong way. So right now, my research is looking at those properties of the natural optics and then seeing where they fit with the solar cells that we have. So obviously we've got single junction silicon solar cells, we've got multi-junction solar cells, we've got thin film CAD-TEL solar cells, we've got perovskite solar cells, and they've all got different response ranges of wavelengths, and it's seeing which solar cells these match best with, basically, and how we can maybe adjust the nanostructures to improve even more their performance in that wavelength range. So this is something I've done already, which is, like I said, using the glasswing butterfly and then just comparing with the different solar cells. So the glasswing is on top of a silicon solar cell, and that's the orange line. The purple line is the silicon solar cell with nothing over the top of it. And as you can see, there is already kind of an increase as soon as you add the glasswing for the higher wavelengths or the lower wavelengths, which is impressive because normally when you add something, add a layer, you don't usually see an improvement. You know, you're putting in more barriers between the light and the solar cell, so it should decrease, but we're getting a little bit of an increase at the far kind of 900 nanometer side. So again, that's kind of more proof of that nanostructure working better than the nanostructure on the solar cell itself. And then we've got the black line is the silicon with glass. So you can see that absorption and that reflection taking away. And we've also got some CAD-TEL reflectance there. That's that green, more interesting wave. And I've also started looking at how this affects the external quantum efficiency of the cell, or the effective external quantum efficiency of a solar cell with different layers on top. So if you've got glass on top, or if you've got nothing on top, or if you've got the glasswing on top, and then at different angles. So the wider angles, because of this anti-reflective property, we can see more efficiency gained at that, or more light getting through, and hence more efficiency gained at those higher wavelengths. Wettability, which we also mentioned, is one of the attributes of the materials. So on the left, we've got the contact angle measurements of some butterfly wings, and also for some plastic, and also for some initial titanium dioxide pattern samples I've been making. So the butterfly wings, similar to a lot of natural materials, have a very high contact angle. So I think, you know, the record, or one of the record materials for high contact angle is the lotus leaf. And similar to that, because of this nanostructure, this complex nanostructure with this very kind of porous pattern, it allows for very high contact angle. And in fact, these images were only a few that I was able to take because a lot of the experiments resulted in the water just rolling off the material. But yeah, so very high contact angle. And if you compare it with plastic, for example, in the bottom left corner, it's got a relatively low contact angle. And in fact, I also had a sample that had an anti-reflective coating on top of the plastic, but that just made the water very, very dispersive. So it just went completely flat, which is why I don't have an image of that. And then, like I said, initial kind of pattern samples are showing a better or improved contact angle, which is kind of a good start. So far, to round up that stuff, we're kind of starting to tick off a lot of those things that I was discussing, but there is still scope for, okay, what about UV tolerance or temperature tolerance? I know that from literature, butterfly wings should be very durable in the UV, but if we're making this synthetically with other materials, how are they going to perform? And scalability, so it all depends on the materials and the manufacturing, what we're actually able to do. And this is why this conference is very good for kind of collaborating and seeing, okay, what are other people working on and what materials, you know, I'm focusing on titanium dioxide at the moment, but there are plenty of other materials that could make these nanostructures and perhaps tick off some more of those boxes. And yeah, that's my presentation, and thank you very much.
Thanks, Katie. Wonderful presentations. And if you have any questions and suggestions, that Katie's email. So please contact. Due to time constraint, we have to, we need to conclude these sessions. But we have one more speaker, Sadiq from Saudi. So Sadiq, are you on board? Please respond if you are on board, or we will just stop the session and going for the lunch break. Sadiq, are you there?
I can hear him very faintly in the background, but I don't think his volume is working.
I think he has some internet problems, looks like. I can see he's on board, but somehow he's not. And please ask your questions if you have. So Katie has shared her email ID. Feel free to ask her any questions, and please post the questions if you have. We have a next panel discussion at 15:45 UK time. So we will try to raise all these questions at that time, if time permits. Sadiq, are you on board? This is the last announcement, or as we are running late, we have to go for lunch. It's not about we are hungry, that we have to stick to the time. Yeah. Hello, Sadiq. Are you there? Please respond something. I think he has some technical problem, so I'm sorry about this. So thank you so much for the first sessions, and we will go for the lunch break now. It's so we will come back around 1 o'clock UK time. So please bring back everyone, and thanks for your kind support and today's the first sessions, and thank you all the speakers with staying with us. We will be right back, and we have 4 more interesting ECR speakers after the lunch, and at the same time we have quiz. So please join the quiz, and there is a chance of winning Amazon gift vouchers for the winner or winners, we don't know. So stay with us. We will be right back after the lunch. Thank you. Hello, everyone. Welcome back. Hello. Hi. Welcome back. We are going to start our next ECR session, and we have our ECR speaker from University of Essex, UK, Dr. Shomdeep De. He's an assistant lecturer from University of Essex, UK. And he's a member of Force Technologies Council and TEDx, and the fellow of Royal Society of Arts. Shomdeep, are you there? Over to you. Okay, if Shomdeep is not there, we can shift to our next speaker, Dr. Krishanu De. Krishanu, are you there?
I think we need to go back to Youssef, please.
Okay, so they are not on live, no problem. So we can move to our another ECR speaker for today's session, Yusuf Chanchangi from the University of Exeter. Yusuf, are you there? Yeah, I can see Yusuf online. So thank you, Yusuf, for your time, and over to you.
Hello, everyone. Can you hear me now?
Yes, we can hear you and we can see your presentation,
All right.
but not in slideshow.
What about now?
No.
All right. Just a minute.
No problem. Yeah.
What about now?
Yes, it is there. Thank you.
All right.
So sorry to interrupt. Before you start, you have 15 minutes. And if the time permits, we can allow some questions for you. Okay?
All right.
Thank you. Yeah.
Thank you so much. Thank you, Anurag, and thank you all participants. My name is Yusuf Chanchangi. I'm a proud member of Solar Energy Group based here at the University of Exeter ESI building, where we have multidisciplinary lecturers or researchers that come together to ensure that we tackle environmental challenges. And here, I'd like to point out something. I put my line manager here because we did most of the research together that I'm going to present during this session. And I will introduce PV again to most, which I know all speakers know what's PV, but I would like to introduce it again so I can relate it to its performance in the lab and also when we expose it outdoor condition. And similarly, I will show some factors that affect the performance of PV when we expose it to outdoor conditions in the real time. And the main aim why we all try to make all these technologies to work very well at the moment is to ensure that we give access to affordable energy, which is reliable and sustainable for everyone globally. We just want to ensure that everyone gets good energy, so we try to protect the earth at the same time. And why is it so important now? Because of the climate emergency. At the moment, we have started to rip off what we've been doing to the environment. We are seeing the consequences where we see lots of disasters from flooding to in different parts of the world, from Pakistan to Africa in Nigeria, where we saw lots of people die, house, properties, investment got damaged. And through recognizing these emergencies, we try to ensure that we accelerate the penetration of this technology globally so we can reduce emission to the barest minimum that the Earth can contain. In doing this, our leaders met in Paris. They all agreed and they signed the accord. And similarly, they came to Glasgow last year. They sat down and said, all right, this is the target. This is what we need to do within this time. And this year again, they all meet up together, say, let's see what people are doing. But one thing they always see, and everyone blame the leaders. What about us, the scientists? What is our implementation level at the moment? What are we doing? Are we still looking at doing more research, or we are thinking of tackling the problem at the moment as ESI, which I know very well is doing at all angles? Coming to PV performance, if we can not deny the fact that silicon, which I have here with me, has been working very well in the industry, and you can see it everywhere you go. Every country is adopting the use of that to generate electricity, which provides clean energy. And this technology, when you leave it in the darkness on its own, it has power, but it needs illumination to generate the real power. So the voltage you see at dark level, you need to put it into light, and that it requires uninterrupted light for it to work very well. And when you get a very good result, it's in the lab when the condition is really perfect and everything is settled. What about when we expose it to outdoor conditions? We're going to see lots of trouble, because here it's a picture just beside our building where we are. There are lots of structures covering solar panels somewhere around here, which will create shading to the performance of a PV technology. Typically, this is what happens everywhere. When people put this technology on their roof and everywhere, that is what they get. They tend to have effect of shading or something that comes to block the light from making this technology to perform very well. And some of them are due to lack of pre-study of the region or the site that needs. And there are lots of available softwares. Some are very, very extremely user-friendly for people to use, and they can just adopt it to use without even being a scientist, so that they can know which kind of shading and how can they get the most amount of what they put when they install it outside. So in considering this, we conduct a lab study where we examine the performance of two technology, which is monocrystalline silicon and cadmium telluride. So we use this one thin film and a solid model to see what is going to be the effect of shading. Because based on assumption, people think that all shading has more effect on the silicon crystalline modules. And if you arrange, as we do here, a monocrystalline silicon model in the same pattern which we all do our TFM these days, in a pattern where the shading can affect the performance of the modules in a similar pattern, then you're going to see the variation. We expose these two technologies onto our lab testing equipment, the simulator, and then we measure temperature as well. And we put all these designs that we fabricated using 3D printer to try to create like sorts of shading that will occur when you install your panel outside. And afterwards, we did some optical characterization on all those materials that we used. And we see that all of them, one way or the other, they have effect of shading, that they can reduce the light intensity or lights coming to the cell to make it perform. And when we check the performance on a normal condition, they are working really perfectly. After being exposed to all these materials, we saw variation on their performance. It depends on the way it's been exposed to that model. They are all performing below standard when exposed to one or two shading type. If you look at, let me take a leaf, for example, which is one of the shading which I show you on the earlier picture. It has an effect on the performance. Definitely, this is just an ordinary leaf from a tree. And when you compare to something like a graphene, which is somewhere around here, it totally covers the whole thing. So I use graphene to replace a building. If you have a building which is just very close to it, it blocks the light from coming in. definitely the performance will be extremely low. To some extent, it will be just nothing that you're going to get out of it. Similarly, when you have a shading like this type, it's going to generate losses that are going to affect lots of performance. This is just a structural shading. Similarly, it affects the thermal characteristics of those modules. You can see here, we show how after some time, even without any shading, after time, then there will be losses, and the temperature will definitely affect the performance of all the model. And with excitation of heat and light at the same time, definitely we expect model. So how do this model will react when you expose it outside again due to environmental conditions such as soiling, which we know we have so many factors. I will just scan through this section very quick because of the time. If you look at these factors all here, these are what we cannot avoid. And they are the factors that influenced dust accumulation on a PV module, as shown here. And this will happen depending on the season, location, and the property around, and the human activity around where installation has been made. So we started also this one with the lab experiment where we put lots of samples, about 13 different samples ranging from charcoal, sand, all the particles that we expect to be moving around within our atmosphere or within the environment where we expose our modules. When we put them, we did the measurement and we see lots of losses where we saw extreme losses. From charcoal, we found about 98% of performance drop. Similarly, when you look at when you just put a salt, which we think it can even improve the light or have a little bit of transmittance losses, we record as extremity, at the lowest, we record about 7%. So it depends on the accumulation of the dust or material that is being deposited on the surface. That's where you're going to see the amount of percentage that will increase. And all this thing, the accumulation depends on how you position your panel. So the angular dependency also counts a lot. And when we move also to when we relate this angular dependency, so the higher you go, the lower losses you go. So when you position a panel in a vertical angle, definitely you will have less losses, but you can't just position a panel. You need to know where to position it properly. And if you position it at ultimate horizontal level, then the losses will be really extreme due to accumulation. And we try to look at, does it remain the same everywhere, considering environmental variation? Then we do the soil mapping there, where we consider weather and other things similar to that. And we see lots of variation in related to places due to optical losses that have been exposed in those regions. And here we will show you the map where we look first here. We picked up the two seasonal in Nigeria. This is the map of Nigeria. We took 2 seasons where we look at the dry and wet season and then try to determine where do we get more losses. And we found that they do really vary with location and with weather due to time. And the amount of deposition or amount of accumulation that causes losses to panel also varies with the time. And moving forward, I'm just rushing it due to the time factor. So moving forward, we look that there's lots of losses. We did a very similar parallel research in India as well, where we saw this variation of environmental factor also repeat and show itself. And then looking at the economical cost, it depends on the region and how much electricity cost per region. If you compare, let's say in this case where we compare India and the United Kingdom, where you're going to relate your losses, the cost of the money that you're going to lose when you have soiling effect on PV performance, it all depends on the region. Similarly, when you compare probably Saudi Arabia and United Kingdom and related with their cost of electricity. And then the natural phenomena which we cannot avoid at all, which is this something like dust haze, dust storm, which we typically see in Middle East, and here in the UK, we typically see things like snow, and them they do affect the performance of solar cell typically, and some of them will degrade the performance to a very minimal. In this case, we consider Nigeria, and we saw very, very, very typical losses of power output, which makes the percentage losses to be less than around 50%. And then when we consider also cloud shading, which is typical here in the UK, where we have clouding almost every day until during the summer period, we can see from morning till daybreak, we normally have a variation of power output. So when you expose this technology outdoor, definitely due to the irradiance available, the performance will really vary. So they are good technologies. We can see that several factors could stimulate alarming PV performance losses, and a very tiny minimum particle when dropped on the PV panel can affect its performance. But due to its economical and environmental merits of this PV technology, which we have here already, it shows that those technology are very good and can perform excellently when exposed. But we need to consider that we have no time. So as we are doing here in our ESI building in the solar energy group, we are trying to accelerate the integration of PV technology in all aspects, from building, roofs, glasses, glazing, everything, and all to the level of doing hydrogen technologies. We are all doing it here, and I think it's the best way we should explore to integrate clean technology and integrate it so we can promote the net zero agenda globally and protect our Earth. I would like to say thank you all for listening, and if there's any question, if there's time available from Anurag or the audience, then they can go ahead. And these are my sponsors mentioned here, and I'm working now under the EPRC project. Thank you so much all.
Thanks a lot, Yusuf. That's a wonderful presentation, and congratulations to you. If someone has any questions, please put on chat box. I can see there is one quick question as we have some time. Shantanu is asking that can decentralized solar module be alternative solutions? Yusuf, could you mind to answer it, please?
It can be the optimum solution. This is my own point of view. This is not a global point of view. It can be, but it's a very way forward where we can promote the integration to solve our imminent problem at the moment. We need to decentralize it and integrate it as much as we can. And we need to also develop a very larger, bigger farms globally to make sure we provide an alternative clean energy that we can all use globally, so we can reduce the carbon emission. That's our main problem.
Thanks, Yusuf. I have one quick question: that what is the current challenge you are facing?
The current challenge we are facing is the acceptance of the new technology. People are relating it to cost, which I don't think it is. People now usually install lots of glasses in their houses, and they pay here in the UK. They pay for people to come and clean it. But people are finding it difficult to install PV on their roof and to pay people to clean it. I can't understand why people decide to just pay for a plain glass, and they can't pay for a glass that will give them electricity and heat and reduce their energy consumption. So it's a very logical thing. If you can put up a glass which just have a little bit of tint, but it can also generate electricity, and you can control the light intensity if you want.
Yeah, that's a tricky one. Thank you so much, Yusuf. If someone has any questions, feel free to post it in the chat box or directly email to Yusuf. Hope he will happy to answer it. Let's move on to our next segment. The next speaker is Krishanu De from the University of Cambridge. Move on over to you, Krishanu. Hope you're online.
Yeah.
Yes, can you hear me?
Yeah. Yeah, I can hear you, and welcome to the conference. And please feel free to share your screen when you're ready.
Yes. Thank you so much, first of all, for the kind invitation. It's a very nice experience for me to be here with you all. Sorry I joined a bit late, but I'll straight away go to share my slides. Is it visible now?
Yes, it is visible. Yeah.
Is it the right screen or the opposite screen? Okay, I think
It is a split screen. Yes, it is now in full screen.
Okay, great. Okay, fantastic. Hello, everyone. My name is Krishanu De. I am almost finishing a PhD candidate at Cavendish Laboratory at the University of Cambridge. Today, I'm going to talk to you about a recent project that's accepted, which is basically on field-driven charge transport in mixed metal halide perovskite semiconductors. What's the current status of perovskite PV? So because this is a solar energy conference, so I thought it's mandatory for me to show it up as my first slide. So you could always see that there are technologies like silicon gallium arsenide, CIGS of various generations, which have now plateaued over the years in terms of efficiencies, and there are emerging PVs here, including organics, perovskite, quantum dots, and various tandem configurations involving those are rapidly rising in their efficiencies, especially the perovskites since its inception in 2009 has really been dominating the emerging PV research. The current certified single junction efficiencies are around 25.7%, whereas the efficiencies in tandem configuration with silicon have already reached beyond 30%. There's a very recent report on the news, in fact, saying that the all perovskite tandem efficiencies are also now close to 27%, which is a great achievement and something unprecedented in the PV research in the last many decades. So I'm going to talk to you today about a particular optoelectronic property of perovskites, which is very important to further drive up this kind of progress with these materials, and that's the charge transport. Now, charge transport in any semiconductor is quantified in various ways, but the most basic and the most fundamental parameter that quantifies the charge transport is the mobility. And basically here in this chart, I'm showing you different compositions that have been explored for quantifying mobilities using various different techniques. So you could see there are some optical non-contact based techniques like terahertz time of flight or even microwave conductivities, which give you ensemble mobility of carriers, including holes and electrons both. And then there are also some electrical contact-based methods like space charge limited current, Hall measurements, and field effect approach. You can always see that the field effect approach is relatively less explored, so there are less data points here, which is why we wanted to study this approach. And to be honest, that's this approach of field effect is not a new approach. This was the first paper using perovskite in field effect transistors. You can see this is 1999, so about 10 years before the first perovskite solar cell paper came out. So this is a very old technology, but somehow didn't really gain momentum as the solar cell and LED field did from 2009. So here in this particular work, we chose a bottom gate and bottom contact architecture of field effect transistor. So just for the people in the audience who are not aware about the field effect transistor, so instead of solar cell, which is a two-terminal device, field effect transistors are three-terminal device. So you have the gate terminal here, you have the source and the drain terminals here. So applying voltage at the gate terminal will induce carriers or a channel of carriers at the semiconductor dielectric interface here. And then you can modulate the conductivity of this channel by applying another voltage at the drain terminal with respect to the source terminal. And the semiconductor here is the perovskite. And in particular here is this mixed lead tin perovskites. Now, these mixed lead tin perovskites are interesting materials because you could lower the band gap of perovskites down to about 1.2 electron volt, which is not possible with traditional lead halide perovskites. So that's why these kind of mixed lead tin compositions are becoming more and more popular for all perovskite tandem applications. And the charge transfer properties of these materials were quite unknown before this study. So that's why we chose to take these materials up for this particular study. Now in a transistor, you have these two traditional characteristic curves. So the left one is called the output characteristics, where you sweep the drain source voltage and you measure the change in the drain source current. And here, this is called the transfer characteristics, where you sweep the gate source voltage and measure the change in the drain source current. And from these two curves, you could find out all the different parameters that are important for a field effect transistor, including mobility, which is the more important one, but then also on-off ratios, threshold voltage, subthreshold swing, and many others. But why did the perovskites didn't really pick up in transistors? So the 3D perovskite, as you know, is the more versatile form of perovskite, and this is what has pushed the efficiencies of solar cells and LEDs further. But these 3D perovskites have an issue of ionic migration. So what happens is that when you apply a voltage at the gate terminal, you would want to attract the oppositely charged carriers at the semiconductor dielectric interface. But because the ions can also move there, so they can also come and accumulate over here, and therefore they can screen some of this applied gate potential. And therefore, the modulation of carriers of the channel from the gate reduces, and that's why there is a reduction in mobility, especially near room temperature, which you can see more and more clearly as you go down in the carrier in the perovskite concentration, i.e., the grain size reduces. So there you have more pathways of ion transport, and therefore you have much more significant reduction in mobility near room temperature. So here, let's start with the results. So for the lead perovskite, so we started with the lead perovskite first. So you can see for a pure lead perovskite, the drain current increases as you sweep the voltage in the positive direction. So that tells you that this is a typical N-type transport, and the maximum mobility achieved is 10 to the power minus 3. Remember, these field effect transistors are devices that measure long range mobility. So these are not really like terahertz measurements, which measure local range mobility. So they are really affected by several factors. Also, the field effect transistors can really tell you if those carriers that are moving are electrons or holes, just from the fact that the drain current changes when the gate voltage is changing in the positive direction. That tells you that it's an N-type transport. So these are electrons that we are probing. But we see that the opposite trend begins to appear as you introduce some tin in there. So as soon as you put some tin in there, you completely reverse this trend. And now what you have is that you have a P-type transport, and from these curves, you can find the mobilities. And we see that the mobilities increase consistently as you introduce more and more tin in the mixture. We obtain a maximum hole mobility of 5.4 centimeters square per volt second for the optimum composition of 50-50 lead tin, with almost hysteresis-free output characteristics. And people aware about perovskites would already know that hysteresis is a good indication of ionic migration. So that was a smoking gun for us to probe the ionic transport in these devices further as well. But before that, just to understand why the mobility goes up with tin, so we measured the scanning electron microscopy images for these different lead tin films, and you could see that the grain sizes increase significantly and consistently with the amount of tin you have in the mixture. And because FETs, as I said, measure the long range mobility, so they are really affected by the grain boundaries. So you have less and less grain boundaries as you have more and more tin, therefore you would have higher mobility. This is also consistent with some theoretical calculations, which I'm not showing here, that says that addition of tin reduces the effective mass of carriers, and thereby you would have higher mobilities. We also wanted to probe the tin 4+ defects in this film. So basically, tin perovskites are really quite unique in the sense that you have the two oxidation states of tin in there, so the tin 2 and tin 4. This is not the case for lead perovskites, where tin lead 2+ is the stable oxidation state. So you always have this problem of some tin getting oxidized to tin 4+, even in very, very pure conditions where you have very little oxygen in there. So we wanted to probe, what about our films? Did it have any tin 4+? And it turns out that all of our films, irrespective of what is the lead and tin ratios, had two peaks that you could easily assign to lead tin 2+ or tin 4+. And then we basically plot here the ratio of tin 4 over tin 2. And we find that this ratio is kind of related positively correlated with the Urbach energies that you obtain from these films. And Urbach energy is a nice measure which tells you about the defects in this film. So this suggests that the tin 4+ is indeed a defect, major source of defect in this mixed lead tin perovskites, and our optimum composition of 50-50 lead tin indeed has the lowest amount of tin 4+. But even if these tin 4+ is increasing beyond 50%, we don't necessarily see a reduction in the PL. So the traditional conclusion would be that the higher the defects, lower the PL intensity, but we don't really see that here. So the PL intensity consistently goes up as the tin4 also goes up, and that's probably because these mixed lead tin perovskite are highly doped perovskites. So this is again the difference between the lead and the tin-based perovskites. Lead perovskites are almost undoped, whereas the tin perovskites are positively whole doped or p-doped, and thereby the recombination, the radiative recombination in these materials is not only a function of defects, but also is a function of doping, and this makes these materials quite unique. But we wanted to understand what happens, as I said, to the ionic transport. So one way to probe the ionic transport is to measure the temperature dependent on the mobilities. So you can see for the lead-based perovskites, we see the usual negative temperature coefficient, as I showed to you before as well, where near the room temperature, the mobility goes down. And that's possibly because of the carrier, so the ions getting accumulated near the interface, and they screen the potential and thereby reduce the mobilities. But we find that as soon as you introduce some tin in there, we again reverse this trend. So you now see a positive temperature coefficient of mobilities, which is free of such ionic screening dominated reduction. And this kind of positive trend tells you about an activated behavior signifying hopping transport in these materials. And if we fit this using a traditional Arrhenius equation, we find that the activation energy for our champion composition is very low, 48 milli-electron volt, which tells you that the electronic defects are quite shallow in these materials. And one of the sources of electronic defects in these mixed lead tin perovskites are tin vacancies that is known to give rise to this doping, as I mentioned, in these materials. And therefore, this shows that the field effect transistor is a very nice platform also to study defect physics, as well as the effect of ionic transport in materials, which are also relevant for solar cell applications. We find that if you now, instead of having cesium Fa in the A site, if you now have an MaFa, so this methyl ammonium from a metanium composition, you see that there is a change in the trend from being a positive temperature coefficient that we saw before, but now it reduces, the mobility reduces here. So there is a now transition to a negative temperature coefficient. And this transition point basically goes down to lower temperature as you have more and more methyl ammonium in the mixture. That tells you that this reduction is related to the methyl ammonium. And from the literature, it turns out that indeed the methyl ammonium does have this dipolar disorder, which is also known to affect the mobilities, field effect mobilities even in the lead-based devices. So we see the same effect even in the lead tin devices. So our idea is that in future, this is cesium Fa-based compositions are relatively more immune to such ionic screening effects and also dipolar disorder effects. We also wanted to see if the transition temperature here is related to any phase transition or not. So we did some temperature dependent X-ray diffraction measurements on our optimum FACS films. And we find that between this range of 122 Kelvin to 182 Kelvin, there is possibly a phase transition region that's there, but we don't necessarily see a phase transition as smooth, as sharp as you see in a single crystal samples, because these are polycrystalline and quite complex in their composition as well. So we don't see a very sharp transition. Instead, it's smeared out. But indeed, in this region, there seems to be something happening in the structure, which seems to correlate well with our with the mobility trend here as well. So, but again, there has to be more studies done here to conclusively establish any trend that we see here between the structure and the transport. Finally, wanted to see if this ionic transport behavior that I mentioned to you before can be visualized as well. So here, this is a lateral device, so no gate terminal here. So this is just a lateral device with perovskite here. This is a lead perovskite. So what we do is that we measure a PL map first, and then we apply a pulse voltage for a few seconds, and we do it for multiple cycles, and we try and see how the intensity in the channel evolves. And we find that as soon as you apply some voltage, there is some change in the PL intensity here. It starts from the positive electrode, near the positive electrode, and then it percolates across the channel, and the intensity also goes down. And this is a very nice indication of ions moving, likely halides, because it starts because the reduction of PL starts from near the positive electrode, where you would assume a lot of iodides would move and accumulate. And these iodide interstitials are known to be deep traps, and they can really affect your additive recombination, and thereby you see that the PL intensity goes down. And finally, I'm just about to finish in a minute. You see that the trend of this continuous evolution of PL is not the case for the biotin and the mixed lectin, where there's something happening after first biaging cycle, but beyond that, there seems to be relative immunity to such changes, which tells you that the ionic migration effects in these lateral devices are also minimized with the introduction of tin. There indeed appears to be something happening at the negative electrodes, which is reversible, and we attribute this to a reversible electrochemical reduction of tin 4+ over tin 2+. And because tin 4+ is known to be a defect, so reduction of that would lead to an increased PL from the negative electrode, and which you don't see anything like that in the lead perovskite, because lead 4 doesn't exist. And this is the mechanism. So finally, we say that in a lead perovskite device, you have an N-type transport, as I showed to you. So the iodides would like to accumulate near the channel, but here for the mixed lectin devices, it's the P-type transport. So you don't necessarily have iodides, but you can have these positively charged A and B side cations, which can, in principle, can also screen, but we think they can form neutral defects with this negatively charged tin vacancies, which I mentioned before are responsible for hole doping these materials. And finally, also find that beyond the influence of the gate as well, even in the in-plane direction, we find that the ionic migration in these devices is much more suppressed. And also because the fact that we don't have any methyl ammonium in our optimum composition, we also don't see any dipolar disorder induced lowering in mobilities. With this, I come to the conclusion. So here we systematically study the field effect charge transport of mixed lectin perovskite films for the first time. We obtain a record high hole mobility of 5.4 centimeters square per volt second. We also obtain a temperature activated FAT transport for the first time in 3D hybrid perovskites. And also we see that the ionic migration effects in the in-plane direction at least are significantly suppressed in the mixed lectin systems as compared to lead systems. With this, I would like to thank all my collaborators, my PIs, especially Satyaprasad Senanayak, who led the project alongside me, and all my funding agencies, and finally to you all for your attention. Thank you so much.
Thanks, Krishan. A wonderful talk, and thanks for joining us. It's interesting, topic. I can't see any questions for you at this moment, but I have a few questions for you. But as the time we are running out, I may contact you in person later. So thanks for joining, and we can move to our next speaker, Dr. Priyobroto Shaduka. He's a postdoctoral researcher from Yonsei University, South Korea. So I think Priyobroto is on board. So over to you, Priyobroto.
Thank you, Dr. Roy, for inviting me to this conference. I'm very delighted. So I'm going to start the presentation now. Please let me know if this is visible to you. Okay, so is it visible?
It is visible, and can you go for this?
Yeah.
Okay. Slide. Cool. All okay. Please go ahead and try to keep in mind 15 minutes. Okay. Yeah. Thank you.
Thank you. Yeah. So thank you everyone for attending this conference. Good afternoon. I am Dr. Priyobroto Shaduka from India. I'm a postdoctoral researcher working at Department of Material Science and Engineering at Yonsei University, South Korea. So the topic of my today's talk is ionic liquid for perovskite light emitting diodes. And my topic is a little bit different from the theme of this conference. Most of the people are working on solar energy harvesting and their conservation. But my topic is different, but still LED or the light emitting diode, they are not out of the league because light emitting diodes are still relevant for sustainable living because if you look at this figure, you see that if we can replace 8,000 street lights with light emitting diodes or LEDs, then we can cut down the carbon emission by 15,000 tons per year, which is equivalent to the car emission of 8,000 cars. So the numbers are huge. So in this way, light emitting diodes or LEDs can actually reduce the carbon emission in the air. And if we can keep on using LEDs for another 8 years, by 2030, we'll be able to remove about 1.4 billion tons of carbon dioxide from the air. So that's a huge number. So even though light emitting diodes is not harvesting the solar energy, it can actually conserve solar energy in other forms. So light emitting diodes have different applications, and it is nothing but a normal PN junction diode, just like a solar cell. However, it works in a different way. It consumes electricity and emits photon, which can be used for different applications like normal lighting, display technologies, or communications. Perovskite materials, they are already very renowned for every other kind of semiconductor device. And they are now also very good for light emitting diodes also, especially for lighting and display technologies. Now, as my topic is different, so before going into the details, I just go through the figure of merits of an LED. So the first one is the luminance. This is the brightness of a LED. So higher the luminance is always better. Second one is the quantum efficiency. That means how efficient it is, how many number of photons we can extract from the device or single electron fed into it. The third quality is the switching speed. That means how fast it can switch between on and on stage. This is particularly helpful for communication devices. And the fourth one is the color purity. This is very important, especially for display applications. I think many of you already know that these displays, these laptop or mobile displays are made of 3 different pixels, red, green, and blue. And the quality of the color or the brightness or saturation level of the color depends on the EL spectra of that individual pixels. You can see here, this is the EL spectra of a LG OLED display. The spectras are not very thin. That means their FWHM is very high and they're actually overlapping. Still, OLED displays are much better than LCDs. You can see from these CIE color coordinates. OLED displays can cover up to 90% of NTC standard. But perovskite materials has a very sharp emission peak with a WHM of the order of 80 nanometer only, which is much shorter than OLED displays. So if we can make perovskite displays, then it will actually cover about 140% of NTC standard. So that will be the best quality display ever built. But still, perovskite LEDs are not in the market. Because the first problem is quite genetic, like all other perovskite materials, they are having low operational stability. So PE LEDs or perovskite LEDs can work only for a few minutes to few hundred hours, so which is much below than the commercial standard, which is about 10,000 hours. And the second problem is the luminance and the EQE of these perovskite LEDs are still quite below OLEDs. If you look at this figure, there is about 2 order of magnitude difference in the maximum luminance from PLED in comparison to the OLED, let alone the group 3,4,3,5 semiconductors. Another big problem is the shift of spectra. So when we turn on the LED, it gives some emission, and over time and under biasing condition, the EL spectra will shift towards red or blue, depending on the anionic condition or ionic condition of the perovskite. And this is especially for mixed ion perovskites. That's because of the redistribution of the ions across the perovskite layer. And another big problem is the efficiency roll-up. That is, the EQE goes down at higher injection current intensity. But for a higher luminance, we need higher injection current. But at that time, the EQE goes down, so the luminance goes down. So there is the kind of trade-off. And these are the 4 or 5 big problems with the perovskite LEDs right now. And that can be solved in different ways. Like there is a possible solutions. Unlike solar cells, in perovskite LEDs, we need a very high excitonic binding energy in the perovskite material, so that there is no premature recombination of the electron and holes. For that, we need to specially confine the electron and holes in small perovskite grains. As you can see in these 2 figures, if we have a perovskite layer with a very big grain like 500 nanometers, the emission from the LED is very weak. But when we reduce the grain size, we are getting much brighter emission. So that's how we can increase the emission. And it also helps to inhibit the ion migration, because if we reduce the grain size, then ions have much lesser space to move around. So the ion migration will be much restricted. We also need to precipitate the surface defects, just like perovskite solar cells. And this can be done by using different ligands, mostly the long chain organic ligands like PABR, PFMBR, all of these things. Especially PABR is very popular because it works very good. However, the problem with these ligands is that they're kind of insulating in nature. So if you use too much ligand, they will make an insulating layer around the perovskite grains. So it will actually disrupt the electrical connection between the perovskite layer and the adjacent transport layer. Or sometimes in the inter-grain connection is also disrupted. So here my idea is to use ionic liquids, because ionic liquids are not something new. They are already being used for perovskite solar cells, but not much explored in perovskite LEDs. Ionic liquids have some very nice property, like they are very difficult to evaporate. So they can actually control the formation of the film, perovskite film, by controlling their growth rate. And these ion liquids are in room temperature, they are like molten salt. So the free ions are moving around, so they can also give some kind of conductivity, unlike the long chain organic ligands. And they are very low toxic, and they can also precipitate the perovskite sulfate defects, which is already been explored in perovskite solar cells. So here I have used this ionic liquid, that is 1-butyl 3-methyl imidazolium hexafluorophosphate ion liquid for my purpose. Here in this ion liquids, the BMIM plus ion works as the cation, and P6 minus it works as the anion, and it helps to increase the performance of my device, which we will be speaking just after some time. So to form the perovskite film, I first prepared the perovskite precursor using CSP BRC for green emission, and I dissolved this CSP BRC in DMSO, then added the additives like PABR and IL. I've used PABR here as a reference because PABR is already very known and it also works good. So if you look at this ACM image at only IL at 30%, the film quality doesn't look good. The perovskite grains are very big, and the surface coverage is also not good. There is so many voids. And when I use only PABR at 40% rate, the crystals, the grain size is very small. However, the shape is not uniform. Also, we see that there is some agglomeration of crystallites, which is also not good for that device. In the third case, I added 10% IL with 40% PABR, and we see that the perovskite crystallites, they are taking some kind of symmetric structure. If you look at the zoomed image, that the perovskite crystallites are now looking like a perovskite nanocrystal with a cubic structure. So this is better, and there is some kind of homogeneity in their size. And we also see that there is some semi-transparent capping around the perovskite nanocrystals, which is the IL. If you look at this TM image and corresponding EDS image, that layer, that is the green part, is the perovskite grains, and the fluorine, which is coming from the ionic liquid, which is wrapping the perovskite grains from outside, like from the grain boundaries. So it turns out like the ionic liquid are capping the perovskite grains from the outside, and in this way it can control the growth of the perovskite crystals, as well as it can also precipitate the surface defects. Now, using this thing, I have postulated the growth of the perovskite film in presence of ionic liquid. Here I have used P.PSS coated substrate, because P.PSS is used as the whole transport layer in my devices. So then I coated ionic liquid, perovskite, and PABR precursor solution on that. And when I turn on the heater for annealing, the perovskite crystallize starts growing. But this ionic liquid, it doesn't react with the perovskite, and it also doesn't evaporate. So when the crystal starts growing, it just rejects the ionic liquid, and that ionic liquid accumulates around the perovskite crystals. And it then starts to regulate the growth of the crystallite size. And in this way, it allows for formation of a huge number of perovskite nanocrystals, which makes a very compact film with a more or less symmetric structure. Now let's go to the performance of the device. Here is the PLD device, the structure of the PLD device that I made. Here, P.PSS works as the whole transport layer, and at the bottom I have IUTO coated glass. And ETL is a TPBI layer. I have used PMA for balancing the electron injection in the perovskite layer. Here is the cross-section image of the device. Now, if you look at these two images, you see that there is a huge difference in the performance. This one is our reference device with 40% PABR, and the second one is our champion device with 40% PABR with 10% ionic liquid. And visibly, you can see that there is a huge improvement in the luminescence intensity, which is also reflected in this luminance versus voltage curve. you can see that the PABR-only device, that is the blue curve, it gets about 10 to the power 4 candela per meter square. But when I added iron liquid in it, the maximum luminance I've got for 10% iron liquid is 1.53 into 10 to the power 5 candela per meter square. So that is very, very good. And it's also huge compared to the other reports at the current time.
Sorry to interrupt you, Broto. You have 2 more minutes. Please try to wrap up.
Okay.
Sorry.
Okay, so I'll try to do it fast. And if you look at the current values, you see that current is much lower for PABR and 10% IL only. And using this high luminance with low current values, we have got a very good EQ, and that is 15.04%. This is not the best, but good one with this luminance level. And in the EL performance, I've seen that FWHM has reduced much after using IL, and this FWHM is very important for the purity of the color. You can see it here that the my modified device with ionic liquid is 134% of NTSC color gamut, while the reference one is 117% of NTSC's color gamut. So there is a huge improvement in the purity of the color. I've also seen the stability is also improved after adding ionic liquid. And this approach works well with high surface area devices. And I'm also trying the same thing with blue LEDs. This is cyan, and this one is the pure blue LEDs. And I measured the PL and FTR. From there, I could say that the ionic is actually very good for classifying the defects, and it also makes some kind of interaction with the uncoordinated lead ions. So in this way, it can precipitate the defects. Actually, due to the time restriction, I'm not going into the details. So the conclusion is that iron liquid can be a very good additive and can be a very good alternative to normal long chain ligands for defect classification, as well as controlling the crystal growth. And it can also change the band energy for better alignment with the other electrode layers for efficient charge injection. This is what I have to say for this topic. And thank you very much for attending this conference. I now welcome any questions if you have.
Thank you, Priyabroto, and sorry to interrupt you because time is important for us to run the whole conference as we are dealing with the international delegates as well. Thank you for joining us, and please stay online and rest of this session. Thank you. We have Somdeep now on board. Just let you know, Somdeep has a serious car accident yesterday, and I think he's on rest. Thank you so much, Somdeep, to join us. As I can see, you have a serious injury. I hope so. And as you say, show must go on. So thanks for joining us. And just don't give you lots of stress. You can finish your talk in 10 minutes if you want. And because the time schedule is so tight for us. So yeah, that's it. So Somdeep, he's assistant lecturer from University of Essex, UK, and also a member of Forbes Technologies Council and TEDx, and a fellow of the Royal Society of Arts. Over to you, Somdeep.
Thank you so much, Anuragda, and thank you so much for having me here. Although we are in a solar energy conference, but my research is in using embedded reinforcement learning to make smartphone more energy efficient. So it's definitely in the line with the conference itself. So already Anurag has introduced me to this conference and the people. So I'm going to skip over who I am and what I've done. But that being said, let's get into the main topic. So there are more than 6 billion smartphone users worldwide. And one of the biggest constraint or objective is because there are so many smartphone users, smartphone has become an integral part of our daily lives. We use smartphone for all the daily needs digitally, meaning that we use smartphone from our social media usage to even productivity as well as entertainment purposes as well. So optimizing the power consumption of smartphone can contribute towards the net zero emission goals altogether. So when I say that we need to optimize the power consumption of smartphone, it does not just mean that we have to compromise the performance when we use a smartphone itself. So the modern smartphone come equipped with the hardware that enables us to do much more. The modern smartphone is equipped with multiprocessor system on chip, which means that on the right-hand side, as you can see, that it comes with different type of processing element, big CPUs, little CPUs, GPU, NPU, which are neural processing unit, DSPs. So all these different type of processing unit that come embedded in the smartphone, these are capable of running at different operating frequencies. And because we have so many different processing element, we are capable of using the same smartphone for our entertainment purposes. For example, we can watch Netflix on it, or play games on it, or we can even use apps such as Excel on the same smartphone. But that being said, because of the different processing frequencies on the processing elements, we need to keep in mind that if a processing element run at a higher frequency, it consumes more power and also dissipates more temperature on the device. So if we are able to optimize the operating frequency of the different processing element, it means that we are capable of reducing or optimizing the power consumption on the device itself. Now, my research specifically focuses on embedded machine learning, and many people have a question that, okay, what is embedded machine learning and how is it different from normal machine learning? Embedded machine learning is a subfield of machine learning where the machine learning model runs on embedded system with limited computing resources, which are very different if we have run the machine learning model on normal computing devices such as our laptop or general purpose computers such as desktop or servers. Now, one of the biggest issues that people have is privacy and security concerns related to data and how machine learning is being trained on those data. So because privacy and security is a big concern, and embedded machine learning models, they are trained and also inferred on the embedded system itself, separate to running on or training on a server. That's why embedded machine learning is more suitable, because it's completely offloaded on the user devices itself. Now that we have talked about embedded machine learning and how it might be different from normal machine learning model, let's just quickly review the reinforcement learning that is one of a very popular model that is currently used as an embedded machine learning model itself. Because reinforcement learning, it's a software agent that runs on the user's device and is capable of taking action so that it can learn from the action what are the best action it could take on the device, and from there it optimizes its own action behavior on the device itself. Now, few of the observation that we have learned, we as users, when we interact with the smartphone devices, whenever we interact, we trigger an action or function on the device itself, and the application that is being run in the background or in forefront, based on how we are interacting, it understand that what actions need to be taken next. And when I say action, it means a programmatic function is running in the background. Then the smartphone device updates the view based on the particular action that we take, such as we are scrolling through our smartphone. It understands that the smartphone has to update the view based on how we are scrolling, either up or down. And then it updates the view back to the user so that the user can see, okay, what is the next scene that we could get from the smartphone. And the other observation that we have understood is that even if we are using different apps on the device, that does not always mean that a higher operating frequency on the hardware side can always translate back to a higher FPS. So we can use machine learning model to optimize what's the best operating frequency to choose, so that we can optimize the power as well as the performance on the device itself. Now, the method that we have created at the University of Essex, we call it the NEXT method. What it does, it's a reinforcement learning agent, which is basically a software running on the device, and every 25 milliseconds, it understands that what is the frame rate that is being generated while a user is interacting with the device itself. And based on that, the software agent, which is NEXT, it calculates the mode of the frame rate. In that way, it understands, okay, if the frame rate is, for example, 60 FPS, it then chooses what's the best operating system of the different processing element that it can run on the hardware side, so that it is capable of generating that 60 FPS frame rate itself. And that being said, when we implemented the NEXT agent on real hardware device, especially we use Samsung Note to run our experiments, we noticed that for different types of applications, from gaming such as PUBG to entertainment or web browsing, we are capable of reducing the power consumption up to 40%. And as I have mentioned earlier, that when we are optimizing the power consumption, it's not just the power consumption that is being optimized, because power is also connected with the thermal behavior of the hardware device itself. We are also capable of reducing the peak temperature of the device by 29%. If you are interested in learning a bit more about our research, you can go to my Google Scholar page, or you can reach out to me via email, and I would love to connect with you. And I'm always open for collaboration. Thank you.
Yeah, thank you, Somdeep. Lovely to see you, and please take care of yourself. We have a question, but Today you are relieved. Yeah, please take care. And thanks for joining. And okay, can I ask questions if you're available?
Absolutely, Anuragda.
I know you have. Okay, one quick question from Shantanu, that what is the minimum requirement on a cell phone for such ML training?
There is no minimum requirement. That's why one of the best reason of using reinforcement learning is, although when we use reinforcement learning on general purpose computer and on, let's say, smartphone devices, which are embedded system, the only difference is that for convergence, which means to find the most optimized result, it might take longer time on a cell phone or a smartphone. But when it comes to general purpose computer, the reinforcement learning, because of the more computing resources available on general purpose computer, it can reach the optimized result much faster, which means it can converge to the optimized result much faster. So when it comes to smartphone devices, in order for it to optimize correctly, it might take a bit longer to find those optimized results so that it can learn properly. And that being said, what we have found out, usually, let's say, if we are running entertainment apps, or if we are interacting with the device much more frequently, then the session for the reinforcement learning to learn might be a bit more than 5 minutes. But again, once it learns, it already knows what are the best operating frequency to choose. And in that way, if you just don't care that it does not optimize the power or thermal behavior on the device faster than 5 minutes, then you are absolutely fine with that.
Cool. Thank you very much, Somdeep. Anyone has any questions? I think you should take care of yourself, and thanks for joining. Thanks. That's so kind. Thank you. And okay, so we are now ready for the quiz. So there is 15 questions, and that's energy related quiz competitions. You can see the quiz link has been shared in your Zoom chat box. Please click on the link. It's a Microsoft form. You have to fill out the form, and you have 15 minutes time to fill out those forms. Right now, we in UK, the time is 14:07 p.m. So we will take all the answers up to 20 minutes. So we will stop 14:25. So every answer should be submitted, and fastest finger first. The winner, who will be the highest scorer, we will declare at the end of today's session. So you can see the chat. Now you can see the quiz link in the chat. In the meantime, I will share all the questions, but you have to answer using the form. If you have any questions, just let us know. Please go for the quiz. There is a chance of winning Amazon gift voucher, and please join us in the quiz. The chat, the quiz link has been shared in the chat box. Please go, click, and automatically submit the answers so that you have 15 minutes try to finish the quiz as soon as possible. Thank you. Shomdeep, could you mind to hello?
Yes.
No, thank you. Thank you. No, thanks. No problem. Sorry. So as I mentioned, you have 15 minutes. Please try to answer all the questions. The quiz link questions has been shared in your chat box. There is a chance of winning Amazon gift voucher. So please answer us as soon as possible.
Open your that form where you are getting answer in the chat. No, let them answer. Just announce.
Please don't answer in the chat. There is a quiz form. Please submit your answer using the Microsoft form. Thank you. The first question you can see, which one is not considered as United Nations Sustainable Development Goals. You have 4 options. You can see the similar questions in your Microsoft form. The answer only acceptable if you fill out the form. Any chat response will not considered for this quiz. So please see the link. It is already shared in the chat box and answer there. Question number 2, you can see fill in the blank. Leaving a computer on overnight for a year creates enough CO2 to fill. So there is 4 options. So option A, the entire Vatican City. Option B, a double-decker bus. Option C, a spacecraft. Option D, half of Mariana Trench. So which is the correct answer that you have to fill out using the Microsoft form link, which is already shared in the chat box. Please don't reply any answer to the Zoom chat box. No answer will be accepted.
Just
Question number 3, you can see in the picture, a new type of solar cells material can be formed from this brown portion. You can see the arrow mark, red arrow mark. It is usually found in ocean and aquarium plants. What material it is? You have 4 options. Option A, a pigment. Option B, a perovskite material. Option C, an algae. Option D, an iron complex. You can see the similar question in the Zoom chat box. Please use the Microsoft form to fill out the correct answer. All answers, all quiz questions, answers can be submitted using the form only. So please answer using the form, not in the Zoom chat box. I'm repeating all the time. We have shared the quiz link in the Zoom chat box using that Microsoft form link. Please answer all the quiz questions. There is 15 minutes time. We will stop at around 14:25 UK time. So you have still 12 minutes left to complete. So please do as soon as possible. You can see question number 4 in your Microsoft form also, that which 2 facts are usually consumed similar energy? Option A, 6 hours laptop using. Option B, overnight cell phone charging. Option C, Making a coffee in a coffee shop. Option D, 3 hours session in a beauty spa. Please answer using the Microsoft form. We will declare the winner after today's session at the end of the conference, today's session. So please try to answer as soon as possible. And maybe you have a chance to win an Amazon gift voucher. So go ahead. You can see question number 5, which food processing is producing less carbon emission? Option A, dark chocolate. Option B, shrimp. Option C, sunflower oil. Option D, milk. Go to the Microsoft quiz form, which is already shared in the chat box. Just simply click, answer all the questions as short as you can. There is a chance to win Amazon gift voucher, so please. You can see question number 6. Which of the following places or place has warmed the most over last 100 years? You have option Maracay, Morocco, Basra, Iraq, Vancouver, Canada, Sigurd, Norway. Please type your answer in the Microsoft form. The quiz form already shared in the Zoom chat box. Please check your chat box, go to the link, simply click and answer all the questions. So we have 8 minutes remaining. We will stop after 8 minutes taking all the questions, so do it fast. Question number 7. Which of the following option is not an energy efficient strategy? Option A, daylight. Option B, occasional use. Option C, maintenance. Option D, design. I again repeat, there is a quiz link already shared in the Zoom chat box. Simply click on the link and try to answer all the questions. We have 7 minutes remaining. Question 8. Which energy company is the official global partner of upcoming FIFA World Cup 2022? It's not upcoming, it's running now. So the option A is Aramco Saudi. Option B, Shell. Option C, Qatar Energy. Option D, Tesla. You have 6 minutes remaining to answer. We will announce the winner after today's conference closing time. So please stay with us that who will be the winner and have a chance to win some Amazon gift voucher. Okay, moving on to the next question. You can see there is a 2 picture, A and B. You have to answer what is A, what is B. There is a 4 options. So which option is correct? That you have to answer. What exactly this picture is actually? 6 minutes remaining. So please go to the link and try to submit your answer. We will take the answer up to another 6 minutes only. Question number 10, you can see a periodic table marking with some red circle. You have to answer that in which European country these lanthanide elements were discovered. Slovenia, Sweden, Ukraine, Denmark. Five more minutes remaining. So we will stop taking all the answer and we will move to our comfort break after that. But just within 5 minutes, please try to answer it. I will disclose all the answer after the 5 minutes. So please stay with us and try to fill out the quiz form as soon as possible. Question number 11, it's filling the blanks. Interestingly, as World War II was drawing to close and X, that is the scientist's name, was attempting to develop energy sources for radar equipment, and accidentally he discovered something. So what's that accidental discover? It's a power bank, it's a motherboard, is it a microwave or an electric cooker? That you have to answer. 4 minutes remaining, please go ahead. Question number 12, you can see a camera picture and there is a perovskite structure. You have to answer, a perovskite material's property depends on dash, depends on Planck. The term was originated from this type of camera. What is the exact name of that camera? Is it a point camera, pinhole camera, bridge camera, and a hybrid camera? The term is associated with a defect related to a perovskite crystal. 4 minutes, sorry, 3 minutes remaining. So please go ahead. Question number 13. You can see one picture. This picture is the head office of a battery related field. Where is this office? You have to answer. So is it an International Electrochemical Commission? It's a IUPAC office. It's a United Nations Climate Sector head office, or International Battery and Power Storage Commission head office. I can give you a hint that it's related to battery and its naming. So yeah, go ahead. 2 more minutes remaining. So please try to answer as soon as possible. What's the general similarity among the following species? You can see 3 species naming koala, ridge sail, and a bramble cave mammalies. If it's quite interesting. These 3 species name has been disclosed in just last COP27. So if you're following the climate change news and all, it is easier for you. So let's go ahead. We have 3 more minutes remaining. So please go to the Microsoft link. We will accept all the answer up to just 3 minutes. Yeah. Last question you can see in your form as well. It's a puzzle. So find out any 3 energy associated words. So you can have to select the 3 words from these puzzles. So which 3 words are actually inside the puzzles that you have to pick up? I know that's a tricky one, but easy one. Just go ahead. We have 2 more minutes remaining. So please try to submit your answer as soon as possible. We will close the quiz and we will declare the winners after the session, today's session, during our closing remarks. So please try to answer. One more. Yeah, we have 1 more minute remaining. So I will stop all the questions. Please submit your answer. We will take answer only for 1 more minute and we will stop taking any answer. Any submission after 1 more minute, after 1 minute, we will not consider for this quiz. We will declare the winner during the closing remarks. Okay, so we will stop the quiz right now. So we have received many responses. We need to decide the winner now. And before that, let's have a quick look at the answers. Just a minute. Yeah, so we are almost ready with the answer. Please stop submitting the form now. The quiz has been closed. And let's have a quick release the answer. What is the correct answer? Hope somebody has win. Yeah, just go to the answers. So ready with, you're excited to know the answers, right? I hope there is automatic answer responding so you know what is your score, but still for everyone, just have a look at the correct answers. So yeah, the question one was which one is not considered as UN Sustainable Development Goals? And the correct answer is option D, Sustainable Gross Domestic Product. Going to question number 2, that leaving a computer on overnight for a year creates enough CO2 to fill. The answer is a double-decker bus. So hope those who have given the correct answer get 10 points. Question 3, that's a diatom algae. You can see it's a new type of solar cells called diatom solar cells based on algae. So the brown color, you can see that's a form of algae. Question 4, which two facts are usually consume similar energy? So that's the 6 hours laptop using, including making a coffee in a coffee shop. So both have consumed the similar energy. Question 5, which food processing is producing less carbon emission? The correct answer is milk. Question 6, which of the following places or place has the worms the most over the past 100 years? That's Norway, because the Norway's summer temperature was -30, and last 100 years it increases to -2. So taking in terms of its negative or the minus temperature increment as it's a warm place. Question 7, which of the following option is not an energy efficient strategy? The correct answer is occasional use. Question 8, which energy company is the official global partner of upcoming FIFA World Cup? The correct answer is Qatar Energy. I think that's the easiest question. Moving on to question 9, the correct answer is a human eye and nebula. So both are looking comparatively similar structures, and that's the effect of a material science. Question 10 is actually the answer is Sweden. If you go through the letters Y, TB, the element, the symbols, yttrium, terbium, so all basically some Sweden-based city names. Question 11, the correct answer is microwave, and the scientist's name was Percy Spencer, who discovered microwave accidentally. Question 12 is the correct answer is pinhole. So this is called a pinhole defect available, or we can see in the perovskite crystals, and the term is actually coming from a camera. Question 13, the correct answer is International Electrochemical Commission, which is situated at Switzerland, Geneva. So, and they have actually nomenclated the A, AAA, AA, all these categories of battery nomenclature. Question 14 is what is the general similarity? The correct answer is option D. All have become extinct species due to climate change. Only 1 or 2 number of these species are right now having with us, and we will lose them shortly, unfortunately. Last question, question 5, you can see it was a puzzle, and there is a few terms that you have to find out, and all are related to energy and science. So the correct answer is option C, that's a capacitor, radiant, and hydropower. I have mentioned that what was the correct word, so it was gambling between these correct words and so on. So yes, here is the quiz, and we will reveal we will announce the the winner during the closing remarks, which is scheduled at 15:55 UK time. So please stay with us. We will stop here for a 10 minutes comfort break. Again, please grab a coffee or take some, a rest, 10 minutes break. We will be right back after 10 minutes. So stay with us. Thank you. Okay, welcome back everyone, and thanks for your all responses. We have received a lot of responses and we are struggling to deal with the scores and with the time. So we will declare the winner during our closing remark sessions of today. But before that, right now we have the industrial speakers, and our first industry talk, we will be hearing from Lucy Crane from Cornish Lithium, UK. Before over to Lucy, just I need to a quick introduction that she is a geologist with a background of grassroots exploration. She holds an MSc in mining geology from Cameron School of Mines and master's degree in earth sciences from the University of Oxford. Before joining Cornish Lithium, she worked as an exploration geologist for alter strategies, planning and implementing exploration strategies for base and precious metal projects up to the drilling stage in Africa. Interesting. So we will hear shortly from Lucy, and let's explore that how lithium and Cornish mining is important for energy savings. There is no voice I can hear, so hello.
All of these low carbon technologies need to be built out of something. And actually, this fourth industrial revolution, we're seeing novel technologies being deployed at a scale that we haven't come across before, whether that's digital systems.
Oh. Hello, can you hear me?
Yes, I can hear you.
I'm so sorry. There has been a bit of a technical hitch with the pre-record. Let me just start again. I'm so sorry.
Problem. Yeah. Liu, if there is any problem on playing the record, we have Lucy on board so she can speak live.
If Lucy is able to, that would be very helpful. Thank you. I do apologize.
No problem. Lucy, are you there?
I can't unmute because he's not the co-host.
Liu, can you make Lucy co-host, please?
Hello, can you hear me?
Yeah, I can hear you. Yeah, welcome, Lucy. Sorry for this technical problems. Yeah.
No, that's all right.
I just.
Are you happy to share your screen?
Yep, I can share my screen. I can't share my video because that's not working, but I can share my screen. Can you see that?
Yes, perfect. Yeah.
Excellent. So if I go
Thank you. And very sorry. Yeah, please go ahead. Yeah.
That's all right. If I go on, can you hear that?
No, the voice is not coming.
Okay. Give me 1 second, then I'll just share a different version.
Yeah, it's a long file, so.
Sorry, everybody, I've just got a different version.
No, it's okay. It's okay. No problem.
Dun, dun, dun. So I'll stop sharing that one and I'll share this other screen. Hopefully the suspense is going to be worth it, everybody.
It is on the way.
Yeah, so I can start talking whilst I'm getting this up and running. So my name's Lucy Crane. I am a geologist based over in the Trimo Innovation Centre, which is just opposite the ESI in person. And Cornish Lithium is a company that's exploring for lithium down here in Cornwall. So lithium is a key element for this energy transition because of its use in batteries and battery storage. And I'm just waiting for this to load. So Cornwall has this in the southwest of the UK. We've got an amazing mining heritage down here. We have evidence of people mining tin and copper going back 5,000 years in Cornwall. And actually tin and copper extraction from underground hard rock mines has been big business in Cornwall for the last few hundred years. However, the last tin mine at South Crofty actually closed back in 1998. And since then, there has been no metal extraction in Cornwall. But that is not because we ran out of resources. Rather, it is because it became cheaper to produce it elsewhere. And so raw materials such as lithium have got a really important role to play within this energy transition. So hopefully now I can actually share my screen. Right, can you see that?
On the way. Yeah,
excellent.
We can see it. Yeah, thank you. Yeah.
Woohoo! So I wanted to start with this phrase, that everything we use in our daily life has either been grown or mined. That's everything, whether it's wood for trees and building work, but if you look around you, pretty much everything that you can see has been extracted from the ground in one way or another. And minerals really are fundamental to our existence. Whether they're recycled, whether they're from the Earth's crust initially, minerals and metals are vital to underpin our society. So with this transition to low carbon or even a net zero carbon world, the reason that we're going to be able to do that is because of low carbon technologies. If we want to stop burning fossil fuels, we need to have alternative forms of energy available to us, which is obviously what this whole conference is about. And we're actually seeing a rapid change in our daily lives. And these low carbon technologies are being deployed at a really unprecedented scale. So much so that people are starting to talk about this fourth industrial revolution. It's being driven by technology. And these technologies are using a whole range of minerals and metals, which are subject to global supply chains. So there are sometimes a lot of challenges associated with sourcing them. These low carbon technologies form things such as wind turbines, they form things such as solar panels. And if we're collecting energy from renewable sources, we need to store it. So battery technology, whether that's in our vehicles or whether that's on a grid scale, are going to become even more important over the next few decades. But to build all of these low carbon technologies, it means we're going to have to mine a lot of raw materials. And the fact that mineral extraction is going to play such a huge role in this energy transition is sometimes left out of the conversation. People quite often think of mining as dirty. It's quite an emotive word, whereas actually mining is the reason that we're able to build these technologies. And as the share of renewable energy rises, we need to mine more and more raw materials. So here are some statistics that came out of this report by the International Energy Agency last year, the role of critical minerals in clean energy transitions. And it's, you know, an onshore wind plant has 9 times the mineral input of a gas-fired power plant that's going to produce the same amount of energy. You're seeing 6 times the mineral inputs into an electric vehicle compared to a traditional combustion engine car, because the batteries and the technology driving it are so much more high tech. We need a whole suite of other metals compared to a traditional car. And so actually we're seeing that there's a big increase in the amount of minerals that we're needing to generate our power. And that's because the share of renewables is rising. It's the same IEA report does have some brilliant stats in if you haven't read it. And one of them is that if we want to reach the terms of the Paris Agreement, so less than 2 degrees of global warming by 2050, or by the end of the century, then we need to be producing 4 times as many minerals as we currently are today by 2040, purely to build these low carbon technologies that are going to facilitate the energy transition. If we want to get to net zero globally by 2050, then we actually need to be producing 6 times the amount of minerals, these are all from mines, than we are by today by 2040. So there's a huge challenge ahead of the mining industry. So in my mind, it's more important than ever that we do that as responsibly as possible. So this is where Cornish lithium comes in. Lithium is the lightest weight metal, and it's also got a really high charge density. So if you want a battery to be lightweight and portable, then lithium as your charge carrier is pretty key. And we're really seeing a massive global increase in demand for lithium because of its use in battery technology, and particularly its use in EVs. So there's a huge global demand for lithium. At the moment, most of it kind of comes from West Australia or South America, but more often than not, it's actually processed and refined into something that's battery grade in China. We've got resources of it within the UK, and so it kind of makes sense to start looking at what's on our doorstep. So what are we doing at Cornish Lithium? Well, we've got 2 different sources of lithium that we're exploring for. One is within the granite rock itself, and I'll explain a bit more about that in a moment. And then the second is looking at the potential to produce lithium from geothermal waters. So these circulate naturally within permeable geological faults underneath our feet, these deep groundwaters. They're very different projects, but the common thread running between both of them is we're looking to explore for in the most responsible way, extract the lithium in the most efficient way. We're also trying to build in circular economy design and principles. So we want to minimize our waste as far as possible. We want to maximize our production of byproducts or co-products, however you want to frame it. And we're also looking at using renewable energy to power our projects in the future. We're a private company at the moment. We've got about 65 staff and consultants based here in Cornwall. So we're growing pretty rapidly. We were founded in 2016. And this is what I just mentioned. A really important part of the business to us is doing things in the most responsible way possible. And as we're starting to develop our projects now, that's becoming more and more important. So my role at Cornish Lithium, I'm a geologist by training, as the introduction very kindly said, but I'm now the ESG and sustainability manager. And our team's role is very much to make sure we're delivering these projects in the most efficient way. So what do I mean when I say we're looking for lithium contained within the granite? Well, if you've ever driven down to where we currently are in Cornwall, and you've driven down from anywhere in the country, you'll have driven down a road called the A30, and it goes across Dartmoor, Bodmin Moor, the St Austell granite in the centre here, all the way out to Land's End in the west. And all of these topographic highs in the area are where the granite rock outcrops at surface. It's harder than the other rocks, so it hasn't eroded as quickly. And this granite is important for 2 reasons. Firstly, it's more enriched in lithium than a lot of granites around the world. And then secondly, it's also hotter than the rest of the rocks in the UK. And that's where we've got the potential for geothermal energy down here in Cornwall. There are certain pockets of this granite that are more enriched in lithium than other pockets. So this satellite image that we've got here is of this St Austell granite. And you can see it looks a bit like you imagine the surface of the moon might look in parts. There are these big white craters, and these are big open pit mines where china clay or kaolin is being extracted. And the kaolin industry has been going for nearly 300 years in this part of Cornwall. And it happens to be that some of these granites in this western flank are one of these high lithium granites. So what we're looking to do is go in and repurpose one of these old china clay pits and now produce lithium from it. So what does that look like in a bit more detail? Excuse me. So we're in an old china clay pit near Trafalgar Downs, and because it's an old china clay pit, we believe that by repurposing this, we can limit the potential environmental impacts, but there's also quite a lot of infrastructure in the region that we might be able to reuse as well. For example, there's a railway that goes from where we're looking to put our processing plant all the way out to the port. There's big warehouses and industrial sites where we can perhaps locate our processing plant, and we're already in an open pit. We're not looking to open another open pit, we're looking to repurpose an old one. So we've done a couple of rounds of drilling so far, which allows you to take samples from the rock we drill down to about 200 meters per drill hole, and that gives us the ability to sample rock all the way down to that 200-meter boundary, and then we can send those off for assay and come back and we can work out how much lithium is in them and come up with our initial estimate, our initial resource of how much lithium is in that open pit. And then we've done a thing called a scoping study, which has kind of been the initial engineering and economic design of the project. Could you feasibly design a mine that would allow you to extract that lithium enriched rock by quarrying it? Yes, you can. And if you add up the costs of designing that mine, extracting the lithium-rich rocks, and then extracting the lithium from those rocks, does it look like it would be economically viable for the lithium price that's currently out there? Absolutely it does. And we'd be looking to produce about 8,000 tons per annum of lithium hydroxide. You can cast your mind back a couple of slides. The UK estimates that we're going to need 80,000 tons per annum within the UK by 2030. So that's about 10% of the UK's needs. There is the chance that this might increase, as in what we might be able to produce in this project might increase on a yearly basis. So this is what the process looks like. First of all, we've got to quarry the rock, and then we have to crush it up, and we need to separate out the lithium-rich minerals, these lithium mica minerals, from the rest of the rock. So we crush it up, we then do froth flotation, which I always struggle to say, and separate out these lithium micas from the other minerals in the rock. It happens to be that some of the most lithium enriched micas tend to have a bit of a magnetic signature. So we're investigating the potential to use magnets to separate out the lithium rich micas from everything else in the rock. So that separates out our lithium rich mineral from the rest of the rock. Stage 2 is then this Lepidico process. So the Lepidico process has been designed by an Australian group, and we've done test work with them at lab scale and pilot scale. Unfortunately, it's all been in Australia because of COVID, but we're now in the process of building what we're calling a demonstration scale plant at our Trafalgar project. So that's going to allow us to try this, this whole process flow sheet at a scale that's significantly bigger than pilot scale. You're going to be mining a bulk sample of the rock and putting it through this process or this demo plant, which will give us a lot of information about things to tweak when it comes to scaling up to a full-scale commercial plant in a few years' time, which I'm sure many of you on this call can appreciate the challenges of that. So we have our lithium-rich micas, and effectively this Lepidico process involves dissolving that in acid and then adding lime to sequentially neutralize it. Different products drop out at different stages. That's a very simple explanation of what is quite a complex process, but it means we should be able to recover a number of byproducts, including cesium, rubidium, and potash, as well as creating a battery-grade lithium product on site, which is very exciting. And we believe that this process should have some environmental benefits compared to other processes which extract lithium from hard rock sources around the world. So this is what the timeline looks like. On average, globally in the mining industry, once you found a deposit, to building the mine and putting it into production is taking about 16 years. Whereas we're trying to do this in a bit more of a compressed timeline because there's such a global demand for lithium at the moment. So we are in the process of building our demonstration plant. It's going to be operating next autumn, and in parallel we're doing a feasibility study to do more detailed engineering design, more detailed economic analysis, and importantly, what are the environmental impacts too? What are the social impacts? So we started our baseline ecological and environmental studies that will feed into that project design. The geothermal projects are quite different. So I mentioned that we've got this big mass of lithium enriched granite underneath the surface of Cornwall. And we've also got these big geological faults. So these are just demonstrating quite how laterally extensive these faults can be. So these are narrow, linear geological features that are natural cracks in the earth crust. And these are there from when we used to be a tectonically active area. And historically, there are warm waters flowing within them at depth. And we know this because there's been so much historic mining in Cornwall. If you've ever been to the southwest of England, and especially been to Cornwall, you'll see that there are engine houses from the old mining industry dotted all around the place. And these engine houses are there because they housed big steam engines which were pumping water out of the mines. So the tin and copper that was mined for previously was contained within really steeply dipping narrow veins. And these steeply dipping narrow veins of tin and copper, if you wanted to mine them to deeper and deeper depths, you had to artificially lower the water table. And to artificially lower the water table, some of that water you're pumping out was from the meteoric rainwater, but some of it was these warm, upwelling geothermal waters, as we call them now. And in 1864, a guy called Professor Miller from King's College in London came and took some samples of some of these upwelling warm waters, or hot springs, as they used to call them, from one of the deep mines in central Cornwall. Took them back to his lab at King's College and analysed them, and found that they were unusually rich in lithia. So he ended up writing a paper to say, you know, these hot springs could be a potential source of lithium. It's a shame we don't have a use for it. So fast forward 160 years and here we are. So how on earth do you access these geothermal waters if they're circulating at anywhere between 1 kilometre or deeper? And how you do that is by drilling a borehole. So what we're looking to do is drill boreholes from the surface down to one of these geological features somewhere between 1.5 and 2 kilometres depth. We'll intercept these warm waters that are flowing naturally within these permeable geological faults. We'll pump that up to the top and then we'll put it through a processing plant. So between 1.5 or 2 kilometres depth, we'll have temperatures of about anywhere between 45 and 70 degrees Celsius. And that is, you know, significantly warm that you can actually do something useful with it. We're then looking to, once we've pumped that water up to the surface, we then need to extract the lithium. And there's a whole suite of new technologies that have been developed over the last few years that kind of come under the umbrella term of direct lithium extraction. And what that means is basically selectively removing just your lithium ions from the water. So your lithium's dissolved as lithium chloride, and these, generally it's either a highly selective membrane or an ion exchange mechanism, and it allows you to just remove the lithium ions from the water, and then you recover lithium chloride as a product. And when we started out 5 years ago, I think there were 4 DLE technologies on the market. I think we've now got something like 45 or 50 on our books. So it really is a rapidly evolving field of research. Nobody is extracting lithium on a commercial scale yet from geothermal waters anywhere around the world, but people are getting very close to it. So because there's so many different technologies out there, and they're all very context specific, we've actually set up our site at United Downs in central Cornwall to allow us to trial a number of these technologies. So we either store bulk samples of geothermal waters that we pumped up from one of our test holes on site here, and we can feed that through these processing plants. Or we have actually set it up so we could pump continuously from the borehole in the corner of this site as well. And we set this facility up so that we can trial a number of different DLE technologies and see which is most suited to the Cornish context. But I mentioned that these waters that we're pumping up are warm, and that's really exciting because if we're applying circular economy principles, how can we be as resource efficient as possible? Well, wouldn't it be great if we could find a use for that warmth? So either we could perhaps partner with people who want district heating schemes for houses, or local businesses and industry that use heat in their processes. And actually, the next borehole that we're planning to drill is on site at a place called Rodders, which is a famous clotted cream company down here in Cornwall. We're looking to drill a borehole on their site, and if it's successful, we'll turn it into a commercial plant whereby we will extract the lithium and they'll use the heat to help them decarbonise their processes. So it would be really lovely and neat. And then once you've extracted just your lithium ions from the water, the plan is that we would drill an injection well and kind of put that back down to depth. So looking forward, We're developing both of our project streams in parallel, whether that's the lithium and geothermal waters or advancing our Trelavo hard rock granite project. And we're really striving to do that in the best way, whether that's environmentally or socially. And actually, if done responsibly, responsible being the key word here, then mining has the opportunity to contribute positively to all 17 of the Sustainable Development Goals. But doing it responsibly is obviously the key part. So to sum up, lithium is a vital kind of enabler of this energy transition because of its use in batteries. If we're going to be creating energy from renewable sources, we need to store it somewhere. And actually, lithium is going to play a really key role in transferring that energy. As geologists, I think that gives us, we understand how the earth works, how the earth systems work, where to find these deposits. So it's more important than ever with this global scramble for natural resources that we explore for them and extract them in the best possible manner, minimizing our negative environmental impacts, maximizing positive ones, and the same for the social side of things. So I'll hand back over here, and I think we've got time for questions after the next session when we've got the discussion. Thank you.
Thanks, Lucy. Wonderful talk and lots of lithium information rarely, because lithium is one of the rarest elements that we are still need to deal with that. We have a couple of questions for you, but I think we should move to our next industry speaker. And after that, we will ask the questions to you. Is that okay? Lucy, hello. Oh, sorry. Okay, no problem. Thanks for joining and thanks for your wonderful lecture. We have our next industrial talk and we will hear from Dr. Hassan Bey. He's the Managing Director and the Chief Technology Officer of Build Solar UK. Before hand over to Hassan Bey, I would like to introduce him. He is over 12 years experience developing low carbon technologies. He has set up a state-of-the-art solar laboratory, teaches engineering courses, and supervises many students. His research interests including manufacturing renewable energy technologies, engineering design, nanofluids, sustainable materials, concentrating photovoltaics, electric vehicles, and space-based solar. He holds a British patent for the solar square technology, and at the same time, he is exploring patent opportunities in other countries as well. In 2019, he received the Cornwall Sustainability Award for Innovation under Sustainability category. With this, I'd like to welcome Dr. Hassan Bey. The stage is yours. Over to you.
Hello and very good afternoon to all of you. Before I begin, I just want to make sure if you're all able to hear me properly.
Yeah, we can hear you properly. And thanks for joining.
Thank you. Should I just, I'm gonna share my screen as well, just. So, are you able to see the screen as well now?
Yes, yes, yes.
Okay. Well, thank you very much for the invitation, Anurag, and I'm quite pleased to be here talking to people who have gathered from two of the most important universities that have shaped my career. I started my master's program at King Fahd University in 2006. I did my master's degree in mechanical engineering from KFUPM, and then I moved to UK to pursue my PhD with Professor Tapas Malik, with whom I have worked quite a long time at the University of Exeter as well, since completing my own PhD. So today's talk is basically kind of an amalgamation of progression in terms of research that has been carried out within our group, not only by myself, I would say, but there have been a lot of people who have contributed to the research that has been carried out. And I've been basically one of the patrons or carrier of taking the research forward into the commercial world. So with that, let me begin my talk. So I'm going to talk to you about a very innovative technology, which can be integrated within our buildings, given the rising costs of electricity, the growing concerns among energy insecurity across the globe. We are always looking forward for solutions which can make our future more sustainable. And today I'm going to showcase one of the technologies that we have developed at the University of Exeter and spin it out through our company, Build Solar Limited, in the form of a commercial product. So without any further ado, let me just dive into my talk. So the big challenge out there today is the growing consumption of electricity. This problem has been there from quite a while. You can see back in the history that right from back about 50 years back, you can see there has been a growing trend of increasing usage of electricity in different sectors. The most important sector, as you would identify through this particular site, is obviously related to residential and commercial buildings, which has been taking up a chunk of electricity for its daily consumption. Now, more electricity consumption means we have to further rely on a lot of fossil fuel resources. There has been a considerable change in the last few years where we have turned ourselves towards renewables, given the drop of the price of these renewable technologies, and we have tried to integrate them seamlessly within the electrical infrastructure that we already have got. But is that sufficient is the question. The answer is simply no, because there are a lot of challenges for the integration of these renewable technologies, which are not really perceived by people who are carrying out the research when they are trying to develop these innovative technologies. As a consumer, there are a lot more requirements for any kind of technology for it to be commercialized, which I'm going to talk to you about. But let's have a look at this very interesting figure. You'll notice that we have gone up almost 4 to 5 times in terms of our electricity consumption, and you can see particularly the percentages that of the electricity that is being consumed by different sectors is more or less the same, even though there has been a big change in terms of the time that the previous data has been captured. So we can clearly see almost about 25% of the electricity is typically consumed within the residential sector, and about 20 to 20% is consumed in our commercial sector. You'll see a big increase in the commercial sector or commercial buildings, because obviously there have been huge commercial buildings that have come up over the age, and they have got a huge amount of electricity requirements. So today the world faces multiple interrelated challenges, and we all want to deliver a sustainable, smart, and connected built environment. What I mean by that, I'll talk to you through. So if we see at the global share of the electricity consumption within our buildings, you'll see that today, if we talk globally, roughly about 35% of energy is being consumed by the buildings. These are some statistics that I just brought up from the International Energy Agency, as you can see. And you will notice that a big chunk of that electricity is again related to the residential buildings, which is about 22%. And because of this huge amount of energy consumption, there is obviously a huge amount of emissions that come out of it, which again can be seen to be roughly about 38% that is being contributed to the buildings. If you look more towards what happens in the UK, you will notice that the trend is pretty much similar from the global share, where we saw roughly that the percentage of energy that is being consumed in terms of electricity or energy is pretty much same within the buildings as well. And more importantly, you will note that, there is a huge amount of energy consumption that happens because of the heat. And because now we are talking about electrification of heat in order to make it more sustainable, then there is obviously going to be more and more demand for this increasing electricity, which means we definitely want more and more technologies or more and more commercial products which can provide us this electricity. In our future, we would obviously want to have cities which are built up, which are electrified, which adopt this new technology, which are far more connected than what you have previously seen. There is a growing need for electricity given the drive by the transport sector already, because there is a huge electric revolution that we are seeing through the introduction of both electric vehicles or e-bikes and whatever that is being charged using the electricity. Now, which means that there is again more and more demand for this electricity. Now, to meet this huge demand of electricity, the only options are to maybe to increase, the existing network that we have got in place, or to incorporate technologies which can be placed on the site of their usage. So think of buildings wherein there are technologies which are generating energy sufficient enough that can power that building, that can provide electricity to those existing electric vehicles out there. So things like that are going to really play a very important role going forward and transforming our cities of the future. Equally challenging is to make these things more sustainable. So we have to make sure that whatever technologies are going to go in there, they are more sustainable, they are more eco-friendly, they don't consume more of our energy resources that are available already, or the material resources that are available already. Which is what we want to do. We have set up a vision to seamlessly transform these buildings. How are we going to do that? We want to change the fabric of the building completely by bringing in technologies that can become a part of the building, that can be seamlessly integrated within the built environment and can create a very clean, smart, and healthier and more connected community out there. So at Build Solar, we want to move away from the standard technology that is already available. The reason to do that is when we took a poll of people, of about 100 people, you will always notice that majority section, more than 90% of people do not like the look of the panel or the solar technology, to which they are simply averse. You might have seen a lot of demonstrations going out in the public where people don't like the look of the solar panels in their simply farms that are out there, let alone their own homes. So buildings are all about architecture, where we want to inspire the space, where we want to integrate new technologies and new materials which are going to make it more sustainable, where it's going to bring in a new flavor to the building. It's going to add to the architectural value of the building and become not only a section of building that performs or generates electricity, but also is going to look brilliant on it. Which is where we bring our product called as Solar Squared, which is the world's first truly customizable, clean energy generating smart construction system designed to seamlessly future-proof our cities. It can be adopted in any color, any option as desired by the architects, and it can provide any kind of visual that is desired by the end customer, where we now want to make construction not only for the sake of construction, but construction as a service, where we are not only providing the end customer or the construction company just a product, but it is equally providing some form of service to the end customer through the generation of this clean energy, through forming a connection to the future, to the Internet of Things that are going around there. This is our product called as Solar Squared, which is one of our first products that we launched through the research work that we carried out at Exeter. It is a clean energy solution for buildings. It looks brilliant and it performs brilliant. It provides three different things that are mostly required by the building. It provides access to your clean electricity. It makes the fabric of the building more thermally secure. That means it insulates the fabric of the building. And third, most importantly, it provides ample amount of daylight within the building. It does not make it completely dark. Daylighting has been one of the very, very important qualities that are required within a building to elevate, the user experience or the building occupants experience. So it provides all these three in one simple product, which can be completely modular, can be scaled to any kind of scale that you wanted. Let me show you a very brief presentation about it.
40% of all electricity generated. With Solar Square, we can transform buildings from energy consumers to power generators. Solar Square blocks capture light energy but also allow light through, as well as providing heat insulation. Building integrated solar with Solar Squared.
So as you can see, the solution provides power, it insulates the building, provides ample amount of daylighting, is carbon neutral, is going to be cost efficient, is aesthetic to look like, and is completely scalable. All these are very important factors that need to be accounted in any kind of a building material, which we have tried to meet here. And hopefully going forward in the future, we will be seeing buildings that have got this product out there. The market that the company foresees is, quite big. The global share of the market of building integrated photovoltaic technology itself is projected to be about 19 billion by 2026. The UK 10-year infrastructure plan that is out there in place has got a plan of about 600 billion. The global micromobility market out there, which again, I'll show you an application where our product could be utilized, is again about 31 billion by 2029. And we have got an existing market or market share through our, one of our partners who makes the glass bricks currently, which is roughly about 180 million. There's a big proposed 250 billion UK Green Transformation Fund, which is going to be announced within the UK in order to completely move towards net zero. So we want to touch on these different sections that are out there. We want to reach out to these different markets which are out there and tap in our product in different shapes and forms, in different colors, and in different variety of uses. I'm showing you an example out here. This is one of the solution where it is adopted as an infrastructure. You can see this is an actual live railway station out in Berlin, which currently uses glass bricks. The only function that this glass bricks provide is ample amount of daylighting, nothing else. We want to transform this into future wherein they're able to adopt our product, which makes this piece of infrastructure not only a piece of infrastructure, but also a clean energy generating piece of infrastructure. Look at another example. This is another example in Canada where they're building huge blocks of building where they like to incorporate glass bricks. So we are planning to, just integrate our product in applications like this, where this product becomes a part of these buildings. Like I mentioned to you earlier, we were a spin-out company, which came out from the University of Exeter. This is us when we got the award at the Cornwall Sustainability Awards in 2019. We have worked alongside a number of partners. These include a number of regional partners, international partners, and finance partners as well, more particularly the Building Research Establishment in the UK. We've had a lot of traction since we announced the product. Our work has been published in a lot of these commercial journals out there, commercial magazines out there, and they have all really liked our product. This is some more traction that we have got since the inception of the company, where we had received, inquiries from big construction companies, be it from Saudi Arabia, be it from Google Sidewalk Labs, be it from Foster and Partners, which are one of the biggest, construction agencies in the UK, be it, Vicinity Centers, which are one of the biggest shopping mall owners within the Australia. Once we had showcased, the concept out there was a lot of interest that had come in. So obviously we had to move from our concept stage to actual prototyping and actual manufacturing of the product, which is where we are at right now. So this is one of the first prototypes that we had developed, showcased here. This is a picture taken up again at the Environment and Sustainability Institute, which has been one of the most important pillars for this particular company. These are the kind of electrical output that we can see from the product that we have made. So you can see roughly the efficiency of the block is about 10.33%, but it has got a daylight transmission of about 87% of the light is being transmitted through, which is state of the art compared to any other PV device which is out there. Now, once we have developed some prototyping and when we were working on the projects, we were again in contact with a number of players out in the UK. One of the important players has been Network Rail, who's looking for converting their entire car park that you see out there through and change it into a new kind of a building, which will not only be a car park in itself, but also power e-bike charging, or maybe provide further electricity to meet all the daylight or lighting needs within these car parks which are out there. We work closely with them and we have conceptualized some more concepts. I can't go more in detail on those, but I'm going to just show you some quick pictures which are reflective of what we were trying to do. The idea was again to incorporate these sections of walls which can be along the railway track side, so that they're again able to provide daylight within the areas where they are incorporated, but simultaneously provide certain amount of power, and more importantly, may be able to provide some kind of Internet of Things or 5G hosting that might be required by most of the places which are kind of a bit remote within the UK. This is one of the proof of concepts of our e-bike charging hub. So you can see where we can customize the whole section in any kind of color that is desired by the end customer. And we can replicate any kind of maybe logos or any designs that is required by the customers. So the whole idea, as you see, is not only to have infrastructure or buildings which are just there for the sake of being a building there, but we want to make them as sustainable as possible. We want to provide certain amount of power, and we want to host some other innovative technologies out there. There are other pieces or other lines of products that we have developed where we can have a complete opaque system. Obviously, there is a requirement of spaces where we require certain amount of daylight, but equally there is a requirement of spaces where they would like to have it completely opaque. The good thing of having it more opaque is that we are able to incorporate any kind of solar technology. We heard a lot about perovskite solar cell technology today. So equally, there are options for us to incorporate the standard silicon solar cell technology or the perovskite solar cell technology within these designs that you have seen out there. We want to add more to the buildings. We want to, have more kind of sensors, for example, within the buildings, which are able to provide a lot of information which is useful for the management of these buildings, which are useful for maintaining the health of these buildings going forward, and can report directly or intermittently as required by the building facility managers. So these are just two of the options. While working with Network Rail recently, we did another project which was called as Smart Solar Walls, wherein we partnered with a number of other companies like a rope like catapult. So wherein we were trying to again develop some smart solar walls which incorporate bifacial solar cells, and they pretty much incorporate standard solar cell technology in there, but definitely have a bifacial element in it. The technology is capable of harnessing power even when part of the cells are shaded, so it has got some dynamic shading related involved into it. I can't talk much about it, but just going to show you here. So the objective, again, while working with Network Rail, was to see what kind of power we can harness from them. So there's about 20,000 miles of railway that is available in the UK, and that can be transformed into a total about 18 gigawatt of power using our solution that is out there. So I'd like to conclude my talk. I think the main things that we have seen here is that buildings are one of the major consumers of electricity, and it's very important that we transform them not just for today, but for tomorrow, to make them more sustainable, to make them more connected. These are very high on the priority list of our governments within the UK, and I suppose worldwide. So we want to work alongside as many partners as possible, be it people who are working within research, where we are able to adopt upcoming technologies into our product or come up with new commercialization products. So I'm very open to having discussion with anybody who is out here who wants to really commercialize something, and we can play a very significant role to do that. We hope that through incorporation of these new technologies, we are able to achieve the targets that have been set out by the government about net zero, and bring our domestic and commercial buildings to a more sustainable future, and have as low carbon footprint as possible. So I invite you all together to work alongside with me, and let's together build solar. Thank you so much for your time.
Thank you so much, Dr. Hassan, for your wonderful talk. And I think people are interested, your build solar and solar square technology. That looks very promising. We have a couple of questions, and I hope you have time to answer them. So I will pass you the questions. So if possible, just try to address. We have question from Ravita. She's saying that what about the cost of smart solar walls and their payback period?
Well, right now, the kind of work that we have done, we are hoping that they will pay back within 3 to 6 years, depending upon the kind of location they are incorporated, because that plays a very significant role. You must know that there is a different amount of solar energy resource that is available at different places on our planet. So depending on where they are placed, we anticipate the payback to be roughly about between 3 to 7 years.
That's great. Another question from Shubhranshu here. He's wondering about, as a beginner in concentrating photovoltaic field, how one should consider the nature of concentrated optics for photovoltaic application.
Well, it's a very tricky question because, having worked quite a lot in this particular area, the key learnings that I have had is, the time when concentrating photovoltaics was really, really hot was when the cost of the solar cell technology was high. So from that peak, it has really changed to the current time where the cost of solar cell technology has gone to be much lower. Now, so it is very important to see exactly that the technology that we are working is not only just providing a concentrator for a concentration state, but maybe what beyond that. So these elements, what beyond that is what are really, really important to look into.
That's great. We have, I think, another questions again. Sriram is asking about what would be the lifespan if you are expecting for solar brick and the solar wall?
Yes. So we expect them to have a very typical lifespan of about 25 years, as you would see with the traditional solar panels. So that is the kind of lifespan that we are anticipating. The good thing about the product is that, when you are having any other construction material, it is just going to go and sit there on the building without generating anything, without paying for itself. What we are hoping that, within that 25 years of time, the product that you have placed on the building not only, pays for its own energy that has gone into making the product, but also generates enough revenue back so that, you're basically getting back the overall investment that you have made to make that wall or the building.
Great, thank you very much. I have one, I'm wondering, actually, it's not a question, how this, the solar square technology, we can able to take it as space science.
Space sector is totally different. It's one of my interests that I have talked to you about, but certainly not the solar square technology that will go to space. There are some other different technologies that we might have to utilize. There's a good talk on YouTube from myself if you want to have a look at it.
Good. It's good information. We must watch and subscribe and like. Okay, thank you so much. I think no question for Hassan, but there is some questions for Lucy. Are you there, Lucy? Yeah. Cool. Yeah, I can see you can unmute yourself. Yeah, thank you. Thank you for joining, Dr. Hassan, and thanks, Lucy. I have a few questions for Lucy now. Professor Naziruddin, I was wondering about that. How much percentage of cesium in available or presence in lithium?
Oh gosh, that's a very good question. So I think there's approximately the equivalent amount of cesium in the rocks as there is rubidium, as there is lithium. I'd have to double check that for you off the top of my head. But, there's appreciable amounts of cesium within the rock. And it forms, lithium and cesium kind of like to hang out together in granite rocks. So you quite often find them in the same kind of settings.
That's great. Thanks. Another question for you, Lucy, that how the thermal runaway can be avoided in lithium-ion batteries.
I did see this one pop up in the chat, and I have to say it's definitely not my area of expertise. Our expertise is in finding lithium and not in creating batteries. But I believe that the design of the battery cells can have a significant role to play, as can the materials that you're using within this lithium-ion battery cell. So your separators, for example, you want them to have a high melting point and things like that. But I'm afraid to answer that in any more detail is beyond my capability. I'd have to Google it for you. So, thank you. I've got a question for Hassan, actually.
Please, yeah.
Hassan, what do you see as your major challenges in scaling up to, these big construction sites? Do you think you've got scale-up challenges, or is that all ironed out now at the stage that you are?
Sure. I mean, given that, the product that we are working on has to be mass manufactured. So mass manufacturing has been one of the challenge that I'm working on the past few years. So I have formed really good partnerships with a number of different companies to enable us to do the mass manufacture. Having been based in Cornwall, it was a bit, difficult initially, given, the remoteness of Cornwall, and there are not a lot of companies which are out there which would help us to do that. So obviously I'd had to look elsewhere. So I have now formed a very nice lineup of partnerships to do the overall. So hopefully in the years to come, we will help unlock this challenge, and maybe a complete facility will come up at Cornwall as well to do the entire manufacture and assembly line.
Yeah, it'd be brilliant if you could do that locally. It really would.
Thank you.
Thank you. We have one question, I think, Yusuf.
Yeah, I have a brief question for Lucy.
Go for it.
Yes, Yusuf, please go ahead. Ask your question.
Yeah, my question, Lucy, is regarding as geologist yourself. I just want to ask, which one is more sustainable regarding mining lithium battery for storage, or going to hydropower as a storage system to be used in the larger solar farm installations?
Sorry, what was the second? The line cut out. Lithium for storage or
hydropower pumps.
Hydrocarbon for storage. I think overwhelmingly lithium ion batteries are. So life cycle assessments are a really useful tool in looking at, it's almost like a way of environmental accountancy, isn't it? And I think generally we're seeing that if batteries are designed in a good way and the materials going into them are extracted in a responsible manner, then, you know, I think that's the future, because the impacts of burning fossil fuels and hydrocarbons is really significant on global warming. And if we want to meet the terms of the Paris Agreement and limit global warming to less than 2 degrees, then really phasing out fossil fuels as quickly as we can is going to be a really key part of that. So I think we are going to see this global shift to battery technology for storage.
I was talking about hydro pumps.
Okay.
Hydrocarbons, so hydro pumps as a storage system to be integrated with a large solar farms where you can reduce the mining activity.
Okay, I have to say I don't know enough about that. So if you wanted to send me an email, maybe we could have a discussion. I can tell you what I know about batteries, and you can tell me what you know about that, and we can discuss. But I'd be very happy to follow up afterwards.
All right. Thank you so much for your time.
Thanks.
Thanks a lot, Yusuf. Thanks, Lucy, as well. I can't see any question at this moment. I have a question for you, Lucy. What do you think that the lithium is one of the rarest element we know? So what do you think that the extraction of lithium is quite challenging, or you know, we are running out of lithium? What do you think about the future of lithium?
So lithium is actually not as rare as people might think it is. What's difficult is finding it in places where it's kind of concentrated enough to make it economically viable to extract it. And we're seeing this massive global increase in demand for lithium because of its use in lithium-ion batteries, as we've just been talking about. And you know, estimates range from us going to need something between 40 and 60 times the amount of lithium that we're currently producing by 2040. If we want to build all of these battery storage technologies. And so the kind of race to find lots more resources of lithium around the globe is already on. And we've seen that. I think the price of lithium is 10 times what it was 2 years ago, because there's so much demand for it. So the challenges rise in, is the mining industry going to be able to find deposits of lithium at a rapid enough rate to be able to facilitate the energy transition, as lots of people have kind of forecast that it'll happen, because it's not, as you said, you know, it's not actually that easy to find a mineral deposit. And then, you know, it's a long lead time. On average, globally, it's taking 16 years once you've found your deposit to actually bringing it into production. There's a way that you can kind of compress those timelines a bit, but you don't want to be cutting any corners. So what we're looking for in Cornwall, lithium from these microminerals in the granite, and also in geothermal waters. Globally, these are considered unconventional lithium resources because nobody's producing lithium commercially from them at the moment, because the technology to extract the lithium didn't really exist 5 years ago, not on a commercial scale. So I think that's what the challenge is going to be, finding enough of it and doing it responsibly. Just need to make sure.
That's really critical, I understand. And I'm just wondering that in one of your slides, I think you have mentioned that Cornwall is one of the highest lithium storage across the Europe. So is it just a traceable lithium, or the lithium mining has already started?
No, it hasn't. It hasn't in Cornwall. So we're looking to develop our 2 projects. There's another company called British Lithium, who also have a project in St Austell, but no, we're all a few years away from commercial production yet.
Oh, interesting. So yeah, that's a great. I think one more question. Yeah, let's see. Okay, a question for Hugh. I think it's supercapacitor, so based on lithium, I guess, from Vasant Kumar. So he's asking about nowadays researchers are focused on a new field like supercapacitor, I think, which is composed of supercapacitor Capitry, which is it's a capacitor and battery combinations, looks like, yeah, which is composed of supercapacitor and battery. Yeah, so which one best for energy storage application?
I'm afraid that is beyond my expertise. But Basanta, if you've got an opinion on that, it'd be really interesting to hear. I don't know if you are able to let us know.
Yeah. No problem. So if you have any questions or anything, just feel free to, we have some time still left, so we can discuss it. Otherwise, just I hope that Lucy and Hassan will allow to accepting emails if anyone has any queries.
Yes, definitely.
Definitely. That's great. Thank you very much, Dr. Hassan and Lucy, for joining us. I know how busy you are and giving us your valuable time to us. Thank you so much. Yeah, see you. Yeah, bye. So we are almost end of today's session. The day is going to end, and before going to the closing remarks, I'd like to, invite Professor Tapas, who is going to announce the winner of today's quiz. So, Professor Tapas, over to you.
Yeah, you can hear me okay?
Yes, we can hear you.
You can see me also, right?
Yeah, we can see you. And yes, you are visible. Okay. All clear. Yeah.
Okay. Perfect. Okay. Thank you, Anurag. I mean, this was a very good idea of including incorporating some questionnaires in a various different aspect of related to the energy science, essentially. And we have a lot of interest. I think there was more than very close to 40 people participated. Unfortunately, I mean, everybody couldn't. We wanted to give prize to everybody, but we couldn't give it to everybody. And two of them came out quite top. One in terms of the top scoring possibilities, which is 150 out of 150. Another one was extremely fast, I have to say. I mean, there was 15 minutes for the questions, and the second one, although it's not the overall score-wise highest, but time and score, if you factor them, that is quite remarkable. And this was answered in 4 minutes, 38 seconds, and scoring 110 out of 150. And so what the organizer they decided is to award both of them. And these two names are one in Vasant Kumar P. I don't know what P refers to, but that's how the name is written in the form. And another one is Ilaraman M. Both of them from India, simultaneously scoring 100% or, as I said, 150 of 150 as well as 110 and 150, but within a very, very short time, 4 minutes 38 seconds. And congratulations to both of you. And our team will be in contact with you for the certificates, as well as the prizes, Amazon voucher, which Anurag has said, and a big congratulations to both of you. Yeah.
Yeah, thank you very much, Professor Tapas, for declaring the winners. Wonderful, and congratulations to both of you. As Professor Tapas has mentioned, that the two winners, we have their email IDs already, and I will contact both of you shortly after the conference regarding your prize. So both of you have the Amazon vouchers, both rupee with almost 25 pounds. So you will receive the voucher soon in your email. So I will first contact you. So congratulations, everyone. We have received, as Professor said, that almost 40, close to 38 entries, and all are very close to each other, just almost 4 minutes 38 seconds, 4 minutes 42 seconds, like this. But as a terms of games, so please take it in a sportingly, and don't worry, we will have more in future conference, then we will organize more quizzes for them. But in this event, thank you so much. I can see Vasanta has chat. Okay, so his full name is Vasanta Kumar Palaniswamy from Madurai Kamraj University, India. Congratulations, Vasanta. At the same time, another winner. So I will get in touch with both of you in email. So please stay connected with us. And this is all for us today. So we are almost 10 minutes ahead of this session, today's sessions. So if anyone has any questions, so please ask me or in the chat box. We have still 10 minutes time, so we can discuss it. And at the same time, it's a 2 days conference. So just let you know that tomorrow we will be again meeting at 9 a.m. sharp. 9 a.m. sharp time, UK time. So please, you have received 2 different joining Zoom links. So this link, today's link, will not be activated or will not working for tomorrow. So you can see in your inbox there will be another email. Please check the date. Tomorrow is 25th. So 25th of November, there is separate Zoom link. Use that one and please join us. We will start the conference day 2 tomorrow, sharp 9 o'clock UK time. And again, the conference will be divided into 3 different categories. One from academia, another is from industry, and third one is from the ECR. So you can have an exploration of different speakers across the globe. And of course, energy. Tomorrow we have more speakers from battery and supercapacitor fields. So let's see how we can explore those recent materials research, at the same time how we can implement those technology in terms of commercialization. So please join us tomorrow 9 o'clock sharp. As I mentioned, there is a separate Zoom link for tomorrow's joining. And if you have any questions, please feel free to ask us. We are available up to 4 o'clock, 10 more minutes. So yeah.
I think, Anurag, you can stop the recording now.
Yes, yeah, we can stop the recording. Thank you.